Okay. Welcome to APEC. It's September 28th, 2024, and I'm your moderator, Tim Ventura. We are streaming for the first time in full 1080p HD resolution. I am so excited to have this up for you guys, and I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. We're broadcasting across a couple of different live stream channels. The main one is the Alt Propulsion channel on YouTube. I would love it if you guys are able to sign up for that and basically follow it. Follow what we're doing. We have a lot of material going up. Today is a tremendous day in APEC history. We have a collection of really, really amazing presentations by some truly groundbreaking presenters. And one of them that I've been following closely and personally involved with is by Jarod Yates, who's going to give us the results of extensive research into the ARTS-Parts purported UFO sample that has been under analysis at Falcon Space. Again, we have done visual microscopy on it, metallurgical microscopy, SEM microscopy, and we're looking at doing Raman spectroscopy as well. So there's a ton of analysis that's been going on there. Jarod has also done a ton of historical research as well into work in the 90s by Travis Taylor and Linda Moulton Howe, as well as more recent scientific research into things like quasicrystals. So that is a big one. But before that, Dr. Hong Du is going to be discussing a practical method for producing anti-gravity based on rare antigravitational hydrogen atoms. And this is actually based on something I had read about in the news a few years back, if I remember correctly. After that, we're going to have Sky Darmos discussing composition-dependent gravity and a new model for gravity-controlled spacecraft. And Shiva Meucci is going to be giving us a talk about mainstream physics models, mistakes, and misconceptions. And Shiva is absolutely wonderful as well. I love his work because he goes back through history. He's able to look at experiments and look at things that could have been done differently and what that might tell us about where science could be, should be, and may go in the future. So again, today's event is broadcasting on StreamYard through the Alt Propulsion YouTube channel. That's our primary. If you haven't subscribed, please do so now. So let me get started. I want to welcome our first speaker, Dr. Hong Du, who is talking about a practical method for anti-gravity within a GUT framework. So I'm going to bring him into the stage. Hong, welcome, sir.
Good morning, everyone.
And it looks like your camera is turned sideways again, but that's a. We'll see if we can get that.
Do you want me to tilt it up?
Yeah. There we go. Does that work well?
Well, I have to spend some time to take care of it.
No, but you know what? You look great and you sound great, and that is the important part. So thank you so much for joining us. So what I'm going to do is turn everything over to you. I'm going to take myself off the stage. You can use the back and forward button for slides, and I will be here if you need anything.
I don't know how to control the slides, but
okay. So if you put your mouse over the slides, if you put your mouse over the screen, there should be back and forward buttons right there.
Let me see if I can do it. It's not moving forward. Should I just click the present button and then move back and forward?
So, you know what? Let me do this one. Let me try this one. So now move your mouse over the actual slide deck on the screen. You're in Google Chrome, right?
That's right.
Yeah. If you move it over the screen, you should have a little bar that comes up. It should say slide number, and it'll have a list, and then it should have back and forward buttons.
I only have present, hide chat, exit, full screen. I'm not sure where to look for that forward and backwards.
So the slide deck, the one that's Not the small one, the main one, the one that's right next to us, the video on the main screen. In the actual video itself.
No, I cannot find it. That's weird. Let me just click slide.
So on the screen, right, there's a picture of, there's me talking, and then you right below me, and then the slide deck is right to the right of us. It's the big one on the main screen. If you move your mouse over that, you should see a little bar that pops up. It should
It
be.
didn't. So that's weird. This computer is strange.
Okay.
Even
Well,
because of my camera.
so if you'd like, I can just say back or forward, and I can advance the slides for you. We can do it that way.
Okay.
Okay. So I'm going to take myself out, and I will be here.
Okay. I'm going to present a practical method for producing anti-gravity in a framework of grand unified physics. I'm an independent researcher. All my work can be found at my ResearchGate website. Can we move forward? First, I'm going to give a self-introduction, and then I'll give the background of anti-gravitational research, and then short introduction of grand unified physics, and then how do we do anti-gravity in unified physics? And then I will present observational evidence of repulsive anti-gravity and experimental evidence of repulsive anti-gravity. There are some experiments that are existing for the charge-based gravity, which is the foundation for the repulsive anti-gravity. And then I will give some kind of a background on the naturally occurring particles carrying anti-gravity. And then I will introduce the practical method to concentrate the antigravitational hydrogen. And this, for this, I filed a patent. The application of antigravitational hydrogen will be just tremendous. Next page, please. First of all, myself, I have a bachelor's degree in physics. Then I got a master's degree in nuclear physics instrumentation. And then I got PhD in optical physics. Right now, I have the training in radiation oncology physics, and I'm a medical physicist. Over time, I've worked on multiple projects, including the gamma ray Compton scattering, inertial confinement fusion with laser pulses, and I used the CCD cameras to study the light scattering in the atmosphere by aerosols. And later I did the amorphous silicon flat panel X-ray imaging with a mercuric iodide photoconductor. And I currently using radiation like X-rays, gamma rays, and beta rays to treat cancer. Next page, please. We have learned that the gravitational research has been going on from like many hundreds of years ago. But the breakthrough was made by Galileo and Newton, and they discovered the universal freefall and the universal gravitation. But the gravity is always mythical because it's extremely weak and it's hard to do it in a laboratory. And there currently are a lot of uncertainties in measuring the gravitational constant, and no elementary particle level gravity has been ever tested until just recently. That was done maybe a year ago by CERN. Um, r- right now, general relativity becomes the uh, academically accepted theory on gravity. It features the equivalent principle for gravitational mass and inertial mass and the universal free fall, and then the warped space-time by mass. Next page, please. Well, we have know a lot about gravity, even we don't have the most fundamental knowledge about gravity. But the anti-gravity research is not that well known. Regardless, its importance is tremendous, because if we wanted to travel in space freely, we have to overcome gravity. Gravity is currently unsupported by general relativity because general relativity features the universal freefall and warped space-time. So there are ongoing efforts in anti-gravitational research. You can find them in our wiki page for reference. There are a very long list of commercial entities, government and agencies, and individual researchers. In the 1950s, it was overwhelmingly active, but right now it's dwindling because it's not very fruitful. Exhaustive attempts in theories and approaches from all possible directions have been carried out, but it's unclear if the theoretical breakthroughs can take place or whether it's possible or not. And currently, there's no practical methods to do so. There are still some support for anti-gravitational research if you are interested. There is a Gravity Research Foundation. It is currently awarding selected papers each year, and it's up to $4,000 if awarded the first place. And there is another one, I'm not sure how to pronounce it, Goldie Award. It promises to award 1 million euros for floating 20 grams of matter in about like 10 centimeters from support for more than 1 minute. Next page, please. The majority of the anti-gravitational research is unfortunately currently not supported by institutes or other official venues, because the mainstream gravity theory doesn't support anti-gravity. For example, general relativity just refuses anti-gravity because of the equivalence principle, universal free fall, and gravity is not a force, but the warped space-time. So when you see universal free fall, then you have no hope, right? Everything must fall. But there are some researchers trying to use existing known theories to counteract gravity. You can just reduce the effect of gravity or even maybe create anti-gravity, not using gravity itself. So there are electromagnetic methods that try to use static electric charge to overcome gravity. And there are gyroscopic methods. There are many other physical theories, including superconducting, vacuum, quantum theories, mass manipulation, effects, and so on. You can Google or you can listen to the presentations at APEC to figure out. Next page, please. So the grand unified physics is a theoretical breakthrough for practical antigravity research. So in this framework of grand unified physics, all natural forces will follow the same equation. They're not different from each other. So, gravity is just another kind of force, like electric force. Space and time are absolute, equal, and universal. Dimensions of space and time are independent, just within the 3D space. Each dimension is independent from another dimension. But dimensions of space and time are all orthogonal. That's just like in the 3D space. X dimension is perpendicular to Y dimension. Next page, please. So if you look at the grand unified physics equation, you will see that the space and time are just treated equally. If you look at dx, dy, dz, and this c dt, they are just indistinguishable. I mean, you can just treat time as space and they can add them together. In the 4D space, if you want the absolute distance, you can just do the squared sum of space and time. And if you measure the time in the 4D dimension, you just do this absolute distance in the 4 dimension space-time, and then you divide by a constant of c, which is the speed of light, and you will get the time. It's very straightforward definition. If you run through all the equations, you will see that dt, which is time, is actually the proper time, which is independent of locations, divided by square root 1 minus v squared divided c squared, and you know it's the Lorentz factor. So it is downward compatible with existing relativistic theories. And the most important equation about the grand unified physics is the equation of total energy. It is the squared equation of total energy equal to the rest mass energy, which is m0c squared, times this is the equation. The big bracket has the equation about the forces, including electric force, gravity, and any other possible forces added together and divided by the master race energy. And then the other factor, the last factor is just the absolute distance divided by absolute time. And it is simplified as a easier like equation, which are all squares. So you recognize the special relativity factor of gamma, and then the general relativity factor eta, which is or zeta, which is the effect of different potential energies corresponding to different natural forces. So how to describe all of the forces in unified physics formation, equation? It's just like the electric charge. The potential energy is a constant times the product of product of the charges and then over the distance. So it's uniform for gravity, for electric charge, or any other charge possible. Next page, please. So grand unified physics is downward compatible with the existing mainstream physics. If you ran the equation, the first order approximation gives the Newtonian physics, and the factor gamma corresponds to the Lorentz factor covering special relativity effects, and the factor zeta covers general relativity effects. General relativity, grand unified physics clarifies some physical concepts, and it abolishes some common misconceptions, like it renovates the concept about the absolute space and absolute time. It redefines speed as space over proper time, not the regular time. It eliminates space contraction and time dilation, even they are explained differently inside the grand unified physics. It re-establishes observer-independent physics. This is very important. In grand unified physics, nothing is observer dependent. Next page, please. So how do we study anti-gravity in unified physics? As we mentioned, conventional mainstream physics won't do anti-gravity. But in the grand unified physics, all natural forces are expressed by the same equations. For example, we know that the electric force is defined by the fine structure constant. If you write the potential energy of the electric force, you will get the sum of all the charges over distance and multiplied by the constant of C, H bar, and alpha. Alpha is the basically it's the fine structure constant. H bar is the what is this name? It's just a Planck. It's called a reduced Planck constant. C is the speed of light. We know that all the charges are free to be positive and negative integers. So that's quantumized integers, but they can take positive and negative values. Then for gravity and anti-gravity, it's a little different, but it uses the same equation, which is potential energy is equal to C times H bar times beta, then the product of gravitational charges over space. So beta is like a fine structure constant, but it's for the gravity, which is a large scale constant. So I use the same equation for both gravity and electric force. And the most important thing is that the gravitational charges, I denote it by eta I, eta j, which are the individual charges. They can be freely to be positive and negative, and they are integers too. So when you think about our existing gravity theories, we always think, oh, the gravity is proportional to the product of masses. And masses, they are always positive. But in grand unified physics, we are using charges. It can be positive and negative. And if you want anti-gravity, just flip the sign of the gravitational charge and you get anti-gravity. That's very simple, right? Next page, please. So in Newtonian gravity theories, We always do gross macroscopic level physics. We never do like particles. Mass Mi or mass Mj are always positive. There are no possibilities of getting a repulsive antigravity. Einstein's general relativity is the same. It actually comes from Newtonian physics. It is also a gross macroscopic level gravitational theory. It just used a more fancy mathematical tensor curve fitting to the Newtonian gravity with m, which is mass, and mj. They are just Newtonian quantities. There is no possibility of getting repulsive antigravity because m, which is the mass, never changes signs. But in grand unified physics, antigravity is quantized microscopically. This is very important because we only do physics at the elementary particle level. We don't do physics at the macroscopic level because macroscopically things got changed. For example, if you want to study charge, electric charge, you never want to study the charge of a regular mass because each mass contains billions or trillions of charges inside it. There's no way you can study that. So in grand unified physics, I got this potential energy described by the product of eta, and eta can be similar to the mass, but it's at the microscopic level, and it can be positive and negative, which is impossible in regular physics. Then we go to next page, please. So how big is this, I call it a large structure constant versus the fine structure constant? How big is this beta? If you do the calculation, you will find that the beta is approximately 10 to the minus 39. It is the dimensionless large structure constant, about 36 orders weaker in magnitude compared to the electric fine structure constant of about 1 over 137. Notice that only particles with the same sign of gravitational charges tend to attract and merge into celestial bodies by attractive gravity. This is a little bit different from the electric force, because for electric force, if you have the same sign of charge, they repel. But for gravity, that's a little different. If you have the same gravitational charge, they don't repel, they attract. Next page, please. Antigravity in grand unified physics shows that only particles with the same sign of gravitational charge tend to merge and grow into celestial bodies. This is very important and is self-evident. Think about this. If the universe want to form into celestial bodies from a large number of particles, only attractive particles can stay together. Repulsive particles will always or spread outside. And for the same self-evident logic, but slightly different reasons, only matter particles can be locally observed. Because if you have matter and antimatter, they will just electrically attract together and then annihilate. So if people talk about why we only see attractive gravity, why we see more matter than antimatter, I would say these questions are not questions because if the opposite is true, then it's impossible, because how can you form a celestial body like our Earth if there are they repel each other? If you have antimatter, how can you stay on Earth? Because they will be annihilated instantly. So these are not questions. There people are not careful about logic. And actually, nature utilizes the this kind of repulsive, attractive matter and antimatter to form the universe. There will be matter and antimatter world. There will be attractive gravity altogether versus the repulsive world altogether. I will give more details how they can form uh, celestial bodies with repulsive and attractive gravity. This is very interesting. And then there are if you are careful, you will be able to see the repulsive and attractive gravity um, if you look far enough. Next page, please. So how the gravity, antigravity, and matter, antimatter can form four worlds symmetrically by flipping the signs of the gravitational charge and the signs of the electric charge. So you see the four circles. The red circles are antimatter worlds. There are two types of antimatter worlds. What is antimatter? Antimatter is defined by the opposite electric charge for the same type of particles. For example, if we talk about proton, if the proton carries positive electric charge, it's matter. If a proton carries negative electric charge, it is antimatter. If they come together, they will attract because of the opposite signs of electric charge, and they will combine and annihilate. So antimatter and matter, they cannot stay. They will just repel each other. I mean, naturally they repel each other because the proton and the antiproton will repel. If you look at all those big big yellow cross arrows, that's how matter and antimatter are repelled by the charge, by the electric charge. They cannot do that. They cannot. Let me say if I say something wrong. Yeah, they cannot come together. If they stay together, they will just annihilate. And then for the gravitational charges, only the same signs of gravitational charges can come together. But gravitational charges can happen, like the sign of gravitational charge can freely be positive and negative in both antimatter and in matter world. So if we already considered matter and antimatter based on the electric charge, then within matter worlds, there are two matter worlds. One matter worlds have positive gravitational charges. The other one has the negative gravitational charges. And how do they come together? Only the matter with the positive gravitational charges will come together. If the negative one is close by, they will just be repelled. But all the negative gravitational charges will come together because they attract each other. So gravitationally, for the same matter world, there will be two worlds. One has the positive gravitational charges. The other world, the matter world, has the negative gravitational charges. And same thing in the antimatter world. There are two possibilities. In the antimatter worlds, they could carry positive gravitational charges, or they could carry negative gravitational charges, but only the particles with the positive gravitational charges can come together. And only those that have negative gravitational charges come together. So there are two antimatter worlds. One have mostly positive gravitational charges. The other one has negative gravitational charges. So in total, there are four worlds just because of the symmetry between gravity and antigravity and matter and antimatter. So there are four worlds. I have the four circles indicating each one. If you look at them and look at the possible gravitational interactions, you will see that between the matter, two matter worlds, they repel each other. And between the antimatter, the two antimatter worlds, they repel each other because of the opposite signs of gravitational charges. And then you look at the matter world with the underwater world, they also could attract or repel each other. So if you run all the possibilities, you will see that there will be more repulsive, gravitationally repulsive forces than the attractive forces. Basically, you count the number of arrows. There are four blue arrows which attract each other. There are four repulsive, one, two, let me see. Actually, the four blue arrows, they represent two interactions, right? Because the arrows are attracting each other. That should be connected. So see the opposing top two blue arrows, they should be made into one big attractive arrow, but I don't know how to present it with a one bar. The bottom two blue arrows, they attract each other. So that represents two attractive forces between the matter world and matter worlds and the antimatter worlds. But among the other interactions, they are all repulsive. So there are possibility of four repulsive cases versus the two attractive cases. So there are more repulsive forces in the nature than the attractive. That's why the universe is actually repelling, and they are leaving each other at accelerating rates. So we know that because of the symmetry, there are many interesting things that can happen. If you look at the bottom left corner with the bolded black text beneath it, matter can gravitationally repel matter. This is the most important thing we want to discuss today because that's where we allow the repulsive antigravity to happen. And then matter can, of course, attract matter. Matter can repel antimatter. Matter can attract antimatter. So there are all possibilities. It's just a statistic. You do the statistics, then you get everything, and you pick what you want. Next page, please. There are actually observational evidence for repulsive antigravity if you look carefully in the universe. because the universe is observed to be expanding at an accelerated rate. If you look at the Milky Way, you will see that the Milky Way is ejecting and accelerating two symmetrical bipolar outflows from the galactic disk center. Many galaxies are observed to eject bipolar outflowing gas accelerating away from the galactic disk, and also black holes and the protostars are found to eject relativistic bipolar astronomical jets. All these effects are only possible with the astronomical anti-gravity because nothing can do that. Electric or magnetic force, impossible because, I mean, they are charge neutral. How can they do long distance acceleration? That's impossible. Next page, please. There are some research papers about the outflows of the Milky Way. This is some recent findings. I think it's early 20,000, I forgot. But the Milky Way is the middle, like if you look at the left side picture, the Milky Way is a flat disk. And then the top and bottom purple blobs are outflows that is accelerating, going to like leaving the Milky Way at accelerating rates. If you use our theory, you will see that at the center of the Milky Way, there are some very active galactic center. There are black holes. There are different sorts of like violent astronomical events, but they will create particles with like positive and negative gravitational charges. You know, it's everything is symmetric. Nothing can be always one-sided. So for those anti-gravitational particles, they will be repelled by the Milky Way's disk, because Milky Way is a disk galaxy. So if you put a big plane that's all repulsive, you'll see that all the charges carrying, not charges, all the particles carrying anti-gravitational charges will have to be repelled. Those created that have positive gravitational charge, they will be pulled back to the galactic center. So that's why you see two bipolar outflows. Next page, please. And there's another Centaurus galaxy not far away, or the millions of light years away. If you look at the galaxy, it's also a disk galaxy. It has a disk-shaped galaxy, but perpendicular to the disk, it has two outflows, one going to the top left, one going to the bottom right. So that's also the evidence of repulsive anti-gravity. How can you do electric force? That's impossible. I mean, electric chargers are short-range action. So if they come close, they will just get charge neutral. But for gravity, it's not possible. They are very weak. So
And
next page.
Hong, sorry, I don't. Let me apologize for interrupting. So
Oh,
we have about 15 minutes left, and if you are going to run over, I think that we can accommodate that. I'm just
okay.
wondering. Yeah,
Okay, let's
I
go
just
forward.
okay.
Yeah, I'll move fast. Next page, please. And also, this the stars, protostars can do this the same thing, bipolar, anti-gravitational, repulsive forces. Next page, please. And there are some new images coming. There are bipolar to anti-gravity. Next page, please. This is more images, but that's repetitive. Next page, please. The recent one is the repulsive antigravity done at the laboratory. This is CERN's Alpha-g experiment. It measures the free fall of antihydrogen atoms. Some of the atoms will flow up, some of them will flow down. Because antigravity, the antihydrogen atoms are antimatters, so they can be easily find about their locations where they are floating. That's possible to measure easily in physics. Next page, please. If you look at the locations of the annihilations of the anti-hydrogen atoms, you will see that most of them are not standard. They could fly down as you look at the red colors, or they could float up if you look at the blue patterns, but they don't stay at the zero most of the time. So they are either going up or going down. That means they could carry positive gravitational charge or negative gravitational charge. Next page, please. This is the video from Alpha-g. The average gravity was measured to be 0.75 of normal gravity. And CERN says that, okay, this is the same sign of gravity. It must be equal to 1.00 g. That is, all the anti-hydrogen atoms should be the same gravitational charge or same gravity. Next page, please. This is another graph. That's the simulation of the gravity based on the measured data. Also, you can see very obvious indicated by the ovals. You will see that they are below the red curve, the top red curve. Obviously, anti-hydrogen atoms have lower average gravity than normal hydrogen atoms. So if you believe in grand unified physics, you will say that based on this 0.75 gravity, it should be 87.5% gravity plus 12.5 anti-gravity. This is the right explanation for the experimental result. Next page, please. There is another experimental evidence for charge-based gravity. That is the Newtonian gravitational induced quantum interference with free neutrons. And if you look at the equation, the phase change of the neutrons is proportional to the gravitational constant. Next page, please. The theoretical phase variation is found to be 0.8 different from experiments. It's always the same, no matter what kind of energy is used and what device was used to measure. And the accuracy of the experiment is well below the 0.8% difference. That means it must be something true. With the grand unified physics, this 0.8% difference is easily explained. Next page, please. There's some evidence in the gravitational constant measurements. So the big G constant measured by different groups are always different. Even for some groups that have very small uncertainties, they are different beyond their measurement accuracy. That means G is different, but nobody pays attention to worry about what atoms they are used to take the gravitational measurement. Next page, please. This is a very sad story about the free fall measurement. Dr. Saas performed the free fall X measurement inside the ZAM vacuum drop tower. That's a 110-meter free fall. The video shows that some atoms like lithium, lead, and carbon free fall slower than other regular aluminum, iron, other atoms. So Dr. Saas proposed the charge-based gravity. This was done in 2004, before I started my theory. But Dr. Saas was prohibited from repeating the experiment, and he filed a lawsuit to request the repetition of the experiment, but was unable to do so. He left us without finishing this experiment. Next, please. I did my own measurements with a pendulum, simple pendulum with stainless steel shells. If I fill the pendulum with wax, the pendulum swings slower. That means wax has slower free fall rate than the stainless steel. Wax is made of carbon and hydrogen, so all of them have a smaller acceleration rates compared to steel. Because the requirements for such experiment is very strict. The difference is on the order of 0.04%. So my measurement has a accuracy about 0.01 to 0.02%. So I have some confidence, but not always, because such experiment has so many possible ways to fail. Like even I use the laser beams and the electric circuit to improve the accuracy. It's just too hard. Next page, please. So in my experimental observations, I would conclude that gravity is a conservative force. It can be described by gravitational charges, and they are carried by elementary particles. When elementary particles combine to form atoms, their initial mass will vary by various binding energies. And when elementary particles combine to form atoms, the strength of gravity doesn't change. This means that different atoms will fall at different acceleration rates. Next page, please. So grand unified physics rejects the current ideas. All hydrogen atoms must carry the same gravitational acceleration. All hydrogen atoms must carry attractive gravity. All hydrogen or antihydrogen atoms must have the same rate of gravitational accelerations. There are only one type of hydrogen atoms and one type of antihydrogen atoms. Gravity is not a force, but not a space-time warped by mass. I don't like the idea. Gravity is proportional mass. It only proportional to the charge. Next page, please. So there must be some common mistakes about the hydrogen gravity or antigravity. Next page, please. So I have shown that the four types of worlds. Now I show that hydrogen atoms can be also having four types. Some hydrogen atoms have positive gravitational charges, and some hydrogen atoms have negative hydrogen atoms, gravitational charges. Next page, please. So this gives us the chance to explore the possibility of antigravitational antihydrogen atoms. Where do they come from? Where does the negative gravitational charge come from? Well, it could come from Big Bang when gravitational charges are created positively and negatively equally. And there are also pair production process that can create positive and negative gravitational charges at the same time, like the CERN Large Hadron Collider and cosmic rays, which has energy up to 10 to the 21st electron volt, spallation on nuclear reactions. And there are energetic celestial events such as supernova explosions, black hole relativistic jets, and galactic center outflows. Next page, please. So because gravity is such a weak force, it is so weaker than the electric force. The electric force or the chemical bond is strong enough to prevent anti-gravity because gravity is basically negligible in the environment of electric force. So celestial bodies can be formed containing mostly positive gravitational charges, but rare anti-gravitational charges. Or celestial bodies can be formed containing mostly negative gravitational charges with rare positive gravitational charges. So early celestial bodies mostly contain like hydrogen atoms, but later they are fused into heavier atoms. If once they are fused into heavier atoms, there's no anti-gravity anymore because mostly they carry the same sign of gravitational charges. Next page, please. So where do we find the anti-gravitational hydrogen atoms on Earth? Well, it must be very rare. That's for obvious reasons. Each, if we look at any atoms, each atom has some positive protons and negative electrons, and then some neutrons which are charge neutral. There are pairs like neutrons can be considered as the positive, proton and electron pairs. So the total gravitational charge is approximately proportional to the number of proton plus electron and then the neutrons. But there is interesting facts about the hydrogen and liquid deuterium. Deuterium. This fact is like liquid hydrogen is lighter than expected than the liquid deuterium because if you think liquid deuterium is two times the density of the liquid hydrogen, you will find that it's not a fact. It's a heavier, deuterium is heavier than liquid hydrogen. That means liquid hydrogen might contain repulsive anti-gravitational atoms. Next page, please. So how much, next page, please go to the next page. Where do we find the anti-gravitational hydrogen atoms? There are some remnant Big Bang anti-gravitational hydrogen atoms. Cosmic rays can blast the interstellar dust. Cosmic ray can blast the Earth and create anti-gravitational hydrogen atoms. Radioactive atoms can release rare anti-gravitational neutrons, protons, and electrons. So they're everywhere possible. Next page, please. But the natural abundance of anti-gravitational hydrogen is unknown. It could be somewhere around a few percent or maybe 0.1 ppm. Next page, please. If you look at the cosmic ray data, antiprotons are on the order of 100 ppm. So you think about the symmetry, half of it could be antigravitational hydrogen atoms. So that's about 50 ppm. And if you think about the abundance of gold, it's on the order of 0.001 ppm. So there are even higher chance of finding anti-gravitational hydrogen atoms than gravitational hydrogen atoms, regular atoms. Next page, please. So now we know that there exist anti-gravitational hydrogen atoms, but how do we do it? We will see that antigravitational hydrogen atoms are very rare. If they exist, they must be one normal hydrogen atom combined with one rare anti-gravitational hydrogen atom. So this thing must be weightless. It has zero weight. If we liquefy the hydrogen molecules, these anti-gravitational atoms will bring the molecule up. Next page, please. So I filed the patent just for fun to explain this way, the gravitational way of extraction or concentration of anti-gravity of hydrogen atoms. Next page, please. So this is a picture of a container maintained at extremely low temperature because any hydrogen atoms containing anti-gravitational charges will float up. So over time, these atoms will float up to the top of the liquid, and you can extract the enriched anti-gravitational hydrogen atoms. Next page, please. But we know that these anti-gravitational atoms are combined with regular hydrogen atoms. We have to create the pure anti-gravitational hydrogen molecules. This is not hard. You can either break the two atoms apart and recombine them. By chance, some of them will become purely anti-gravitational hydrogen atoms. You can do it either chemically or physically. Next page, please. So once we have the liquid anti-gravitational molecules, it's so easy to use it for space traveling because they provide anti-gravity all the way. If we have 1 ton of these antigravitational molecules, you don't even need any jet fuel to go beyond the solar system. So this is so easy to use. And also you can build a space elevator because you can put hydrogen antigravitational, liquid hydrogen molecules and segmentally, and you can just raise a very long elevator without stressing the materials containing these antihydrogen molecules. Oh, sorry, antigravitational molecules. I'm sorry about the time, and my computer was having issues, so I I forgot how to control the time. But thank you for the great opportunity. Next page, please. So many thanks to Tim and the APEC conference organizers. It really is a pleasure and honor the opportunity to exchange theoretical and experimental ideas. You are motivated enthusiasts aiming high, try to extend advanced humanity beyond our solar system. Thanks so much. That's it.
Awesome. Well, Hong, thank you. Thank you so much. Let me take that down. We are a little bit over, but that happens, right? I mean, this is the magic of trying to do like a live conference event. I want to bring everybody who is backstage on here, and let's put our hands together and give Dr. Hongdu an enormous applause. Thank you, sir. That was a wonderful presentation. You had so much to cover and so much more, and especially in terms of like when you're looking at the universe and the composition of the universe and the behavior of galaxies and things like that. I'd never looked at that before. And so that was all, for me at least, that was all brand new. I think the audience is going to get a lot out of this.
Thank you.
Absolutely. Well, so we don't have time for Q&A, but I believe Mr. Jarod Yates is up next. So what I'm going to do is I'm trying to keep things as close to on track as possible. I'm going to take everybody out, and Jarod, you have a presentation that you've uploaded, right?
No, I was going to share screen. There you go.
There. Oh, okay. Oh, it's that. Okay, perfect. Okay. Well, so without any further ado, I guess I should probably set this up briefly for folks. This is a project that you, myself, and Mark Sokol have been deeply involved with. Mark was the initial person to obtain and do analysis on the Earth's parts sample. And then you've done visual analysis. You've also done a ton of homework on this thing. And so that's what comes out here. So,
yes, sir.
Okay, well, take it away, sir, and thank you so much.
All right. Buckle up, folks. I'm going to have to go fast here. So this is Arts Part 2. If you haven't caught the first one, I strongly recommend you go back and watch our first presentation of this from July. That was about a week after we got the sample. Since then, we've had some more time to do some more interesting tests on it. Over here, you can see an example of the scanning electron microscopy. Over here, the energy dispersive spectroscopy, where you can see the elements. We did this testing at the beginning of August and have been going through the results of this and trying to come up with some analyses. So just to give you a quick rundown on how this is going to go, I'm going to go over a bunch of pictures of our SEM and EDS pictures. One of the really interesting things that we found was there's these little microspheres that look like zinc encased lead, and a couple of them are ruptured, which are indicative of some interesting things. We're going to go over the Oak Ridge National Lab Aero report that came out 2 days after we came out with our report. Within their report, they have some interesting stuff about the bismuth nanospheres and the bismuth layer and how it's not continuous but has discontinuities in it. We're going to go over some of the fascinating symmetries we found in the placement, seemingly purposeful placement of these zinc lead microspheres. We're going to go over the testing that we're currently performing on it, as well as what we are hoping to perform here soon. And then I'm going to go over some speculation as remaining hypotheses for how this material that seems to have been made from elements on Earth could still, in fact, be very non-prosaic, could have originated from someone other than military testing sometime in the 20th century. All right, starting out, SEM and EDS. First off, SEM, scanning electron microscopes. That's for taking pictures really close up. EDS, that's for telling what's inside it for the elements. Here's an example from Jacques Vallée and Gary Nolan back from their paper they wrote in 2022 for NASA. Just to give you an idea on the range of sizes that we're looking at and the density of material that you're looking at. So yeah, we're around the, sub 1 micron range. Also, I'm going to upload at the end of all this, you'll have links to this presentation as well as all of the links that I'm using within the presentation. There's an excellent video from the Soul Foundation that Gary Nolan did recently where he goes over some of their tests on some UFO material. Highly, highly recommend. So for reference, this is the sample we are dealing with. It's very small. Here it is sitting on a penny. Don't worry, the penny isn't contaminating it. Here's the date of the penny, so you can see just how big we're dealing with. It's about 4 millimeters long by about 2.5 millimeters wide by about 0.4-ish millimeters thick. Here is an edge on view for reference. Here's the glue. Oh, sorry. One last thing on this one. So this thing right here, this is epoxy or glue from the previous owner where they were performing tests on it. We have not removed that because we don't want to damage the sample in any way. So we're just leaving it on for now. With that glue, with the whole thing, we weighed it out and it was at about 7 milligrams, give or take 0.5 milligram. So for reference, here's that glue spot here at the back. We're looking at the edge on skinny tip here. You can see some of that layering that's going on the side of this sample. For reference, as we're looking at these SEM pictures, this KV down here, this is like the brightness that you're dealing with. So we're dealing somewhere between 5 kV to 30 kV for our brightness in all of these pictures. So this is about mid brightness here. And over on the side, you'll see size scale in microns for most of this stuff. Here is the elemental composition of that image I just showed you. Don't worry about this for now because we're gonna have a lot better ones here coming up. But in that, we have carbon over here in red. You can see that is actually sitting on the testing surface here, not the testing sample. So there's a little bit of pollutant going on in this image. We have other images coming up that are much less polluted. You can see that same surface is a little oxidized. But the important thing to note here is that the sample does seem to have carbon on it. It does seem to have some oxidation on it. And most importantly, though, we see that magnesium there. Ooh, pretty magnesium. Here, now we got the thing flipped over. You can see the glue at the back. We're at about mid brightness still at about 15 kV. We're not very zoomed in. We're going to zoom in, though, on this really interesting spot here. There's a couple interesting spots on the tip here, right? But we're going to zoom in right here. See, it's about 0.4 millimeters, 400 microns thick at the skinniest edge there. So as we're zoomed in here, this area really caught my attention. You can see some of the layering going on here. You can see the stridation of the columnar breaking here. But this area here, this really caught my attention. So these things, they look kind of like these little nano cylinders, and it looks like there's some connective something going on between them. I'm going to present a little bit later in this talk as to what I think is going on with these. First, though, let's do some elemental detection of this area. We have carbon, oxygen, magnesium, and then we got this zinc that's dispersed all over the place. Now, for reference, you can see how the zinc is like up here in the air. That's because this is not bright enough, so it's getting a little bit of extra noise going on up here. But down here, I'm not so certain that this is actually noise. I think we're actually getting some good zinc peeking through here. And I've overlaid that zinc over here so you can kind of see what's going on. So for reference, here's those little cylinders that have some connecting lines going between them over here. This green is the oxidation that is going on the surface. And you can kind of see how we got some lines of zinc, some semi-regular patterns of the zinc. And the reason why I say that's important, this picture down here is from Gary Nolan's YouTube video that I just referenced. And in their samples, he was noting how some of these atoms in their materials seem to have very specific atomic placements. So it's important to keep that in mind, that we have potentially atomic placements of certain elements going on in this sample as well. Here is the rough spectra from that one. Now, important to keep in mind is when you're down here at the 1 to sub 1 keV brightness, anything where your count is below a 1 is potentially noise. There might be something there, but it might also be a big old nothing burger. But right on the edge of that nothing burger, we were detecting some aluminum and niobium. Now, this is the only time that we detected that, so it's likely noise. But at this point, with so many unknowns about this, it's important to keep in mind every single little thing that you are able to observe about this. The important part is we have magnesium and zinc, like we've been saying, and a fair bit of oxidation and carbonization on the edge here. All right, this is the magnesium side, the shiny side, and we can see the edge of it, how it has broken. We are only at 5 keV, so our brightness is turned way down. And right here, this is that delamination layer here, right? So right here, it's like the bismuth magnesium zinc transition zone where it delaminated, where it sheared apart. Good takeaway from this picture is you can see the columnar breaking that we had here. In the next image, I'm going to show you how there's a specific shape or pattern or angular structure to these breakings. Make that in another slide or two. First, though, I want to show something on the bismuth side, on the dark side. We have a couple of interesting geometric structures on here. These bright spots, those are all the zinc line lead. We're going to get to that in a little bit. But first, let's look at these geometric structures that look like they're showing up here. Zoomed way in and enhancing the contrast on those, it looks like we have some very specific 90-degree angle going on within some of these circular patterns going on there. But this one really caught my eye. You can see one of those center cylindrical structures, and you see 3 legs coming off of it. It seems to me like that's weird. I can't say for sure one way or another whether there's something important about that, but it really caught my eye because it seems like there's a semi-regular angle between these 3 legs of this thing. I can't even begin to imagine what's going on with that, though. Just something worth looking into. We're going to be uploading all of these pictures. I'm going to share the Google link drive to every single picture we've taken. So I thoroughly recommend that everyone take a look for themselves and do your own analysis on this. Take your own time and do your own research and see what you can come up with from the images that we are sharing, because these are the most images that you'll find on the internet about ARTS parts to date. We have hundreds and hundreds of high quality images of this that we are sharing to everybody for free because we want to get as many eyes on this as possible. All right. Here is, again, the bismuth side. There was one thing about this edge that I thought was quite interesting. Right here, you can see these little divots here on the side in one of the shearing layers. And I thought that was quite interesting. We'll come back in towards the end of the talk, and I'll be showing you some other spots on the surface here, which seem to match that same pattern that you see there. Here we are up a little bit higher, still on the bismuth side here, and we got the brightness turned all the way up to max at 30 kV. And now you can really see this edge structure here really well. We're focused on this line right here. And you got some of these sharp spikes coming off, but most importantly, you can really start seeing the angles of the shearing that occurred when this thing was peeled off of whatever it was peeled off of. Yeah, I think there is much to be gleaned from observing the edges of this thing and how they break. Now, over here, we're focused on the actual surface. Linda Moulton Howe had one of her scientist friends. They put this thing in a beaker of deionized water and left it there for 40 days. And there was a stream of bubbles, of hydrogen bubbles coming up off of a couple different spots on the sample. And they noticed that the spots where the hydrogen gas was coming off of, it seemed like there was cavitation occurring on the surface. Well, we can see a couple of spots, and in the next couple of slides, we'll note a lot more obvious where some of those spots are. But once again, indicating that this thing seems to react to water and produces it produces some redox reaction. Now, way towards the end of the talk, we may have noted some sodium on it, but once again, it was down at the threshold, so take with a grain of salt, so to speak. it seems more like it's the zinc and magnesium that's getting converted into the hydrogen. Here's another zoomed in example of one of those cavitation zones. So on this one, right here, this is an obvious cavitation zone, as we can see from the oxidization that has occurred in that area. So for this image, you can see the green spots is your oxygen, the blue spots, the darker blue spots is your magnesium, and then these turquoise spots, that's all your zinc. Splitting it into its constituent colors here, you can see how you have oxidation very strongly in that spot there. You can see we have a lack of magnesium in that spot, and we have a lack of zinc in that spot. Also note how the zinc is very thinly distributed. If you've looked into the sample at all in the past, you'll note that Lindemoulton Howe and company noted that there was something like 97% magnesium, like 2 or 3% zinc, right? So there's a lot less zinc than magnesium in this sample. Here is our counts that we got on it. Now, another thing when you're looking at these, when you look up higher, when you're getting the brightness up higher, this is much more reliable area up here. When you get counts up here, you're much more confident down at these lower levels than you are down here. Once again, carbon, oxygen, magnesium, maybe some zinc. No, yeah, definitely some zinc. All right, here's a picture that I have skewed for good purposes here from the first talk. There was something on the bismuth side of the sample that really caught our attention. I think that's on the bismuth side. Maybe it's on the magnesium side. No, it's on the bismuth side. Anyways, this little 90-degree fiber thing here. We were really curious what's going on with this. We're like, is it a hair? Is it a piece of polyester? Is it purposeful and part of the sample? What's going on with that? Well, we did make sure that we got that on the SEM. And as you'll note, we're real dim at 5 kV. But all of these little zinc lead seed microsphere things, those fluoresce. Anything that's metal is going to fluoresce and be really bright. And the fact that this thing doesn't fluoresce at all suggests that it's probably not made of metal. Here it is under the metallurgical microscope. This is at like real colors, so you can get a closer idea of what we're looking at. Here is with some added filters to the metallurgical microscope, and you can see it looks like it has some core material going on in there. Well, I found this picture of white or gray hair under a similar microscope, and based upon these little bumps that you see here on the edges, I'm wondering if some old scientist that tested this might have gotten one of their whiskers on there. Coming up in November, I'm going to be visiting the lab, and we're going to try to hopefully do some live streaming of the sample under the metallurgical microscope. So maybe I'll just pluck one of the gray whisker hairs that studying this sample has given me, and I'll put that on the scope. We'll do some comparison. Here's one last image of that weird fiber going on under there. Now, there could be, you know, cooler explanations, like it could be a fiber optic cable or something, but I strongly doubt that. It's probably more likely a contaminant, I would suspect. All right, we're way zoomed in. We're fairly bright at 20 kV. We're way zoomed in at 1000x here. All of these bright spots, those are all the little zinc lead microspheres that I'm talking about. And you can see that some of them have ruptured. Now, that's interesting. That's worth pointing out, and that's something that I'm surprised no one else has observed yet. We're going to get there in just a second as to why ruptured spheres are cool. So on this particular image, you can see we have some weird morphologies going on. There's like this big deal going on over here. We're at 200 microns right here, right? So this thing's like 75 to 100 microns long or something like that, compared to all of these, you know, 15 to 30 micron seeds or microspheres. Here, I'm comparing that with our EDS. So for reference, that seed thing that you saw is right here. I'm going to do a GIF that overlays the two here in just a second. But first, I want to go through what you're seeing on this image. So the yellow, that's the lead. The Arrow report, the Oak Ridge National Lab report, said this thing has about similar parts lead to bismuth, and stopped there and said, so it must be slag. I strongly contest that you should just stop questioning this because you detected lead in it. And here's why. We can see these microspheres, right? So you see a very thin layer of this turquoise zinc here on these guys, very thin layers of turquoise zinc, and then you see the yellow lead coming out and peeking out of the ends there. And for this particular spot where it ruptured, you can see we got like this Mount Vesuvius kind of thing going on of the lead peeking out all over the place. And wherever that happened, we also happen to have oxidation, right? So it seems to me, gonna throw out a hypothesis here, it seems to me that because some of these are ruptured and not all of them are ruptured, that something happened to cause just some of them to rupture, right? So it might be, once again, hypothesis, it might be that they're acting kind of like capacitors, right? And they're getting overcharged. And for the ones that get overcharged, they rupture. It may not necessarily be capacitors. I'm using that as an analogy. It also would explain why you see ones that are close to each other as being ruptured and ones farther away just being overdriven and not yet ruptured. And ones even farther away, not yet ruptured at all. Because when you have a catastrophic failure like that in a circuit board, yeah, you'll have capacitors that are all tied together, all blow up, and the ones farther away don't blow up. But the ones closer to it might be stressed out and be much closer to failure than the ones even farther away than that. Just something to consider. These guys here, the red, that's carbonization. Have no clue what's going on with why we're seeing the carbon in it. I would love to have some other eyes look at this, say why that is. It kind of looks, if I go back, it kind of looks like those might be skin cells, maybe. But the problem with that is that we're at 20 kV brightness. So if this was skin cells, like I don't know. I don't know. That is not my area of expertise there. It's not. So here's a GIF that I made where it's going to go back and forth between the two and it's going to overlay them. So one interesting thing here is this curve. I'll go back up. This curve here. You can see once again, we got that zinc with the lead poking out, but we have a structure, right? We have like almost half circle, half ring going on there. Anywhere where you see a circle or a line or a right angle, those are spots to pay closer attention to because that suggests potentially purposeful manufacturing. And here it's a little easier to see the ruptured spots as well when we go back and forth. All right, here I'm pointing out some more of those ruptured spots so you can see it a little bit closer. All right, now it wouldn't be fair of me unless I did put this side by side with what slag looks like. I mean, Arrow is saying it's slag. Let's see how right they are. So I went online, and by no means am I a metallurgist, so take it with a grain of salt. But what I found here was this one particular image from this one paper whose link is in the slideshow if you go to the link. That looked a lot like this guy, also in size, right? This is about 100 microns, so this thing's about 75 microns long. Well, that's about the same length of that. This kind of looks similar to this. Maybe it is crushed slag. Except slag has iron in it. Now, right here, this is from the Arrow report. They did say that they found iron, if you can believe the Arrow report. But the amount of iron that they found was very negligible. Over here, as we see in the EDS report for this particular bit of slag, you can see that they had a fair bit of iron. And actually, if you go to the paper, you'll see that it was like 15% iron compared to this that is in the like sub 1% or sub 1/10 of 1%. So something to consider. The fact that we never found any iron in ours suggests that, you know, there's less than 1% of iron, kind of like what maybe they're saying. Compared to slag, you would see much higher amounts of iron. So really important to consider when you're talking about the slag angle, where the heck is the iron? All right, so this same image that we were just looking at, I've split it into the colors here so you can see what's going on. Yeah, we got carbonization everywhere. We've got oxidation. There is a serious shadow or lack of oxidation in these two carbonized areas, right? The long guy and the potential skin cell or something. There's also a lack of magnesium in that area, which is weird because we have somewhat of a lack of zinc, but not nearly as much as the lack of oxygen and magnesium in these two areas. Going back to those little arranged spots on the edge that I talked about towards the beginning, Here in the magnesium, you can see we have a similar arrangement here of those holes there. It's kind of weird. We're finding similar morphologies in completely different places that seem to suggest that some kind of potentially purposeful arrangement or purposeful manufacturing. Also kind of weird is you see some straight lines going on. Like I just said, pay attention when you see straight lines. Over here, we're looking at the zinc a little closer. There's a couple of interesting spots on this zinc. One spot, you can kind of see like a big like half ring going on here. I'm going to speculate again, throw out another hypothesis again. When I look at this and I think of it through the lens of what if this is advanced technology, which everything about this out of place artifact is suggesting it might be. I see microcircuitry. I see micro traces going on here. Take that with a big old grain of salt, right? It might not be, but when I look at this as an electrical engineer, that's what I'm seeing is microcircuitry or micro traces. It's almost like they're using the zinc as kind of like PCB traces of some kind. Just what I'm seeing. You also have some of these long, straight, curved areas. Something to consider. Here I'm going to do a GIF going back and forth between the two. You can see how the zinc kind of follows this straight line here. Yeah, once again, thoroughly recommend everybody else. You should go through this for yourself, see what you find. This is also a cool little circle thing here that's both on the zinc and magnesium. You can see that that half moon thing that I was talking about shows up a lot more in the zinc than it does on the magnesium. Here's looking a little closer at the EDS of that, carbon, oxygen, zinc, magnesium, zinc. Now over here, there's a little spike on the edge here that this image isn't showing, but that is the lead right there that just wasn't being monitored for this particular image, but that's what that spike is. All right, moving on to the bismuth side. Again, this is that same image from before where the brightness is turned way up and you can see the spiky side there. Let's look at the distribution of elements going on there. So because this is the bismuth side, the bismuth delaminated from the magnesium zinc. So magnesium, we got darker blue. Zinc, we got the lighter turquoise blue going on there. You can see the presence of both of them over there. You can see the bismuth all over this, but it seems like you can see all of that zinc poking out from underneath the bismuth, right? Because it's a really thin layer of bismuth and we're turned maximum brightness, maximum penetration depth of the light at 30 kV. You can see we got some oxidation going on. And specifically, there's a couple of spots here where you get a little bit of lead action going on. A little harder to see because it's so bright, but yeah, it's all there. Also, and this is going to come in important in a little bit here, these red spots of carbonization, you see those on the edge, specifically on the points. So something caused this thing to have carbon deposits occur at sharp edges, almost like it maybe was in a high voltage environment of some kind, potentially. Just throwing that out there. Splitting that same image up into its constituent parts, we can see, yeah, it's got oxidation layer all over the place. Yeah, it's got a lot of magnesium. The zinc, again, we're seeing that distribution, how the zinc seems to have very sparsely populated when compared against the magnesium. Same kind of goes for bismuth. Bismuth is kind of in between the zinc and the magnesium for how prevalent it is. And because it's kind of dark, it's not showing up on the edge as much. The important part, though, is the lead, especially the lead-zinc comparison, which in this GIF, you can kind of see it. It's moving a little fast, I know. But when I look at this, I see a relationship between the two. Now, yes, the two colors do shift from each other. The lines don't overlap perfectly. But when I look at this, I see a correlation, a semi-mid correlation between those two elements, like we saw previously in the zinc-lined lead microspheres. Yeah. Looking at that under the spectra here, once again, we got the noise floor down here, but we do have the zinc, the magnesium, We can see that we do have bismuth and lead. We're still kind of low. We got our zinc in the more trustworthy area of brightness up here. And then we got the lead bismuth up here, even more trustworthy. Let's zoom in on that. You can see the lead up here is about a little less than half the amount of bismuth. Down here, more in the noise floor, it looks like there's a lot more lead in a ratio of bismuth than up here. But either way, we can see that, yes, it has lead, not nearly in the one-to-one parts that the error report suggests from what we're observing, and less lead than zinc when you really start looking at it under the brightness. Here is the bismuth side. Again, we're going to look at the spectra of this part. This is a separate area of the bismuth side. We're trying to look for how uniform all these elements are distributed throughout the thing. You can see the carbonization is much less bright here, right? We have some brighter areas here along with the oxidation, but it is not carbonized everywhere like it is with the oxidation. Over here, once again, interesting spots is the zinc, bismuth, and lead, and how those all have interesting overlaps when you overlap them all together. I think I got a GIF coming up here of that. Once again, we've got our bismuth lead way up here in the trustworthy area, the zinc. So this image is looking really similar to the previous one that we just saw, showing that it's got fairly uniform distribution of these elements. Zoomed in again, we can see, yes, fairly uniform. We got still, again, the same amount of like a third lead to bismuth, more zinc than the lead. And down here in the noise floor, that, yeah, it looks like there's a lot of lead, but you got to go up here to really trust it for sure. All right, now this part is kind of weird. When you're down here in the noise floor, like I said, you can't always trust it, but you still got to consider it at least. In the noise floor over here for one of these, this is an image that Mark took while he was at the lab. He took like his cell phone over there and recorded the whole thing. And this didn't make it into the report that they gave us, but I thought that was interesting enough to still share. So we have sodium, Na, sodium, right next to the magnesium on the periodic table. And we got bismuth and lead right next to each other in the periodic table. The reason why this is important that we saw sodium, potentially important, is because if this thing was in a really high energy environment, like a gamma radiative environment or a reactor, nuclear reactor type environment, any high energy radioactive environment, you might start seeing some transmutation of elements where heavier elements are being transmuted into lighter elements. So I'm just throwing this idea out there that the magnesium being transmuted into a few artifacts of sodium, or some of the presence of lead that we're seeing, maybe that could have been bismuth getting transmuted into lead. I'm just throwing that out there as an idea. Take it with a grain of salt. Here is another image that I took of that. So in this case, pink is your sodium rather than bismuth like it was in previous images. For this particular image, this here is your sodium. And you can kind of see in this super blurry zoomed in cell phone shot that, yeah, it looks like there might have been some detection of that. Yeah. Here's zoomed in even further and even blurrier. Sorry, folks, this is the best I could do with the materials we got for recording. All right, this is from the error report. So in this image, we have our layered structure here. Now, these layerings, you can see our scale here is 200 microns, right? So the bismuth layers that are separating all those, according to this image that they have, you can see that up here, this really bright line, that's your bismuth. And then throughout the rest of this is all your magnesium. And then inside of that magnesium, you can see we have layers of zinc that are not necessarily evenly distributed, right? We have a really bright layer of zinc and then a dispersed layer of zinc, really bright layer of zinc, dispersed layer, and then a really dim layer of zinc. Also important is this bright spot that you see for the zinc and for the lead. Those are the zinc-lined lead microspheres that have ruptured, which is why you're seeing it show up so brightly in those areas. Over here, they claimed in the Arrow report that these vertical lines might have been some carbon-based binding agent. I don't know enough whether or not to say for sure that that's accurate. Because we saw some carbonization on the outer edges of the thing, it makes me wonder if these microfractures might have allowed for additional carbonization to occur rather than saying that that is a binding agent. Maybe it is a pollutant like we saw on the edges. Not sure. Here is another image from the Arrow report. This is really zoomed in, right? 5 microns wide. So up here, if you've looked at like cloud chambers before and you've seen how like radioactive emissions seem to go through materials, to me, this looks kind of like it might potentially be some kind of radiation damage, which if it was in a high energy environment, like we're going to see here in a few slides, it very well could have been, then that would make sense. This is supporting the hypothesis that this thing at one point was sitting in a very high energy radioactive environment. So that's the first part of this image. Second part of this image, all these vertical lines you see at the bottom, Arrow is saying that those are artifacts from the focused ion beam, which may very well be the case. I'll give them potential credit for that. It's called curtaining, focused ion beam curtaining. However, I like entertaining ideas. So the idea that it might not necessarily be curtaining, keep that in mind. So here's some images of what curtaining looks like. And yeah, I can see the relationship between that and this, but there's enough variation between this and this that it just makes me wonder. It makes me keep open different possibilities that it might be something else, especially when we look at these nanowire structures. So like these little cylinders I showed you at the beginning, wow, those sure look like these guys to me, or at least, they look more like that than the curtaining, that we're seeing here. Also, when we look at these vertical nanowire structures that have been built in other experiments, to me, I see more of a relationship there. But, I'm not going to hang my hat on that. I'm just saying, All right, another part of the Arrow report. So this part was really interesting to me. Once again, zoomed way in at 5 microns. This is the reason why Arrow said that they didn't think that it was existing as a terahertz waveguide. So if you had a waveguide that was as discontinuous as this, it would be a really crummy waveguide, right? You'd have all these impedances and resistances that are occurring as the signal can't like propagate normally throughout the thing. And yeah, I'll totally give them credit for that. If I was building a waveguide, if I had to use a waveguide and it had this kind of structure to it, I'd just be shaking my head. It would be so unpleasant to try to use that as a waveguide. Here's a more zoomed in area of here. Now, the sizes of these things, you can see these little nanospheres of bismuth that are scattered throughout the bismuth layer, that are comprising the bismuth layer. That's really interesting. That's really telling of a couple of things. Maybe how it was built, maybe what it was being used for. Here is a random paper I'm going to throw in there where we're talking about bismuth nanoparticles combined with lead being used to make quasi-crystal matrices. A little bit. I'm going to show you why I think quasi-crystals might be prevalent in the sample. And there's a link to that within the thing too. First, though, I'm going to go down a road that no one else to date seems to have done. So supposedly this sample came from the Roswell crash. That is the multiple angles that we have gone down for tracing the history of this sample. Everything about it, seems to suggest that it does come from the Roswell stuff. And yet no one seems to be addressing that we have purported documents of the Roswell crash that give us additional insights to this. Why aren't we at least entertaining the idea that if this thing did come from the Roswell crash, let's look at documents about the Roswell crash that can support or negate the idea that this thing did indeed come from it. So here are some purported documents from the Roswell crash. Roswell crashes were July 3rd to 5th. So just 2 weeks later, General Twining, purportedly, this document, its veracity is still in question because it's from the Majestic documents, but it's one of the more reliable Majestic documents than some of the other ones. So I'm going to treat it like it's real, like I like to do with the Majestic documents. Anyways, in here, they're talking about how inside the wedge-shaped craft that there was a toroid, a donut-shaped tube, that went the diameter of the craft, 35 feet. It was made of a plastic material, and it looked like it was filled with deuterium, heavy water, suggesting that it was some kind of neutronic or atomic engine. Here's another memo from about a week earlier than that, also from General Twining, saying that it was a neutronic engine, that there was heavy water and deuterium present in it. Over here, we can see that they found supposedly, they found a whole bunch of uranium. UF6 is uranium fluoride 6, uranium-235, uranium tetrafluoride, magnesium, maybe like we're finding in the craft, and plutonium, thorium. This whole thing seemed like it was some kind of fusion or fission reactor. Oh, and just for fun, a metal similar to lead with a chocolate brown color. I think element 115 was chocolate brown color, but I don't know one way or another on that one. I just thought that was interesting, the chocolate brown association. Here's another part of that same memo that is really important. Focus on this. They said that when they looked at it under a really strong microscope, that they saw a series of fine grid-like lines intersecting groups of dots that are arranged in circular patterns. Well, guess what, folks? Blammo! We got circle here. We got these straight lines coming off that circle. We got a semi-regular arrangement, circles of these zinc lead dots coming out of this area. Over on this side, we got these straight lines of those little zinc lead dots coming from an area. Well, I started trying to draw some, I'll admit this is crummy, like paint drawing here, but I got some better stuff coming up. But I just thought it was interesting as I started drawing some of these circles on here, how it seemed to follow this natural arc of some of these circles, right? And there was a weird triangle in there too, but the most important part was these straight lines on that one. Over here, we see a bunch of these lines radiating out from this central point here. And I do apologize. These images were kind of skewed from the angle of the camera, so it's really difficult with this. I really wish I could have been there for the testing of this to really zoom in on these pictures a little more, but working with what I got here, folks. So here's five-fold symmetry. These black dots, these are five-fold symmetric quasi-crystals that I'm just overlaying on top of these to try to see how well they overlap. And I'll admit, it's not even close to a perfect one-to-one. I'd say at best we're probably sitting around the 50% correlation from what I'm able to see between these two. And full transparency, I tried overlaying some hexagonal structures over these, and I thought it might be closer to 60%, a little bit closer than these quasi-crystals. But yeah, it's really hard to say at this point until we get the Raman spectroscopy and some other methods that might be even more destructive testing to be able to know for sure at the atomic level whether or not these have quasi-crystals inside of them. Nevertheless, circles of dots arranged. I loved that. I loved that. Here is a GIF going back and forth with some other painted on lines that I was doing. Just trying to see the arrangement. Now, one other thing that I'm going to mention about these is the ratio, and this is why I think it's quasi-crystals are important. The ratio of the distances between these dots, some of those distances between these dots comes really darn close to the golden ratio. And if you see the golden ratio pop up with, vertices like these, that is a really good smoking gun that you're dealing with quasi-crystals. So something that definitely deserves a real good approach to testing this is people need to at least entertain the idea that there could be quasi-crystals present in this, which if this thing, which showed up in 1996, was, being built with quasi-crystalline arrangement of these microspheres. Lou Elizondo, in a lot of his recent interviews, because of his book just coming out, he's been saying it's like finding a fully built 747 in King Tut's tomb. If this thing was built in 1996, it's not super likely that anybody was building that. It's absolutely impossible that somebody was building quasi-crystals in 1947 or earlier. So just out of place artifact. That's all I got to say for these. The zinc lead microspheres and their arrangements, if there's one thing you can take away from all of this as to why this sample deserves people's attention, it's that. Why do we have zinc-lead microspheres that happen to rupture in weird ways, that happen to be arranged in these specific arrangements on this piece of supposed slag? Here's another image that I think I showed in my last talk. Once again, I was attempting in this one to have 5-fold symmetry. I was showing 10-fold, which is almost the same thing in quasi-crystal world, 5-fold and 10-fold symmetries. I was attempting to show how these colored, because all those zinc-lead dots, they actually show a bunch of different colors when you look at them under natural light. It seemed like that some of them had specific arrangements, and it seemed like the distances between those had some ratios, golden ratio distances between them. All right, so here's the testing that we got going on right now. We got gamma ray testing going on. If this thing was in space or in some kind of strongly energetic nuclear environment, it's possible it might still be emitting some of that gamma radiation. So we have it set up right now. It's a really long-term, like 2-month-long test where we have it set up next to a gamma detector, and we're just seeing, do we get any counts of gamma off of this thing? There was a really interesting thing that Mark and Michael did where they had this sample sitting there and they shined a flashlight on it with a straw, a plastic straw sitting next to it. And when they shined the light on it, it seemed to get attracted to the plastic straw. Now that could be tribal electric charging of the plastic straw. But the fact that it did that when they turned on the light is suggesting that there might be some photoelectric effects going on here, which if you know anything about UFOs, you know that they tend to show off a lot of light. Like the light seems to be really important. And in my previous talk, I talked about how I think Norway observed that the brightness of the craft seemed to be associated to the function of how they accelerate or decelerate. So really important test that in November, we're going to do a lot more of these tests and try to quantify if indeed there's any photoelectric effects and how strong they are. Upcoming tests. Like I said, I'm going to try to live stream the metallurgical microscopy here in November. Really important test is the Raman spectroscopy. That'll show us if potentially there's any quasi-crystals in there. We want to do some scanning tunneling microscopy, which is going to show us really high resolution if it's a conductor. And then for the parts of it that are not conductive, for the insulative parts, we're going to show some atomic force microscopy. And then the most important one, this is the one that I am just uber excited about. So supposedly, TTSA, they got their sample, and the reason why they got their sample from Linda was because they said that they wanted to be able to test it for the terahertz waveguide stuff, but they couldn't do that at any like public place. Like there was no facility equipped to do that, and that they had to go to the Army to do that. Well, there's plenty of terahertz spectroscopy out there, but there's not a lot of free electron lasers where you have really high intensity terahertz. In fact, that's like what directed energy weapons are, like the kind that the Army might be interested in using and testing. So there is a handful, though. There is a small handful, like half a dozen in the world, public institutions that have high energy free electron terahertz lasers that we are currently looking at to try to be able to test this thing to see if indeed it does levitate, as the rumor mills suggest it very well might under such conditions. Okay, finishing this off, we got some remaining hypotheses for how this sample could be built from terrestrial materials and yet still be an out-of-place artifact. We have Dan Burrish, who is a whistleblower, came out back around 2000, 2005, and he was saying that the aliens are all time traveling humans from like the deep future. So maybe aliens from 24,000 or humans from 24,000 years in the future, you know, were using terrestrial materials to build their craft and they came back in time, or they came back in time some other way and built stuff. I'm just saying, like, don't throw the baby out with the bathwater. There's a lot of different ways that this thing could still be weird. This is one of those ways, is if there was time travel of some sort involved. Another way, you have breakaway civilizations of some kind. Maybe there was some civilization that was building megalithic structures earlier than 13,000 years ago. I included this picture that obviously take it with a grain of salt, but the whole face on Mars right next to the five-sided pyramid, right next to some other interesting structures. People have tried to suggest there was a civilization on Mars at one point. Dr. Brandenburg, who's been on here a few times, has talked about his his observations that suggest there may have been some kind of nuclear event, 2 nuclear events on Mars a long, long time ago. Just something to consider, throwing all the ideas out there. You could have breakaway terrestrial civilizations that might not even be human, right? Maybe some marmots or some, dinosaurs or someone, tens of millions of years ago. Maybe they advanced really rapidly and we didn't see any evidence of it in the archaeological record because it happened so quick. Who knows? Throwing out ideas, no bad ideas. Or maybe somebody came here from somewhere else a long, long time ago, and they've been here a long, long time. They got places under the ocean or something. Another idea. We have the interdimensional. Who knows? Maybe the Marvel universe is multiverse is more real than we think, and maybe it came from Earth, just not this Earth. We also have this spiritual side that some folks like to entertain, which is maybe it comes from some immaterial realm and is able to transition into our material realm. And when it does so, whatever could be the case could be the case. Maybe it's using terrestrial materials to materialize here. Maybe it's lots of maybes on that. I'm throwing out 1,000 maybes at you, right? These are all the ideas that others who have come long before me have suggested might be the case for these craft. So things to keep in your back pocket. All right, so we've gone over the SEM and EDS. We've talked about the ruptured zinc lead microspheres, as well as their strange orientations. We've compared it against the Oak Ridge National Lab sample. And within that comparison, we've looked at how those nanospheres of bismuth might be very important. The arrangement or the distribution, discontinuity of their distribution might be really important. We've talked about what we're currently testing and what we're looking forward to testing. And I gave you some of the most wild speculation possible on how this thing might still not be as conventional as we think, right? How could this thing be an out-of-place artifact? What possible reasons could there be for this out-of-place artifact? So take it away. We got ruptured zinc lead microspheres. Some of them ruptured like they've been overdriven, and they happen to be laid out in really interesting symmetry ways here. That's the takeaway from all of this. When you're talking about arts parts to people, this is what makes it weird, is these zinc lead microspheres arranged in very specific patterns. Slag is not going to do that, folks. Here's all the links. Leave those up for a second. And when you visit this presentation, if you look in like the comments section or the notes section, I have some additional links that I couldn't fit in this single slide. That's what I got.
Jarod, that is amazing. How did you squeeze all of that into just about 1 hour? That is absolutely tremendous.
2 cans of caffeine.
Okay. Oh, you're doing the yerba mates. I'm doing Rockstar, not product placement. They're a little product placement. Yeah. So, yeah, Jarod, thank you so much. So what I got to do here is I'm going to add everybody in. Let's give Mr. Jarod Yates an enormous applause. We don't really have time for Q&A. We can come back to this later, right, during lab updates or something like that. But this is absolutely wonderful. And one of the things, I should put this out there, you and I had talked about doing kind of a podcast about this too. And part of that is because there is so much scope to what you have covered, right? And so it's hard to put all that in a single presentation, and it helps to be able to frame that in different ways for different audiences and different people. So again, thank you, man, so much. That is absolutely tremendous.
I will absolutely stick around. If y'all stick around later, we'll try to go through any additional questions that y'all have, because I'm sure plenty of people got a lot of questions on this.
Awesome. Okay, well, so let me do this. We're at 1:59, so what I'm going to do is go to Mr. Sky Darmos. So let me take everybody out except for Sky. And Sky, welcome, sir.
It's an honor to be here. Yeah.
Oh, and you're over mute. Oh, wow, you're over mic'd.
Over mic'd? Why?
Yeah, which is good. Usually it's the other way around, but your mic is.
Yeah, I bought it yesterday.
Can you turn the volume down a little bit?
Okay, over mic.
I think
on
that's
my
better.
Computer?
That's much better. Much better.
Okay.
Wonderful. Wonderful. So you have a presentation again. So let me read this here. It's composition dependent gravity and gravity control spacecraft. This is something that you sent me, and we've had kind of a back and forth about this. You've also been collaborating a little bit with David Chester on this. David,
Yeah, a lot.
yeah. So
A little bit. Okay. Yeah.
You're researching quantum gravity. You're going to describe a detailed analysis of Cavendish experimental results going back decades that support the idea that gravity is related to baryon number, and so this would mean that we can inflate the mass without increasing the number of particles to make a spacecraft or aircraft free fall more slowly. So it's a little bit of a different approach to it, but it's very, very interesting. And
Thank you.
again, you have put so much work into it. So you should be able to do the advance and the back and forth slide thing. I'm going to take myself out, and thank you once again, sir.
Yeah, thank you very much for having me here. Okay, so this is SPD quantum gravity. SPD stands for space particle dualism. That's one very central concept. So space particle dualism theory started with an interpretation of quantum mechanics called the similar worlds interpretation. Now, this is quite different from the many worlds interpretation, because the many worlds interpretation includes all worlds, even worlds where I'm not sitting here, I'm sitting somewhere else. But here we only have the indistinguishable worlds. And that means there's no measurement problem. As soon as I observe something, some worlds that used to be indistinguishable are not indistinguishable anymore, and that's how the measurement problem is solved. And also, there's no spooky action at a distance anymore, because the spins are orthogonal on all the indistinguishable worlds, which are classical worlds. And so when I make a measurement, I find them to be orthogonal. There's nothing strange about that anymore. So that problem is solved. And then we have also a means by which consciousness can influence the world, which you could argue is already part of the Copenhagen interpretation. It could or not. But here it's very clear that consciousness has an influence on the world. So that's very important, because as Penrose has argued and Lucas, Gödel's incompleteness theorem shows or proves that consciousness must be non-computational, and therefore the world cannot be only guided by physics. It must also give consciousness a chance to influence things. And then we have Wigner's dilemma, and that's kind of resolved by saying that all the observers are entangled. Let's get to the next slide here, because we're in a bit of a hurry, I guess. It's a lot of slides. So Eugen Wigner initially supported the view that consciousness collapsed the wave function, but then he stepped away from that because he found it strange. He could not understand how you could do quantum mechanics in the space-time, because I observe you how you are in the past, and you observe me how I am in the past, and so then you're kind of led to solipsism. But when you realize that all the observers are entangled, then that resolves the problem, and you can have different people existing in the world, so there's no solipsism. But what you have is a cosmological solipsism, and I believe that's already part of the of other interpretations. When you look at the many minds interpretation, or Max Planck's interpretation, where he says that you could commit quantum suicide and then you survive in your version of the world, but everyone else's version you have died. And so you see that already in other interpretations of quantum mechanics, or basically in all of them, we live in an island of entanglement, and so there's nothing outside of that island. And so Yeah, so that would suggest that there's no other life beyond Earth. And one piece of data that supports that view very strongly is the CMB data, the CMB anomalies. We find that there are 4 major cold spots when you do spherical harmonics. You find that there can enter different numbers for n, and so the major cold spots, there are 4 of them, and they're in the direction of the north and south pole of Earth and the direction of the north and south pole of the plane defined by the orbit of Earth around the sun. So the chance that this correlation is accidental is 1 in 3,500. If you if you just look at the chance for having such large cold and hot spots, that's 1 in 3,000 and 3,500. It is when you look at how well the cold spots align with the equinox and the ecliptic of Earth. And the numbers and formula I wrote here are about predicting the exact effect size. How big are the temperature differences? We know them to be 1/10,000th of a degree. And so by using the observer effect, so basically this would be a kind of a passive psychokinesis over millions of years. Like the dinosaurs basically already looked into the sky, and by observing the sky, they collapsed the wave function of the sky and the universe. And so the universe is created in a retrocausal fashion from the present to the past. So it's the present creating the past. Okay, so here we also see some non-Copernican structures. Now, before 2019-ish, before 2019, I attempted to explain these concentric ring patterns by saying that we dive into the spiral arms and then our view is obstructed and then less stuff is created. But that explanation doesn't quite add up because the true distances, intergalactic distances that I found out in 2019, they show that the distance between the rings is much greater. It's not 2015 million light years, but 1 billion. So actually, the concentric ring patterns, one can explain them as baryonic acoustic oscillations, and that's how the mainstream does it, and that's how I'm doing it too, but using my theory and coming up with very precise figures for that. Next slide is so this is very central for the theory. So the first part was about explaining what a superposition is, what it means to be in many places at once. It's not the particles who are in many places at once. It's our consciousness, our collective consciousness is located in all worlds that are temporarily indistinguishable to us. So that only would explain a probability distribution that is a mountain, not a wave. So we have to explain the waviness of the wave function. And we can do that by postulating that every particle carries its own quantum of space, which is an oscillating complex area 2 sphere. So the oscillation basically means that that it has a complex surface area, and the real part disappears as the surface area is described by a complex number z, and that goes around the origin of the complex plane, and thereby the real component of the surface shrinks down to 0, and then it emerges again. So every time that happens, the probability of detecting that particle on a particular pathway goes down to 0. So that's what makes the probability go up and down like a wave. And here around we see some formulas like the radius of elementary spaces. The theory was born out of I was reading a book by Brian Greene. That was like back in 2005. It was talking about similarities between particles and black holes. It's a very popular idea. Was even mentioned in Big Bang Theory in the TV sitcom. So so the initial idea of space parallelism was that every particle was basically a black hole, but the surface, the event horizon, was viewed as a building block of space. But then in 2016, it turned out that if you use such small radiuses for your space quanta, then they cannot overlap to form a three-dimensional space. So basically, the elementary space had to be much larger, and actually they were scaled up in size exactly by the amount that that gravity is different from the electromagnetic force, and so you get very large elementary spaces, 10 to the power of so a resting electron, for example, would have a size of 10 to the power of minus 21 meters. And you can describe dimensionality, like you don't no longer say that dimensionality is 3, but you say it's 2.99999, and you have 35 nines here, and then you have a number, and so that explains why gravity is so weak. So gravity is explained by saying that there's a higher density of these elementary spaces here and a lower density here, and so particles are attracted to regions of space with a higher density of space quanta, and that's how you can explain gravity. And because there are already so many virtual particles, so most of space would be constituted of the elementary spaces of virtual particles, and so if you already have a huge sea of virtual particles, then adding a few an electron, the electron will emit virtual photons, and they will locally increase the density of space here. But it's a tiny increase because there are already so many virtual particles, and that's why gravity is so weak. Okay, so I won't explain all these equations here, but one can use this theory to explain the mass of the muon and the tau. I was trying to do that since 2015, and I finally succeeded in doing that in 2023. And so basically, we view second and third generation particles as merged elementary spaces. It's a bit like black hole mergers. You merge together and you get something bigger. And to get the exact result, you must consider so many things. You need to consider how particles polarize the vacuum. There's naked mass, and then there's the observed mass, and all these kind of things have to be calculated. And you even need to include something that I call neutral particle flavor mixing. And actually, it happens with neutrinos, but I say it also happens with electrons. Basically, we just don't notice it because of some dynamics with the wavelength. So the accuracy is very high, 99.191% for the muon, 98.91 for the tau. That was the first one, and then I got 100% for the tau, which means agreement within margins of error. And the final version was 99.998% for the muon and 99.83 for the tau. Okay, so so then we also have to introduce charge mass dualism. I won't talk about that long. I can just mention it briefly because it's not quite on topic. So basically, there's this electromagnetic mass theory that says that the mass of an electron comes from the energy that is stored in its force field, and I extend that to other particles, which to me is a very obvious idea because when we look at the neutrino, it's so tiny, and it's correlated to the it's associated with the weak force, and the weak force is so extremely weak, and I thought those two things must be connected. And at first, when you do the first calculation, they don't seem so connected. It seems off by a factor of 100, but when you account for all the running of coupling and everything, then it's very much correlated. And the mass prediction I have here is 99.84% accurate. So that's a pretty high, considering that pretty much nobody tries to even predict any particle masses. Now this gravity theory, it in Einstein's theory, you have Einstein's field equation, and basically what Einstein did is he turned it upside down, and it's basically like a collapsing black hole. When you turn it upside down, it looks like expanding universe. And then people claim that that's how you could do cosmology, but I disagree. I think that Einstein's field equation are only made for one single object. You can't even calculate two objects together. You can't have an exact solution that includes two objects. So I do gravity differently, and I agree with Newton actually in this regard. And Newton was asked, if there's universal gravity, then why doesn't the universe collapse? And I agree with his answer. His answer was because the universe is infinite, and from every direction there's an infinite number of stars pulling, and so that's why nothing moves and it doesn't collapse. Now something is moving, it is expanding, and in my theory the reason for the expansion is entropy. So it's an entropic expansion, and that explains why it's accelerating. Now of course we know about the acceleration very indirectly from supernovae. They're too faint, and the accelerated expansion softens that problem, but it's still actually there, and only when you use my theory it disappears completely. So it's very complicated in the mainstream to calculate distances using redshift, because when you go above redshift 0.2, then you have to switch to another formula. The formula that applies in my theory, it applies for all the redshift regimes. So it looks a bit different from the mainstream. It doesn't have it has a 4 factor of 3 instead of 1. It has to do with how the universe expands differently. In the mainstream, it starts off very high, with a very high speed, which it must, because otherwise it would collapse back. And in my theory, it cannot collapse back. It doesn't have to fight gravity, and that's why it can start off very slowly. So you can have a universe that not doesn't start with a big bang, but great slowness, like a very slow. So it's the Hubble value. The evolution of the Hubble value is like a quadratic function, basically. And you can also so the small equation, the T0, that's actually enough to calculate it. The complicated one on top, on the left, that one is more precise, because it's looking at what the initial Hubble rate was and so on. Yeah, it's the results are basically the same almost. And so when you look at a black hole, the entropy in a black hole increases with the surface area. So it's proportional to the surface area, and since the surface area is something quadratic, that's why the expansion of the universe is also quadratic. The evolution of the Hubble value. This is the age of the universe. Here, 42 trillion years. Full age is even longer. And we can prove that. I can prove that with 8,846 supernovae. When you see SPD is the name of my theory, you see that the expectation line and the measured line is the same. And for GR, for general relativity, it's way off in everyone, except for those lower than 0.2, the redshift. And that proves that the distances must depend on a single formula, not on different formulae for different redshift regimes. So that's what this is proving. But also the average luminosity agrees with that I get agrees with theoretical predictions, while the general relativity one does not. Okay, there's something wrong with this slide. Okay, some slides. Sorry, I should have checked the slides. The slides seem a bit off. Okay, what can we do about this?
Oh, yeah. So Sky, that actually is because you uploaded the PowerPoint, and that does happen sometimes. So
Can you
what
switch
I'm,
to another one?
yeah, yeah. So do you want to upload the PDF, and then you can
Yeah,
go back and,
upload the PDF.
yeah, yeah. That'll only take a sec. Sorry about that. That's
PDF. But so this file was from you. You uploaded that.
no. This was. It just doesn't always. It doesn't always interpret PowerPoints correctly. So.
Okay, so but I just uploaded the same again. I mean, I don't know what else to do.
And this is the PDF that you uploaded?
Let me see if on my computer it displays correctly. I mean, it's correct until a certain page.
Yeah. Is that a
Yeah,
PDF?
it's my problem here.
Okay.
So so I have to reconvert it. One moment.
Oh, okay. Yeah, I see what you mean.
It should be fixable very quickly. One moment. Like there's one.
Yeah, because I'm reviewing it on my machine, and it's looking funny as well when you get down to some of those more distant slides.
Like we can get the previous slide from the email, but okay, one second. I have it fixed right now. Okay.
Awesome. Okay. So let me do this then. I'm going to. Well, actually, why don't you upload it first,
Okay.
and then I
Okay.
will just
Now
switch.
saved and now converting. Desktop. Okay. Publish. Yes. Converting now. Okay. All the pages converted. So now uploading it here. Present slides. Did it work?
Okay, so you are uploading, and I do not see it quite yet. And does it look like it's uploading? The other thing that you could do is a screen share. So this
Yeah.
is the old slide deck, I believe.
Yeah, this is the old one. Yeah, it's the old one. But how can I remove? Okay, I removed it, and now I upload it again.
Yeah, give that a try. We'll see if we can get back in there.
Upload file. Okay. Is it uploading? Yeah.
Yeah, you sent me one. You've sent me 2 or 3 versions of this. The one that you sent the other day worked fine, and it looks like this one just something.
Yeah, sorry, I added so many additional slides, and something got wrong. I should have double checked it.
Oh, that's okay. That's okay. I know you were working on this thing until the very last minute. So
yeah.
How's that? How's that look? A little
Yeah,
bit better?
now it looks fine. Okay.
Perfect.
Okay.
Perfect.
So we can use my theory to also calculate the exact weakness of gravity. We do that by calculating exactly how many connections there are from one elementary space to the next. And that's very complicated stuff. I'm not getting into that. It's too much to cover. So then there's this little idea of mine about faster than light travel. Since the time dilation is correlated to an increase in the density of space. So on Earth, you have both the background from the vacuum energy and you have the background from all the virtual gluons from Earth, and then gravity should be weaker, but it's not, because if you change a constant all over space, then it's basically becomes time dilation. And if you change one constant, you change all constants basically, and so it would also change the speed of light. So you could increase the speed of light by suppressing vacuum fluctuations, and you can do that with one can do that with a Casimir experiment, but that's very limited. It only suppresses some wavelengths. And maybe if one could use some macroscopic, create some macroscopic fractals, then that would suppress them a lot. But that's very speculative. I haven't actually written anything about that in my books, so I'm going over to the next slide. My theory also offers a method of testing wave function collapse. We can actually pin down when exactly the wave function collapses, which was not possible before. There was no such proposal before. We can do that by delaying the quantum eraser in the late quantum eraser experiment further and further to see until when we can still do the quantum erasure. And so when the wave function collapses, arguably you cannot delete the information anymore. And there's also a theory of consciousness, which explains qualia, saying that everything we experience there's a record of that. It's a bit like the Akashic records. And it explains remote viewing. It also explains qualia. So the redness of red would be correlated to all the experiences we had with this frequency. Okay, so back again to the time dilation. So speed-dependent time dilation can be explained by saying that because the size of space quanta is proportional to the energy, when a spaceship has higher and higher velocities, has more and more energy, and that's why basically all the space quanta are getting inflated, and if you change something fundamental like space quanta everywhere uniformly in a frame of reference, that's like changing one of the fundamental constants. And so it doesn't matter if you say you're changing G. Well, we'll later learn that there are different G's, but it doesn't matter if you change G or H or C. It all basically boils down to a Lorentz transformation. And so that's time dilation. And you have the same with gravity, but the reason for that is very different. The reason there is that the density of space increases inside a big gravitational field, like the gravitational field of Earth, and that weakens the gravity between two masses. But that is like a fundamental constant change, and that's why that translates into time dilation. And this meme here I created a year ago. It says that you can never reach the speed of light. You can get closer and closer to it, infinitely close. And the same applies to escape velocities of a collapsing object. It can never reach the speed of light, and so you can actually you cannot actually have a true black hole with an event horizon, because time slows down infinitely before that can happen. And my theory supports that view very strongly, because it says that we exist in all worlds that are indistinguishable to us temporarily, and that notion of temporarily, it means that there's an absolute frame of reference. So in which frame of reference is it simultaneous and temporarily? So because no black hole can form from the view of an outside observer, so we say that it doesn't really form. It always remains a collapsing star frozen in time. And my theory also says that there's no Hawking radiation, because first of all, Hawking radiation, it violates a lot of conservation laws, baryon number conservation, lepton number conservation. You recall an evaporating black hole, it would basically turn into photons only and nothing else. So that's the only known way of destroying matter, basically, and it shouldn't be destroyable. And now that we know that the lepton number that now we know that electrons cannot decay and protons don't decay. So there's really no basis of violating these very fundamental principles. Also, the second law of thermodynamics is violated, but people argue that because the radiation goes into random direction, therefore entropy increases. But that's not a good argument, because when you have a sea of photons, you can measure each one of them, and then you know the entropy is very much reduced because you know the positions of things. So now let's get into the whole gravity business. So because in this theory, gravity is a side effect of the strong force, mainly the strong force, also electromagnetism, but mainly the strong force. So it basically a quark, it emits virtual gluons, and they increase the density of space. And so it only depends on the number of baryons, because it's only the number of hypercharges, basically. So you can calculate the G value of hydrogen by looking at the ratio between gravitational mass and inertial mass of iron. So basically you calculate out the binding energy in iron to arrive at the G value of hydrogen. So you divide the upper number 55.84 by the lower number 56.35, and you get the G value of hydrogen. And the basis of that is the G value of iron, which has been measured pretty well, I would say. I assume it to be 6.67428 for pure iron. The measured value is actually for stainless steel. The next slide. So here on the example of lead, here we do the opposite. We divide the gravitational mass by the inertial mass. So you can see here the different rows here are the different isotopes of lead, and the natural occurrences like 0.014 and so on. So the G value of lead is 6.6678. Okay, now molecules, they are pretty easy to calculate too. So hydrogen, so you have 2 hydrogen atoms, so there's a factor of 2, and then there's the inertial mass of oxygen in atomic units. So that's how you calculate this. 6.6618, pretty low value. So it's very good to do experiments with water. Okay, calculating the G values of mixed materials. Sorry for this big mess here. There are many different calculations here. So the only difference here is that we have to first calculate the atomic ratios. You cannot use mass ratios. So when you say 50% this material and 50% that material, that's not good enough. You have to actually know how many percent of this type of atom and how many percent of that type of atom. So you have to calculate that. So yeah, David Chester. No, it's hard to baryon lepton numbers aren't conserved. So that baryon lepton is conserved. Okay, good. Yeah, we can discuss that later. Well, it's only a minor point. It was about black holes. Let's focus on the gravity part. Thank you, David. So in practical situations, you always have, most of the times, you have different materials for the source and the test mass. So the effective G value has to be the geometric mean of the two. So you see the square root there, the G value of the big mass, the attracting mass, and the G value of the small mass, the test mass. And you can see here that the correlation is very strong. The odds that this is a statistical fluke is 1 in 10 to the power of 69, extremely small. And a very new value is one from Wang in 2009. That's lead and SO2. Yeah, so on to the next slide. But this is very, very important evidence. It's basically the strongest evidence that I have. So here I did some own gravity experiments. So here I measured the gravitational constant of water. Back at the time, I didn't quite realize that test mass and source mass are equally important. I basically assumed that it's mainly the source mass that is important. But nevertheless, the difference is very small. These experiments are very difficult. And in a more advanced experiment, I would have to use a laser and the container would have to be transparent. The Cavendish experiment, you basically have two big masses and you have a beam with small masses, and the small masses are attracted and the beam is twisting, but the torque of the string, it pulls it back again, and so you get an oscillating motion. And so that oscillation period is 15 minutes and 50 seconds. And if Einstein was correct, it would be 15 minutes and 49 seconds. So if you try to do this kind of experiment, it's very challenging. And so 2 years later, I did the meta-analysis of all measurements of big G. So that was much easier, just relying on the experiments that are already out there. But this took me like a whole month to do this because I had not done the insulation right. So there was air coming in. And once I figured that out, it worked. and this was some other trials I did before, which were not classical Cavendish experiments. They were more like those type of Cavendish experiments you see on YouTube sometimes, where it actually touches the source masses. So here I was basically just looking at a chaotic system, like it was not isolated from air, looking at if it would turn faster for iron or for water. Like it would take three minutes to touch for water and 2 minutes to touch for iron. And I was doing that statistically, and look, it was like a race. And I did that 66 times or so, or even more. Yeah. So then we move over to free fall acceleration. And so basically in Newton's theory, what you have is for example, when you want to calculate escape velocity or free fall acceleration, I think let's take the example of escape velocity. You have kinetic energy on the left side, and there's mass in it, and then you have gravitational potential energy, and there's also mass in it. And when you want to solve for the escape velocity, then the small m cancels out because it's both on the left and on the right side. But in my theory, there's no mass in the gravitational potential energy. It's instead you have a quark count, and that's this Y letter, blackboard bold Y letter, and the absolute value, it means the number of elements, how many charges are there, hypercharges. And so when you solve for that, then you basically end up with a stable ratio between the number of, it's still balanced with the mass is still there, but it's balanced by the number of particles. So you get a fixed ratio for different chemical compositions. And this connotation with blackboard Y is good for theory building, but it's not so practical because you cannot know how many. You cannot just put it on a scale that tells you how many particles there are. So it's more practical to use G values instead, and use inertial masses together with G values. And so for the free fall acceleration, you can basically just use the ratio of big G's, because small G is different at different elevations and different gravities. But the ratio between the G values at one location of different elements, it will be equivalent to the big G values of those same materials. So there's this SAS drop tower experiment. It's not so significant, but it's quite interesting, quite impressive to watch. You see that iron, it falls at this faster rate than the aluminum capsule that was used in the experiment, and so it stays on the ground. And aluminum is the same material as the hull, and so it also stays on the ground. Lithium falls slower, and so it lifts up ground, and also carbon, and also lead, and so they all lift up the ground. But the problem is beryllium and boron did not lift off the ground. It could be due to cohesion or something. Sass himself argued for that. So this experiment is not so significant in my own estimate. It's a 1 in 16 odds. Yeah. The neutrino free-fall experiments are much more significant. When you look at them, we see here they I should actually use the cursor sometimes. We see that the values here, the theory and expectation. So we see that the free fall rate is lower in every single case. That's like crazy. Every single case, it's lower. That means, and if you do the analysis, you find that neutrinos fall 1% lower, and here the odds are 1 in 1024. It's not sigma 5, but it's one piece of evidence, and there are so many pieces of evidence. Next slide here. So I did my own experiments. Here I did some experiments with a release clamp and a receptor platform, and I found that the difference in the minimal free fall times is exactly as predicted. So in this case it was 0.2 milliseconds from this particular height. And the reason why here we have to use minimal free fall times is because here it can only delay. It cannot fall faster. It can only delay. Then I did the same with release clamp and photogate. So here lead and steel, odds of 1 in 64, and the standard deviations were very high because the release clamp is very inaccurate. It's pretty messy. So I replaced that with a magnetic free fall mechanism, and here I got much smaller standard deviations and even non-overlapping standard deviations when increasing the height to 2.5 meters. Normally I was using like 2 meters. This was in one room. This was in Hong Kong. In another room, it was I got separated non-overlapping standard deviations in a second, third, fourth, fifth, seventh, and ninth trial. And here the combined odds are 1 in 524,000. Here in the next slide, we have a lead-filled sphere. Here I wrapped it up in paper because I had the theory that it shines through, the laser light could shine through. That didn't seem to be the case later on when I did some tests. So this is lead and this is zinc. And we see that zinc was falling faster 17 out of 19 times. And I would take care that the mass which supposed to fall faster was actually lighter so that nobody could blame the mass. So here the combined odds are 1 in 2 trillion. So the next one is wood zinc trials. Here the odds are 1 in 10 to the power of 20. So here I also got some amazing agreement in the time difference, 0.4 milliseconds as predicted. There's a slight difference here. 0.4 milliseconds difference is predicted for nutrient-rich wood, which has calcium, and 0.5 milliseconds if there's no calcium. And now we have the amazing experiments of Giorgio Toro. He did pendulum experiments, which were actually conducted in a vacuum, which is pretty impressive. And they're very careful experiments. And he sent me the results. And he conducted those experiments before even knowing about my theory. So they are not biased in any way. So, and the average agreement here is 99.97%. It's a 1 in 64 chance. And the next year, this year, he did more experiments, this time including plexiglass, which I recommended. Well, his value for plexiglass is not so good. It doesn't agree so well. but the agreement is now 99.95%, without plexiglass 99.96%, and the odds are the same, although there's one more element here, or one more material. The hierarchy is not longer perfect. Before it was perfect, so the odds have not decreased further. But if you combine the odds, it's 1 in 4,000 something. Next slide. Now these are some balance scale experiments that I conducted at the beginning of this year. Let me quickly check the time. Okay, we have time. So here in the pictures you see I did experiments with gold, and actually here you can see a lot of elements. I have about 50-ish elements here. They are the size 1 cubic centimeter, and you can see here that I was using a balance, this one here, to measure the mass, and then I don't have a force sensor displaying Newton, so I had to use a regular scale, but with a lot of digits, a very precise scale, and I had to decalibrate them to have them show different values, and then track how the difference changes with the chemical composition, and that's what you see in these graphs here. Of course, in the future, I will do this with a very advanced device which displays Newton and will measure with a resolution of 4 micronewton, not micronewton. So here then I included more elements. I purchased more elements. Some of them are quite expensive. So I got this graph. Here I must say I did many measurements and I chose the value that fits best, but the standard deviations you get there. And so these here, they were more randomized, like every measurement just taken once. And here I did many, and I basically so it's the best fit basically. And here but this here I measured only one time for each material. You see that the precision is not so high of these instruments, and that's why there are large standard deviations. So in the future I will get in maybe a month or so I will get a quite expensive device to measure very precisely the force, and here I expressed it in gram. I basically need 0.4 milligram precision, but not in gram, but in Newton. So that's 4 micronewton. So now to gravity manipulation. So as Tim Ventura, or as Tim already explained, if you are able to increase the mass without increasing the number of particles, then basically this is your mass. It goes up, the number of particles stays here, so your number of particles per kilogram is going to be very low, and that's why you will have a very low G value. And you can do that by using fiber wires, but usually they are not hollow, but you can use hollow core fiber wires to accelerate particle using lasers. So it's like a Wakefield accelerator, but you have to use a very dense gas, possibly hexafluoride, hexafluoride, something like that. The densest gas, or the second densest gas that exists, because some of them are toxic. This one is not. Then, but you cannot make a hoverboard, because if you go on top of it, it's supposed to be much bigger than yourself, because if you go on top of it, you're gonna push up the G value again. So that's not good. If you use this in Earth orbit, then you can have artificial gravity, because basically the spaceship will fall slower than the people will still fall at the normal rate. But if more and more people go into the spaceship, then the artificial gravity will start to wear off or dissipate as the orbits become more similar of the spaceship, and because the people by standing on it basically contribute to the total G value. Basically, they will be pushed to they will be in similar or natural orbits. So what you naturally have if you have like only one or two people standing on it, basically you have different orbits for the people in the spaceship. The spaceship wants to go here, the people want to go there, but because they're in orbit together, they have the same speed, and so they're forced into the same orbit, and so they're pressing against each other. Okay, so now to some additional evidence about this chromogravity. You could call it chromogravity, also, or SPD chromogravity. So there's a mass gap between neutron stars and black holes, and it's very, very big. And basically, that's, according to my theory, that's because the masses that we have for neutron stars and black holes, they are wrong. They're calculated based on the gravity, and the gravity, I mean, it's wrong for Earth and all the other planets. The planets, the masses that we have are basically assuming that the planets are like iron spheres, because that's the G value that is used. So in fact, you need more mass to generate the kind of gravity that we observe Earth to have. So all the planets are actually a bit heavier, and the sun is 0.5% heavier. And but black holes are actually lighter, because there's this for atoms, you have this nuclear binding energy that reduces the mass, but doesn't reduce the number of particles, and that's why you have higher and higher G values when you go towards iron. So for black hole, that happens with the gravitational binding energy. Gravitational binding energy reduces mass, but it doesn't reduce the number of particles, and so then you have truly like amazingly high G values. For black holes, it's something like 9.8 or something, if I remember correctly. Actually, it's written here 9.44. Okay, cannot remember all of my numbers. For neutron stars, it's 8.017. So you have 15 to 20% nuclear gravitational binding energy for neutron star, and you have 30% for black hole, and so that's a lot. And so black holes, in my theory, they are lighter to this amount, and neutron stars to this, and so there's a gap between them before, but as you translate to the SPD masses, the gap is closing in, so then you get a statistical gap that is natural. The next slide. So here I basically just calculate what I just talked about. Here we also have an agreement with the Tolman-Oppenheimer-Volkoff limit. I guess everybody knows Oppenheimer now, also because of that movie came out recently. So basically, the masses you see, they disagree quite extreme a lot with the Oppenheimer limit. But when you use my theory and the new Oppenheimer limit, based on that, then you have a very strong agreement. You have 2.08, and the values are very close. They're both about 2 sun masses. Okay, now we get over to some of my latest research. Composition dependent corrections to the perihelion precession of Mercury. So the Einstein's theory was agreeing very well with the perihelion precession until the year 2017, I would say. That's when Park, he calculated all the contributions to the perihelion precession. And when you do that, you risk getting too much perihelion precession, but you can't do anything about it because those planets all exist and they're all the comets and everything. So the only theory that could solve such a problem is SPD quantum gravity, because here you can actually reduce the perihelion precession, because if planets are really heavier than we think, then they're harder to move when subjected to the same gravity. So you get a little bit of less movement there. It's tiny differences, like 1 arc second in a century, but it's quite substantial. It's you get agreement, like when you take the data of Clemens, which is the standard. Actually, it's actually listed in Wikipedia as a standard, so to say, and you get disagreement for Einstein and agreement for SPD. So 99.79% agreement in value and disagreement in margins of error, and in my theory it's 99.98% and agrees. Perihelion precession of Saturn. Now it's tricky to talk about the perihelion precession of other planets because admittedly the perihelion precession of other planets are deduced from the perihelion precession, like any deviations are treated as one factor, treating all planets equally. And so they're not looking at the deviation for individual planets. It's all like put in a big jar, in a big melting pot. But there's some chance that the perihelion precession of Saturn that was reported, it was actually independent because it was based on some probe that was sent there. And here we have some excellent agreement, 99.9993% for SPD and 99.9990% for GR. And here both agree within margins of error. So here quantum gravity corrections of gravitational wave induced orbit decay. So this is a bit complicated and tricky. Here I got like 3 pages in the slides, but to sum it up, basically both in the mainstream and in SPD quantum gravity, you would have to think that the Taylor pulsars, which are famous for confirming general relativity, that they must be white dwarf pulsars because their mass is way below the Chandrasekhar limit, and I mean with rotation you can have even heavier. You will have the Chandrasekhar limit is even a bit higher, so they are even more sure to be white dwarf pulsars. And in the recent last 20 years, we have heard more and more about white dwarf pulsars. It's not quite yet understood how they form exactly. It's easier to explain the high spin with neutron stars. So anyway, if we look at the gravitational binding energy and everything, according to my theory, they cannot be a neutron star pulsars. They must be white dwarf pulsars. And so here I calculated the G value of a white dwarf, or those white dwarfs, without accounting for the gravitational binding energy, and then accounting for it and everything. And then I get an agreement of 99.912% for my theory and 99.83% for general relativity. And there's no agreement within margins of error for general relativity since 2010. So things have become rough for general relativity recently, but nobody talks about it except of me, at least in those areas. But I think in most areas, nobody even talks about the problems with measuring big G and how that actually violates the equivalence principle. Okay, so this is the last slide. This is my most recent work. It took me 2 years of brainstorming to figure out why the composition dependence in the Edwards experiment, which is the standard reference for the equivalence principle, why it is so tiny actually that it was overlooked until Fischbach discovered it in the data. And so in this first picture, you see the method applied by Fischbach. I calculated this myself, but I was basically using his method here. but with my very precise G values and everything. But here we basically take the ad hoc modified adjusted values by Edwish. Basically, when he had a half full bucket of water, container with water, he would measure value and then double that because it was half full of water. And that's a crazy method to use. I mean, first of all, you cannot rely on mass ratios. You would have to rely on atomic ratios. But I mean, it was 1908, so it was atomic physics was not so very advanced by that time, like or barely existing. Yeah, he could not have known about binding energy, all these things, and so he didn't really have any expected values. He was just doing an experiment to try to prove what he already believed, namely the equivalence principle. So, but when we use more precise methods where we account for the composition of all the brass cylinders that were used to put various materials in, if crystal, copper, sulfate, and tallow, many different materials. So he would get a better agreement. But while here the odds are a bit lower, but the agreement overall is better when you look at it here. And we get excellent agreement here because here we actually calculate how weak the effect is, because here we have to calculate an effect and then divide by a factor of 100,000. Like, that's a crazy amount, and it's very ad hoc. Like, what would make this effect so much weaker? Like, what's the reason? And Fischbach simply thought, okay, it must be a fifth force, and that's where the popular term fifth force comes from. He proposed it, and he would have to use a coupling constant for that, and basically, instead of saying that gravity is the side effect of the other forces, he basically said the opposite. So here we also have to divide. Here we have to divide by a factor of 100 of 1 million. So, and here we have to do, we get actually too small effect and multiply by a factor of 100. So basically the Edwish balance, it's basically looking at the gravity and the centrifugal force between two sides of a beam. And I mean, they're connected, they're one object. And that's why my expectation would be that you wouldn't get any composition dependence at all, but you still get some composition dependence because one side, the test mass on one side is hanging down and closer to Earth, closer to the source of gravity. That's why you get a tiny effect, and I calculate that tiny effect, which is at 10 to the power of -9 here. Yeah. So it's a very tiny effect, but the agreement is phenomenal, and actually all the elements agree here except for magnesium. But if you look at all the platinum pairs, you see that their standard deviations are usually 2, and here it's 1. So basically, the accuracy of the magnesium measurement was overrated. So if you use the same standard deviation for all of the platinum pairs, then all of the elements agree. And here you have 4 different elements that don't agree. Okay, and this is my book. It has 760 pages. It's on Amazon. And it took me 10 years to write. I started in 2014 with just 50 pages, and now it's 760 pages. It's basically an endless story. All my research goes into that book, and it's usually up to date. I update it every 3 months. So it gets bigger and bigger. So you get more and more for the same amount of money. Okay, that's all. Thank you for giving me the chance to speak here. It's a big honor because David Chester works for Tim, and I was eager to meet Tim, and thank you for letting me speak here.
Sorry about that. Okay. Sky, thank you. David doesn't work for me. I just work with David. He's one of the usual suspects. That's what we'll call him. Let me bring everybody in. And I'm going to take the slide deck down. Everybody, please put your hands together and give Mr. Sky Darmos an enormous
Thank you.
hand. Sky, it's obvious from your presentation that you have been working on that for many years, and it's absolutely tremendous. So thank you so much for presenting that. So I dropped a link into chat to the book on Amazon, but like people can always rewind the replay, right? This is live, so they can go back and pause it and look that way as well. So I definitely want them to check out your book on Amazon, and on the actual presentation page. We're trying to drop the presentations, and yours in PDF format is there, and it has the link in it. So
yeah, it's just a bit unfortunate that there was this glitch there with the PPT.
Oh no, don't worry at all about that. You know what? We have glitches all the time, but that's
I guess it happens to others too.
Yeah, it's part of the excitement, right? That's part of the excitement. So, yeah, thank you yet again, sir.
Thank you very much.
Okay. Well, so I'm going to take everybody out except for Mr. Shiva Meucci. And Shiva, welcome back, sir. So I have been begging for anybody who's watching, I've been begging Shiva to do more presentations because I love how you go through the history of science and like you pull apart these experiments, right? And sometimes they're accurate, sometimes they're not accurate, sometimes it could be interpreted different ways. And that's one of the things that I've seen like in my own history as well, right? Is like anytime you do an experiment, at the very least, there's always like noise that we throw away, you know? But like sometimes, you know, especially lately, like I've been reading that people are kind of making experiments fit the predictions, which is also kind of bad. So
yeah, there's a lot of issues with the experimenter effect, where basically the experimenter is imputing their view on the results, and you know the way in which they throw away or keep results and interpret them utterly changes what the experiment means. And so yeah, that's a lot of what the video we're gonna put on today. But I want to say a couple of words before putting the video on. Did you have the video available to?
I don't. I think I can pull that up. But I did want to ask you. Your mic volume is a little low. Is there a way that you can move it closer, or?
You know what? I can. Let me pick this up and see if I can get it a little closer to me over here. I'll just.
And what I will do in the meantime.
Hopefully that is that a little bit better?
Okay, there we go. And there is the video. Okay.
Okay. But yeah, I wanted to say a couple of words before, as kind of a preamble to sort of make a point, and then start with the video. So if you'll allow me, I just wanted to bring up a kind of a preparation for the video before we start it.
Oh yeah. Do you want me to? Is that this? Do you want me to do the screen?
No, that's some other points I wanted to say for right after the video.
Oh, okay. Okay. Yeah, go for it, sir.
Okay. So one of the things I want to bring up is kind of something that is understood in the science of developing artificial intelligence. And so the first example I wanted to give that's going to kind of set things up is that when chess champions are learning how to do things, hopefully some of you may have watched that recent drama. I think it was something Queen's Gambit, I think was the name of it. But basically, the idea is that a lot of what chess champions tend to do is memorize previous games that have occurred before. And that could be a very large portion of the way in which they play is by memorizing all of these games that have occurred. So I want you to think about what exactly is occurring there. Imagine if you only learned chess from memorization of these, tens of thousands, hundreds of thousands of games and their successive moves. Because the chessboard is fairly limited, it's actually not all that unlikely that you could memorize a very great portion of all the possibilities of what could occur in a chess game. And so what you then have is a stereotype for even if you as a player played against somebody who all that they did is try to figure out what the probability is that you are conforming to one chess game that occurred in the past or another, then it will seem as though they're playing in a novel fashion, but all they're doing is selecting a game that has occurred before and responding to you with the next move in that game that resulted in a So in other words, they are not playing in a way in which they actually understand the game. Now that's not that's not the only thing the chess champions do, but let's say that was a type of chess champion. That is, and like I said, this is kind of relates to something called the Chinese room, which was an argument against the older version of AI, which is more programmatic, and chatbots of ever having any sort of consciousness whatsoever. And it was so the Chinese room is this idea that if you take Chinese symbols to someone who's an English speaker and never, they know nothing about the Chinese language, you could pass some symbols that represent sentences underneath a door. And if they have the right set of rules and had a bunch of other Chinese characters that they could arrange according to a set of rules, just like those chess players, they could then pass another sentence of Chinese characters out from underneath the door, and you and the person on the other side, who is an actual Chinese speaker, could appear to have a conversation with the person who's in the room, but they're simply following a set of rules. And understanding that there is this difference between following a set of rules in a way that looks novel, but is not factually novel, that is very important to understanding that this same sort of thing can actually occur in mathematical physics as well. In other words, you can actually have a Chinese room situation where the rules of arrangement are more important than what the characters mean. And so I just wanted to kind of point that out as something that can be occurring and something that we need to consider as part of the problem with the abstraction and the shut up and calculate version of physics that's been going on for roughly the past 100 years. So, oh, and then there was one other example I wanted to get there, is that one of the things that can also happen is, let's say, for instance, in these very high level games that the chess, this chess player who was learning chess through memorization of games learned there was never an instance of a pawn being promoted. Then if that were the case, then they would never promote a pawn, and they would never, and they would insist that that is not a possibility within the game as well. So there's certain things of that nature where there's a lack of understanding, and that there's this solid line between comprehension and conforming to a set of rules, and not only conforming to the set of rules, but doing so in a way that is it has its own sort of meaning. So in other words, just understanding this kind of differentiation in the way in which we do mathematics for physics and separate the structures and the way in which they can be fit together properly from what the structures mean is, I think, a very important distinction that I don't think most people have really recognized as a possibility, that we can actually act as a stochastic parrot in the execution of being a physicist. So let's go ahead and start up that video and run through it, because I think that's a good preamble for it. Can you do that, Tim?
Yeah, sorry, I'm just doing that now. And
yeah, no problem.
Let me see. Okay, there we go. So I'm going to share that, and I'm sharing audio as well. Okay, and perfect. Okay. And so I'm going to play it like this.
To noun. Only by understanding this fact.
You have to back it up. Yeah,
Illusionists invented relativity 15 years before Einstein. That's right. It's historically accurate to say that Einstein merely finished relativity. But the central calculation that defines everything you know about relativity was created 15 years earlier by illusionists, and I'll provide the proof for that as we progress through our historical overview. Along the way, I'll grant you an intuitive understanding of relativity completely lost to modern audiences. So first, what many people don't realize is that for thousands of years, there was no difference between a magician and a scientist. The razor-thin line between illusionist and natural philosopher, right up to the 19th century, was only an attitude of hiding versus sharing, the knowledge they learned of the physical world. Each deeply desired to uncover and master the hidden truths of the world, and the word occult simply refers to that which is hidden. To accomplish this mastery, one must truly comprehend evidence and experiment, and most importantly, how humans experience and interpret it. To find truth, one must utterly master illusion and falsehood to be able to separate it from said truth. The process of removing impurity in the practice of alchemy was well understood to be a metaphor for the practice of removing falsehood during that process of truth-seeking which gave birth to modern science. Understanding the long history of focus on illusion and falsehood is critical to a more robust understanding of how and why relativity was invented, and indeed how science itself eventually emerged. For instance, while we can only speculate that all the engineers for the pyramids were thought of as magicians, we have adequate records from a little before the Common Era that the Pythagoreans were a mystical order who guarded secrets of divine geometry and the harmony of the spheres, with a death penalty for sharing those secrets because knowledge of truth grants power. Today, we think of their magic as nothing more than geometry and consequences of wave mechanics combined with some basic astronomy, but their secrets still move the modern world. Pythagoreanism influenced all the Greek philosophers, and it could be said that their search for magic was the beginning of Western science and philosophy. Plato's school, for instance, as a legacy of the Pythagorean cult, had the axiom, "Let no one ignorant of geometry enter," emblazoned above the entrance. In 415 AD, Hypatia of Alexandria was a well-known astronomer and mathematician murdered for the use of magic and astrolabes, and is held as one of the very first martyrs for natural philosophy. In the 1500s, John Dee, Queen Elizabeth's advisor, mathematician and astronomer who greatly advanced the art of navigation, was directly referred to as a magician and accused of demonology. In the 1600s, Johannes Kepler applied Pythagorean occultism and their musical view of the universe to develop his 3 laws of planetary motion. In the 17 to 1800s, Sir Isaac Newton, the most influential scientist in history, was not only an avid alchemist, but deeply entrenched in the general study of the occult. From ancient times to modern, it was always the same archetype of person, obsessed with comprehending reality, whose obsession itself was the requirement to produce illusions and deceptions of the senses. In the 1500s, Leonardo da Vinci created the first workable mechanical automaton that could sit, wave its arms, and move its jaw. During the 1700s, creating lifelike illusions became a sensation, with one of the most famous examples being the silver swan, which is an automaton that preens and catches mechanical fish. It does it all in an extremely smooth and surprisingly lifelike manner, set to music that it also simultaneously creates. The Mechanical Turk was a chess-playing robot that toured the world in the 1700s, but secretly hid a small chess master in the table below the board who could manipulate the automaton to move chess pieces via intricate mechanical devices. In each case, an obsessive dedication to comprehending the intricacies of the real world and its mechanical nature was required to separate human perception from underlying reality. We wouldn't refer to early illusions as smoke and mirrors without the fact that natural philosophers were all fixated on light and its manipulation, and so it is no coincidence that mirrors also pervaded all aspects of the occult since ancient times, and specifically played a crucial role in alchemy. Finally, one of the most famous and influential illusions of all time was Pepper's ghost, which was invented in 1862 during the heyday of optical science. It is still widely employed today to project deceased artists on stage in concerts, and it is often falsely referred to as a hologram. It is especially notable in our narrative that this particular mirror illusion with light would have reached a height of popularity right around the time that relativity was first conceived in 1889. These environmental influences grant us key insights into the scientific minds that lived in the transitional period in which relativity was developed. Every single scientist of that time period deeply and intuitively understood the intricacies and complexities of how to perform illusions and therefore debunk charlatans. Finally, they also understood that nature itself creates its own illusions as well. While superstitious people would have once believed that a mirage was the work of a jinn or a pernicious god that meant to tease the thirsty with a false promise of water, such apparent magic always drew the attention of the scientific mind. Therefore, the behavior of light was the core of 19th century science which gave birth to the modern world. Like the mirage, there is another automatic illusion performed by nature that every single scientist of that era would have known very well, but that you almost certainly have never even heard of. We must make sure you completely understand this particular little-known illusion so that you can understand why illusionists invented the least-known illusion of them all, relativity. First, however, we'll need to avoid a common confusion about our next subject, the Doppler effect. While Christian Doppler proposed the Doppler effect for light in 1842, in 1845 the Doppler effect was empirically tested and confirmed via sound experiments. It is absolutely critical that, if you know anything about relativity, you remember that relativity does not apply to sound, even though Doppler applies to both light and sound. For example, for light to behave according to the modern interpretation of relativity, it is mathematically necessary that every moment be four-dimensional. Sound only requires 3 dimensions. This differentiation between the mechanical workings of sound and modern ideas of light did not exist until after the illusion at the heart of relativity that this film is addressing. Put in simpler terms, classical waves were understood as something that couldn't exist on their own. Remove the water and ocean waves cease to exist. Waves are an action occurring to something else. The wave only exists as a notably active portion of some substance or set of things. Classical waves, put simply, are just a consequence of particles of a substance bunching up and spreading out. A disturbance from and return to, an equalization of stresses between parts. It's a little like entering a crowded elevator in that everyone slowly adjusts to try to balance the space. Because it takes time before a neighbor reacts, there is overshoot, and because there's overshoot, there is backfill. That's all a wave is. Displacement from equilibrium, non-instant reactions, return towards equilibrium and overshoot. Disturbance, lag time, and movement towards least resistance. What the medium's properties are, where it is, and what it's doing, completely defines the waves and flows moving through it. A wave is nothing more than what sections of a substance are doing, a verb, not a noun. Only by understanding this fact can you really understand the specific illusion we are about to discuss. It is an effect that even physicists are rarely aware occurs in sound if they haven't thought it out. Let's quickly review the salient facts of the Doppler effect. The characteristic change in frequency can be caused by 2 different mechanisms. First, by moving the emitter through the medium, and second, by moving the listener. Let's say you're in an ambulance. Waves emitted from a moving emitter are squashed in the direction of travel because the wave only travels at a given speed within its medium. Air in this case. So even though you're creating the same number of waves per second, the ones going in the same direction can't get away the normal distance before you create another wave, and they get stacked up this way. The ones moving away from the emitter also have to travel away from the point of emission at a speed determined by the stationary medium. So even though your emitter creates pulses at the same timing, you've run away from waves going backwards, so you added your motion to the distance between waves, and this causes them to be spread out. This effect occurs no matter how the difference between the emitter and the medium is created. If there's simply a strong wind, the waves get stacked up and stretched out by the same mechanism. The illusion, however, is this. Place 2 people on a flatbed truck in open air, and no matter how fast the truck carries them through the air, they will hear no Doppler effect so long as they are moving together. Why is that surprising? Because we know that the waves going in one direction are physically different from the waves traveling the other direction. People on the ground will certainly hear the Doppler effect in the voices of the people passing by, but the people moving together cannot detect it at all. If we ignore things like turbulence, there's no clever experiment they can perform on the back of a moving truck which will reveal the frequency shift we associate with Doppler effect, even though it is certainly happening in reality. The waves truly are beaten into the air in physically different ways depending on the direction of travel. The issue, however, is that there is a second method, where the wave size stays the same, but the listener can run into or away from the waves to change the perceived frequency. The 2 effects can be combined in an opposing manner to create an exact cancellation and thus produce our illusion. It's simply that a perfect compensation automatically occurs. What is gained by motion at the emitter is lost via motion at the listener. For instance, looking upwind. Even though waves are actually bunched up and have shorter physical length between them, the listener is actually moving away from them, so they are playing catch-up, arriving at a slower pace, no matter how close together they are in the air. Each peak has a longer delay between their arrival, which perfectly lowers the frequency it was raised for people hearing it on the ground as they passed. Furthermore, if they move around on the truck, the only Doppler they will detect is the motion between them, not their full motion through the air. It is this strangely automatic and perfect compensation that hides the fact that the waves physically exist in different shapes, but the co-moving observers cannot detect the fundamental truth of this very real alteration. We know it is an objective truth that the Doppler effect is occurring, even though the illusion hides it, because we know that sound waves do not exist without air any more than ocean waves exist without water. We know waves aren't independently real, so we can separate truth of their relative size from the false equivalence of the subjective experience. And as a good illusionist and good scientist, we can separate fact from fiction, even when experiment cannot. The consistency and convenience of the observer's perspective is completely irrelevant. The experimental replicability of it is irrelevant. Subjective experience, even subjective experience of instruments, is irrelevant. Humans and instruments alike can experience perspective illusions. It is in the infinite causal depth of events and the unbroken mechanical interlocking of them that we separate superstitious thinking from rational. An illusionist knows that perspective is the heart of illusion, and only a fool believes his perspective trumps underlying reality. This hierarchy of objective reality placed above personal perspective is the separation of magic from science. Every charlatan shows us a test of reality that seems to prove something. Causal consistency, however, not bare empiricism, is what first separated science from superstition. Every superstitious person has mountains of evidence for their beliefs, but it is the process of identifying the interlocking nature of reality that reveals what lies under our many illusions and separates out the dross. This mechanic's first ideology, hard-won over the thousands of years of search for magic, is what brought humanity from the caves with the light of science. Mechanical reasoning is the beating heart of scientific pursuit that weeded out faulty interpretations of experiment. Magic is causally inconsistent, but science is a perfect interlocking causal machine. This mechanism of a compensatory illusion you just learned about in the Doppler effect will now lead you to independently discover relativity yourself in just a moment. Let's now embark on the final leg of our journey as we create a devious extension to the Doppler illusion we just described. Let's imagine that I had some friends who ran some experiments on one of those open trucks to try to pierce the Doppler illusion. And in the process, they discovered a way they could at least detect their motion through the air using sound, even though they couldn't detect the change to the sound. They had placed a small plate 10 feet forward from a speaker at the back of the truck, and another plate 10 feet out to the side of the truck. The speaker emits a single short chirp. Using a microphone just above the speaker, they listen for the reflections of the chirp that come from those plates. It turns out the echoes will always be different in timing by a certain amount that depends on the speed of the truck. Because they know the angles and distances the sound would have to travel through stationary air as the experiment moves through it, they can calculate the exact speed of the truck. They simply did a little calculation and discovered that while the forward plate runs away from the sound and the reflection slams quickly back into the oncoming microphone, the total amount of air the sound traverses is always greater than if the experiment was stationary. The path the sound must take out to the side, however, is very different in that it has to travel out at an angle and back to catch the moving microphone. While being longer than the stationary path, it's shorter than the path along the wind. Given that my friends are also good Platonic philosophers and scientists, they did a little geometry and figured out that regardless of the speed, the path out to the side and back would always be the square root of the path along the wind. They also found that there was a relationship between the speed of the wave and the speed of the experiment that always related to a specific angle, and that difference always leads to a certain amount of growth in the path length across the wind. It's a geometric formula. Pythagoras would be so proud of them. But we, my friend, are illusionists and can use their work against them. To create yet another compensatory illusion in this experiment, we merely need to invent a material which shortens in response to wind passing across it in the squared relationship they already identified. We could make sure they are only allowed to use this reactive material to construct their experiment. Then, just like the Doppler illusion, no matter the speed of the experiment, the chirps would always return at exactly the same time by eliminating the difference in distance. To put it as George Fitzgerald did in 1889, we'd need to shorten the experiment by an amount depending on the square of the ratio of their velocity to that of the wave. While it turns out one must take Fitzgerald's relationship, subtract it from 1, and then find the square root of that for the final calculation, he had described the root of the illusion. There you have it. Shortening perfectly compensates for all speeds of the truck, making both of the very different paths exactly equal in time and path length through the air. Our sound experiment is an exact analog of the Michelson-Morley experiment, which was the entire impetus for relativity. Now we can see how the core principle of relativity, the factor of change, was invented by illusionists 15 years before Einstein. But our story doesn't end there. Let's dive deeper into how this illusion relates to our modern understanding of relativity. Now, you might be wondering, how does this relate to light and Einstein's work? Well, here's where it gets really interesting. The Lorentz-Poincaré ether theory, which preceded Einstein's relativity, treated light as a mechanical wave, just like sound. This might seem counterintuitive to our modern sensibilities, but it's crucial to grasp this perspective to see how the illusion of constancy in the speed of light shaped modern theory. Poincaré's mechanical relativity is historically described as mathematically equivalent to Einstein's relativity. But those two interpretations still describe completely different versions of the world. In this original view, light is just a mechanical wave traveling through the medium of space called the ether, just as sound propagates through air. The key insight of Fitzgerald, and later Lorentz, was that if matter itself contracted in the direction of motion through this ether, it would create an illusion of constancy in the speed of light, just as our imaginary material created an illusion of constancy in the speed of sound. This formula is the exact basis for what we now know as the Lorentz transformations, which are at the heart of special relativity. A formula that is a mathematical description of our illusion. You must remember, however, constancy in light is nothing like what the word seems. It's a solipsistic perspective where waves always propagate according to your personal experience. Constancy is the belief that whatever speed you go, light propagates with you. We had to add another dimension to allow all the conflicting perspectives to be true simultaneously. If the inventors of the formula were right, however, then just like our illusion with the truck, the Michelson-Morley experiment simply fooled people into believing that a wave always behaves the same regardless what the medium or emitter is doing. Because we know a wave is an action and not an independent object, however, we cannot be fooled by the illusion into believing all perspectives are equal. Einstein's genius was in recognizing that if this contraction was real and universal, we could ignore ether altogether and greatly simplify the difficult calculations of Lorentz by merely treating the constancy of the speed of light as fundamental. He gave us a shortcut that allowed us to calculate electromagnetism much faster and easier. Simply act as though the topical illusion is truth and ignore the underlying mechanics the math refers to. But here's the kicker. In the Lorentz-Poincaré view, time dilation and length contraction are real physical consequences caused by motion through the ether. The constancy of the speed of light may be just an illusion, but one correlated with real, measurable consequences according to the precursor theory. The mechanism that underlies the constancy effect is not just a mathematical trick or a quirk of measurement. It's a fundamental aspect of how matter interacts with the medium through which light propagates. It shortens. In the precursor theory, the apparent constancy of light is a symptom of a deeper mechanical truth. The constancy we observe is like the woman sawn in half, but the deeper truth is that we experience this amazing thing because real mechanical devices are doing something very particular. Now you might be thinking, but hasn't this ether theory been disproven? The answer is no. Only old versions of ether were ruled out, not this relativistic one we're talking about. The mathematics of the Lorentz-Poincaré ether theory are identical to those of special relativity in the overwhelming majority of situations. The key difference lies in the interpretation and the underlying physical model. Einstein and Minkowski's approach, which we typically learn in school, treats the constancy of the speed of light, the illusion, as a fundamental principle and ignores ether, the causal mechanism of it. The Lorentz-Poincaré view, on the other hand, retains a preferred frame and treats constancy as a perspective illusion created by the interaction between matter and the substance of space. You might wonder why we don't hear more about this alternative interpretation. Well, for most practical purposes, both theories make the same predictions. That was the beauty of Einstein's simplification. However, there are some edge case situations where they diverge, and this is where things get really interesting. Experiments like the Sagnac effect, the results of the Harfili-Keating experiment, and observations of the anisotropy in the cosmic microwave background radiation all suggest some form of preferred frame, something that aligns more closely with the precursor ether theory than with the conventional interpretation of special relativity. Even more surprisingly, general relativity itself, Einstein's crowning achievement, introduces concepts that are more compatible with an ether-like substrate than with the etherless view of special relativity. Minkowski's space-time that Einstein eventually used in general relativity behaves in many ways like a physical medium, but is fundamentally different. It allows the physical impossibility perceived in the illusion to occur by adding more space to reality, which can accommodate 3D conflicts via adding the fourth dimension. Einstein famously quipped about space-time when it was first introduced. "Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore." But when his mentor Minkowski suddenly dropped dead shortly after his snide remark, he found a way to use the mathematical formalism. It's worth noting that even Einstein himself, after a few years of consideration, came to believe that some form of light-bearing medium was absolutely necessary for his theories to make sense. Just 5 years after he published his opus on gravity, he wrote an entire lecture explaining the necessity of ether. That 1920 lecture can be summed up with the following quote: "According to the general theory of relativity, space without ether is unthinkable. For in such space, there not only would be no propagation of light, but also no possibility of existence for standards of space and time." Strangely, only a few historians are aware that Einstein denounced constancy as incompatible with his finished general theory on at least 5 different recorded occasions. And other renowned fathers of physics also called for a return of the ether as the field continued to progress. In 1951, Paul Dirac published a paper on the ether he summed up with the following: "This motion's physical significance in the theory is that if there is any electric charge, it must flow with this velocity. And in regions where there is no charge, it is the velocity with which a small charge would have to flow if it were introduced. We now have the velocity at all points of space-time, playing a fundamental part in electrodynamics. It is natural to regard it as the velocity of some real physical thing. Thus, with the new theory of electrodynamics, we are rather forced to have an ether." In the 80s and 90s, John Stuart Bell gave numerous statements advocating for ether, saying, for instance, "I would say that the cheapest resolution is something like going back to relativity as it was before Einstein, when people like Lorentz and Poincaré thought that there was an ether, a preferred frame of reference, but that our measuring instruments were distorted by motion in such a way that we could not detect motion through the ether." Now, you might be wondering, if this alternative view has merit, why isn't it more widely known or accepted? Well, that's where the history of science and the nature of paradigm shifts come into play. Thomas Kuhn's famous work, The Structure of Scientific Revolutions, discussed how difficult it can be for new ideas to replace established paradigms, even when evidence favors them. It's a problem so well known there's a name for it: Planck's principle. Paraphrased, science progresses one funeral at a time. The shift from the many additional calculations required for relativistic ether theory to Einstein's shortcut was so appealing, and Einstein's formulation so mathematically elegant, that physics as a field was reluctant to look back. The more concise formulation reduced manual calculation overhead and made forward scientific progress easier. Relativistic ether never caught on because the work was hard enough without the extra considerations it brings. They asked themselves, why look backwards? And the ether became synonymous with outdated thinking, despite the fact that the Lorentz-Poincaré formulation had no evidence against it. No one ever suspected that all the additional underlying mechanics would ever, one day, grant additional insights, so it was forgotten for a century. But here's the most important takeaway. Whether you prefer the Einstein-Minkowski view or the Lorentz-Poincaré view, the fundamental effects of relativity, time dilation and length contraction, are real observable phenomena. The only debate is about the underlying cause and interpretation, not the effects themselves. These effects aren't just abstract concepts, from the design of particle accelerators to the need to account for time dilation in GPS satellites. The universe really does behave this way, regardless of how we choose to interpret it. The only question is if all the additional underlying mechanics of ether grant us any additional insights. Will the additional information allow us to manipulate space? We're finding that with the many crises cropping up all throughout modern physics, the calls for revolution are being answered with hydrodynamic space we used to just call ether. We'll have to save exactly how the ether paves the way into the future for a different video, and so we come full circle. Just as the illusionists of old sought to understand the fundamental nature of reality by mastering deception, modern physics grapples with the possibility that what we perceive as the fundamental constants of nature might themselves be a kind of cosmic illusion, a perfect compensation that hides a deeper reality. The next time you see a magic trick, remember, you're not just watching an illusion. You're witnessing the roots of curiosity that culminated in a tradition that has driven scientific inquiry for millennia. A tradition that gave birth to relativity itself and continues to shape our understanding of the universe to this day. And who knows, perhaps the next great breakthrough in physics will come not from a laboratory, but from someone who understands that to reveal the truth, you must first master that which is hidden.
Shiva, that's amazing. That's absolutely amazing. Let me click stop sharing. Okay. And let me apologize for not
So yeah, something that
maximizing.
we could do some a little bit of discussion about it, but I did want to say a couple to kind of follow on to that. So so from the ether view, what where can we go from there? And I wanted to say a couple words about that.
Now, can I put your notes up now? Can I put the notes up that you
yeah,
have?
let's go ahead and start with that, because even though I've got these slides prepared, I'm only really I'm only prepared for presenting a little bit of it. I can't really do all of the slides that I put together here. They're more notes than they are really slides. So we'll do some discussion after I just bring up a couple of things that I believe are a kind of a roadmap to how we might be able to manipulate the ether and use that for things such as alteration of gravity. But while we've talked about in the past some of the ideas of what exactly is gravity in the ether view, and that is going back all the way to the way in which we perceive the start of ether theory, which really probably had its best start with Fresnel and in his prediction of the Fizeau experiment, which he successfully predicted would carry ether along at a certain rate and therefore carry light along at a certain rate. It did exactly as he predicted. His theory, however, was that there was more ether. There's an increased density inside of matter that causes refraction, instead of the opposite of that, which would still change the wave function in the same way, which is a reduced rigidity. So in other words, it would still slow the light if we looked at it from a perspective of reduced rigidity. So this is the one way in which we can completely turn our perspective of ether and matter inside out. So all these various extensions of ether theory that we see all throughout modern physics, using different terms that they don't say ether, because that's the rule of the past century. You never say ether. But things like a crystalline structure with topological defects in it, these are basically spaces that open between. So in other words, when you look at space as the real thing, and matter, and especially things like mass as alterations or reductions to changes to the actual thing of note, then you have a different way of looking at reality that's kind of inside out of our previous views. So just to kind of look at some of the hints we had mentioned, all of these various ways in which we could see that there's a preferred frame, and that even general relativity had a preferred frame perspective, and that matter of fact, Einstein referred to this often as like a Machian perspective, because he actually liked Ernst Mach's idea that that can be paraphrased, saying that when the subway station jerks, it's the stars that throw you down, and that is basically the idea that there's a universal frame of reference. So the Faraday paradox, just to quickly touch on that, but I think that this is kind of maybe one of the small roadmaps along the path of experimentation, et cetera, and how we might manipulate the ether. Now, the Faraday paradox is the specific embodiment of it that I'm talking about is when you take we know that we can induce an electric current with the difference in movement between a magnet and a conductor, right? We just move a magnet through a conductor, it creates a current. We're all very usually aware of that if we know anything about electricity, etc. However, with the Faraday paradox, one of the things we find is you can take a circular magnet and a circular conducting disk, and if you put the magnet over it and rotate the disk, of course you can produce a current in the disk. However, if you hold the disk in place and move the magnet, it does not create a current, which is very unexpected. And then worse yet, you can take the magnet, place it on the disk, and spin them both, and it will also create a current. And so what this indicates, I believe, is that there is a, and just as Faraday also believed, there is a preferred frame in which the magnetic field is staying stationary. Now, we can go into some discussions about that later, but just from this perspective, that I believe that is a sort of a hint along the way that these the lines of force are, of course, these vortex filaments, which I'll briefly just say they actually work well from the Kosarak continuum perspective, where we have a superfluid space, which is also just like Maxwell's inviscid, fluid that he modeled Maxwell's equations in. And so the Kosarak superfluid actually can help us look at the direction that Einstein eventually took towards torsion from a more microscopic perspective, and allows those additional degrees of freedom in rotational, basically rotational degrees of freedom that will that allow a different view of torsion that I believe that basically had he rejected Minkowski's formalism eventually, I believe that Einstein and Cartan would have actually developed ether theory in a way that would have already advanced us far beyond where we are currently. But so the first thing is the Faraday paradox that gives us kind of a hint in direction. And then here's the thing that I wanted to talk about really quickly that I think is very valuable for people who want to do experimentation in, and look at things like, for instance, Tesla's idea of scalar waves. So a lot of times whenever we talk about scalar waves, there's some interpretation of Tesla's works and words, and a lot of times probably one of the best interpretations are the idea that scalar waves are longitudinal waves in the ether instead of the transverse waves, and that they would travel at orders of magnitude faster than transverse waves, because that's kind of a normal thing with waves, that you have of those two types of waves generally in the substance, there'll be a difference in their speeds, so we kind of expect that a longitudinal wave would travel much faster. But what I wanted to talk about instead is the idea that what Tesla was talking about many times whenever he was talking about wireless transmission, he was talking about loading the ether in a certain way. And for this, I need to describe that there's two types of resonance that people don't really think about. So the original type of resonance that most people tend to think about is that between borders you have a reflecting wave, and that when the waves end up adding up in some way in which you add additional amplitude to the wave repeatedly as it reflects back and forth, you can cause this resonance to store more and more amplitude in a given wave, and it's because of the use of these borders. However, there's another kind of virtual border that is different, and I'll explain it in a way that everyone as a kid had these experiences with water when you swing in a pool. Well, one of the experiences that I had that kind of revealed this secondary type of resonance that does not require borders. But I had the go jump in, rock the pool, the waves kept bouncing back and forth inside the pool, and that was a lot of fun for kids to make the waves higher and higher because they kept adding energy to the waves that were reflecting. However, there is a way in which if you simply touch the surface of the water and press down a little bit, and then keep changing go between a fast frequency and a lower frequency with a higher amplitude, you can begin to make the water bounce further and further and further in place without any borders having any effect. And what you're doing is you're using the reactivity of the substance itself as a way in which to create a local loading of the substance. And so this is a way in which I believe that that whenever Tesla was talking about his standing waves, and whenever we hear about these ideas that he was able to light a room where there was light, but there was no source for the light, and whenever he was talking about this way in which of transmitting power, I believe that this was the type of resonance that he meant to convey, and that this type of resonance might itself, as you create this localized resonance itself, may be the way in which he was producing these scalar waves. Perhaps that is just a speculation I have, that perhaps that type of loading of the medium and using that sort of resonance, where you have a sloping between high frequency and low amplitude up to a low frequency with a high amplitude, and cause that loading of the local substance as a method of resonance, which is against the reactivity of the substance. I believe that may be a path that will be fruitful in the future for our development of use of manipulation of space. And so, and just going back to, of course, one of the ideas of, work with gravity is basically the local alteration of space's properties, ether's properties, and specifically in its rigidity, and this is comes at the same time as all of the increase in vortex filaments and the local vorticity of space, which is what we basically see as the way in which we see there's a gradient produced where a sort of buoyancy effect happens between massive objects. So okay, so from here I wanted to that was just kind of to finish off where the video was going, and I was hoping we could have a little bit of discussion with the group from this point, and about the specifics of the video and how it relates to the development of relativity.
Yeah, Shiva, again, thank you so much. So before anything, let me bring everybody in. And again, you have put so much work into that. Everybody, please put your hands together and give Mr. Shiva Meucci an enormous applause. Shiva, thank you. Thank you. Again, I love it that you were going through and showing different perspectives and different interpretations for all this. And the amount of work, this is one of those videos. I'm going to promote the video itself. I'm going to have that out there on my social networks. Hopefully more people can see that and just start asking questions, right, about science, and the more they ask and the more they read, the more they'll learn. And I think the history of this is so important. So yeah, if you guys want to we have probably about 10 minutes, I think, before lab time, and we could probably go a little bit longer than that if you want. But
yeah, I was just hoping that the idea of putting together, how there is an automated compensatory illusion in Doppler effect that occurs would help bring out the perspective that Fitzgerald and the others did, where there would be this automatic compensation. So it is natural for automated compensation illusions to occur in reality, because that's what occurs in the Doppler effect. And it turns out, by the way, that the Doppler effect would be implicated in the process of shortening as well. But that's a discussion for another time.
Yeah. One question.
Mm-hmm.
Yeah. What would be your absolute frame of reference? What would be that frame of reference? Is the Milky Way? Is it Earth?
I don't believe it would be any one of those. In other words, it's just like, what's the absolute frame of reference when in the ocean? It is the water, but the water of the ocean is moving. There are currents in which are moving in different directions, and there are local eddies and currents, and there are large scale currents. And so the same thing would be true of any ether view, is that everywhere there would be. You can look at it as an average. In other words, you can average out all those alterations in current. When you want to navigate from the U.S. to Europe, but that is an averaging out of what's actually occurring. So you can think of the space in between as this one thing on average, but you can also go an additional layer deeper and consider the smaller scales of differences that in flows.
There has actually been some research on the dipole in the microwave background. It was originally attributed to movement of the Milky Way relative to the CMB, which you would probably take as the ether, the CMB background, I guess. But then there was an Indian astronomer, and he showed that when you really attribute that to a speed, when you look at different sources of radiation, then you actually get totally different directions of movement and totally different speeds. So that casts some doubt on it being an actual speed of movement. My own interpretation of it is that it has to do with the observer effect in quantum mechanics. So, but I'm generally sympathetic to the idea of an ether, because I also believe in absolute space and time, but more because of quantum mechanics. Yeah.
And one of the things this ether view does, it actually leads smoothly into deterministic chaos and and a pilot wave version of quantum physics. In other words, they're kind of it's very natural to go from one to the other, so that the idea of the observer effect is only a matter of interaction effect. In other words, instead of observation, as a lot of people like Neumann and those who had this, cut and
Yeah, okay, I'm in that camp. I'm actually in the
all that's
consciousness camp, but it's okay.
right, and all of that is put aside, where instead this viewpoint leads to to deterministic chaos, which is, in other words, there are mechanics, but the mechanics are so complex and have so many inputs that it's impossible to predict with any reasonable accuracy after any.
So you don't believe in free will, basically? Yeah.
I believe that the idea of free will is generally misconceived, because the idea of the self is misconceived, because we put things in boxes and make them more discrete than is actually realistic. And so,
What about Gödel? What about Gödel's incompleteness? And he showed basically the consciousness and non-computational and non-physical, basically.
Yeah, that's the idea of computation there is linear. In other words, there are no. That's the same thing as the three-body problem. Whenever you take a very linear perspective on it, it's not solvable. But you have to look at things that a more simultaneous view of all the effects. In other words, you can't just look at one. This leads to this, leads to this, leads to this in a very linear fashion. That's why you have the three-body problem. Instead, you have to look at a lot of simultaneous effects that are coming in. And what I would say is the way of phrasing it. I call it paracausality. In other words, the causal effects of all of the various, you can't look at one butterfly effect. You have to look at all of the butterflies affect linear chains all side by side, and how are they interacting with each other. And that's the only way you can look at, anything complex. And so whenever we have these ideas of determinism, we're like, oh, you don't believe in free will? Well, no, I'm just saying the idea that there is not a free will in determinism is a misperception of the idea of chaotic determinism. In other words, it's a misunderstanding of chaos theory. And so,
but you also don't believe in telepathy and.
No, I believe that those are totally possible as ways in which there's information stored in the vacuum, and that the way in which the vacuum interacts with the mind may allow for various effects that we don't expect. And I actually have a very intricate model of exactly how the vacuum and the brain work together in a way that has to do with the Bohm-Pribber model, which is one of the reasons why working with David Bohm's version of pilot wave, why those things interact very well is actually kind of convenient. And I hadn't even really realized when I to a version of looking at the way in which the brain works, which is the holographic version of the brain. And so
so you accept non-locality.
Say again?
So you accept non-locality, that is good. Yeah.
Only a certain version of non-locality, in which the idea of non-locality comes from the fact that there are contributing factors from various places that are occurring. In other words, there's non-locality that occurs in fluid dynamics, but the non-locality that occurs in fluid dynamics is causal. In other words, there is a causal linking, there is a mechanics to it. There is nothing magical or weird or strange about the non-locality in fluid dynamics. There is just simply the fact that one cannot separate. Okay, we can have a false separation of the water in a river from the riverbed. When we say river, we actually mean the way in which both the water is cutting into the landscape and the way in which the landscape is shaping the water. And if we look at it at different scales of time, we can believe that the water is just pushing the land around over thousands of years. We watch.
So you have a speed for that?
Say again?
You have a speed for that, for your entangled particles, how fast they exchange information?
The speed is the speed is not relevant in the same way. This is a very long discussion about Bell inequalities. If you look at the way in which Bell wrote an entire book denouncing the way in which we now interpret Bell inequalities, by the way, and he repeatedly went over and over about how pilot wave solves the issues and discussed this. Like it was John Stuart Bell's quote I gave in that video, specifically from it's because he was trying to debunk people's interpretation of his work, and he went through a lot, and people didn't pay attention to what he had to say. But specifically, the idea is that your ideas of non-locality have a lot to do with non-locality in holography. In other words, if you look at the way in which a hologram displays a picture, there's a common source, and there's a commonality between the what you may think of as the events in the whole field of wave production that comes from a holographic surface. And so there's a variety of things that are oversimplifications, and I agree that the oversimplifications are not good ways of looking at the universe. However, to understand a chaotic determinism version of reality, to understand this version, a more complex version of causality, allows us to see these perspectives of instantaneous action at a distance as nonsensical, and that there is an actual mechanical reasoning that will work. Just like there's a mechanical reasoning for non-locality in fluid dynamics, there's a mechanical reasoning for the non-locality of that we see in quantum mechanics in a pilot wave version of the universe, which is, so there are non-local effects. But the point that I was trying to get to is with this idea of the river, the water, the river bed, both of them make up. You can't separate them from each other. They are a river. But the same thing is true of a particle if we look at it as an event that is a bouncing event. In other words, a cavitation that is tearing apart and closing up in the ether, or basically a topological defect that is opening and closing repeatedly in a space. Well, that is an analog to the work of what's his name at MIT, the fellow at MIT who does basically the experiments with the walking droplets. Basically, he's produced an analog of quantum physics that allows us to see that the information coming from elsewhere defines what the particle will be. In other words, the particle, the droplet, only remains separate from the bath by the nature of the information. In other words, the waves that are in the bath itself. The combination of energy and the locations of those waves are what make the particle not only exist, but also to guide its trajectory, which looks completely random, but it is not random. It's defined by its previous locations. And so there is a memory in the bath that is created by the previous bounces of the droplet. And that information is impingent upon an upcoming location for that droplet. In other words, the droplet will be moving, and then there's information, a wave coming in that will alter that droplet. And so there is a non-local aspect to the future of the droplet at
One
each
question.
time with the bath. And so that is how this non-locality
again, we're just about at the top of the hour. So, and Shiva has done, again, amazing work. If it's okay, Mark just popped on to do lab updates. I'd love to go to lab updates, but guys, let's do this. Let's put our hands together one more time. Again, not only for Shiva, but all of you. You guys are doing tremendous presentations, and this is amazing work. I'm just overwhelmed, So thank you so much, guys. If it's okay, let me take everybody out, and I will go first. I'll go to Mark, and then I'll go to Drew for lab updates.
Alrighty.
Okay, sir. Yeah, Mark, you're missing out, man. We've got amazing stuff going on. Well, you have amazing stuff too, so I guess I shouldn't say.
Yeah. I'm sorry I wasn't here the entire presentation. Said I had the kids, but we got a lot going on at the lab. The Alzaphon setup is almost complete. There's a couple more last things to do for it, but the big news this past few weeks is we got this vacuum chamber over here finally set up. It has a couple more things left to do, but for the most part, we're pulling down a hard vacuum U8 ultra high vacuum, -7 torr. Possible we could even make it to -8 torr, but inside this bell jar over here, that's vacuum of outer space. That's where satellites fly. Not right now in particular. It's -4, so that's very close to it, but it'll be there in a couple of minutes. What else do we have going on? We repositioned some of the stuff over here, made the lab have more space. And as I promised you guys, the Mercury Vortex engine will be ready in October. Here it is. It's almost complete. The only thing I'm really waiting on with this is the correct motors. This motor doesn't have enough torque for it. But the basic concept, as you can see from the top, there's going to be magnets all along here. I did not put them on yet because I want everything else to be done first. That's like a 5-minute job to put the magnets on. But if you put the magnets on now and then there's like little scrapings of iron or something, it's very easy to contaminate your work. So I'm going to wait until everything else is done. Basically, this is going to turn around rapidly. Because there is iron over here, the magnetic fields will shoot out into the liquid mercury. And if I can just open this up, actually, instead of opening up, I'll show you one of our other prototypes. So basically, there's a bottom half and a top half of this thing. So this is the pinwheel. We call this the bike wheel. Then there's these iron grommets that fit inside it. This is one of the prototypes. This one was a little bit too large, so it's not going to fit. And this was one of our first attempts at building the base. So basically, you can see the groove around here. Over here, it's very high. Over here, it's low. The width of it, as viewed from this angle, is the same. It's the height that's changing. And if you all know the equation for centrifugal force, the force equals the mass times the radius, and the radius is not changing over here, but the speed is squared. So on this side of the device, we have half the amount of a mass because it's half the height, but we have twice the speed. And since the speed is squared, there's going to be an overall force in this direction. And that is what is expected. That's why we call it our liquid metal engine. We'd have a liquid metal in there rotating around. The rotation is induced by an electric motor from battery, and then it's coupled via the iron and the magnets. These two are going to be connected together. We're going to insert the liquid metal into it, and then there's going to be a plug that goes in there just to keep it sealed up. So this is kind of what it's going to look like when it's almost complete. There's going to be one more part that goes on top of it, which will be a cover. This central axis over here will be sticking out a little bit. There's going to be another bearing just to make everything a little bit more rigid. So overall, the entire device is going to look kind of like this. We're going to make 2 of them. And the reason for that is we can have one turning clockwise, the other turning counterclockwise, sandwich them together, and that will cancel out any torque. So if you just run the motors at similar torque levels, it won't want to wobble left and right too much. And we expect a net force measured in either ounces or pounds of thrust. So like multi-newtons of thrust should be possible with this device theoretically. For those familiar with the Vimanas that are talked about in the Mahabharata, they talk about a Mercury vortex engine as being a key part of the Vimana's thrusting mechanism. This is a proof of concept of that idea. It also goes into the inertial propulsion concepts like we have over here. This is these gyroscope machines. And these have shown, to produce some sort of thrust as well. But those are nearing the engineering limits of what we can do. They produce very small amounts of thrust, but they do produce thrust. So I think this is going to be the better version of that. What else we have going on over here? This is our vacuum pump that we got from Drew Argamara, who's going to be presenting in a moment. And we're doing a little bit of an overhaul on it. I got some more gaskets and stuff, and we're gonna get that up and running. Right now, the vacuum pump that is being used is actually being borrowed from our Alzafon S-band setup. So it's important to put that back into place and have this as its own standalone unit. As far as the S-band Alzafon thing goes, there's just a couple more wires left. Been distracted by our vacuum chamber and some other work, but we're very close to getting it up and running. I hope to have it ready sometime in October. We're still looking at resumes, trying to figure out who would be the right fit for the open positions we have here. So if anyone wants to send one in, mark@falconspace.org, and we'll take a look at that and see if we can work something out with you. Kepco power supply. This was programmed up by Tom Butler. Basically, had to literally custom solder together these wires so that it can run off of our LabVIEW program. And this is going to control the electromagnet. We got the signal generator. Everything is pretty much ready to go. The sample is inside the chamber right now, and we have one conundrum to think about. So the sample's in the chamber, but there is a bit of Kapton tape that was inadvertently placed in the wrong position. You can't really see it so well, but through that looking glass over there, you normally would want to see the sample, but you're not seeing the sample because there's a Kapton, there's a roll of like Kapton film that was positioned incorrectly. In order to correct that, we'd have to take the whole thing apart. So we're debating whether to do that or not. Yep, that's pretty much what we have going on over here at Falcon Space. There's some more stuff. We have our metallurgical microscope. We also we're running an experiment with the arts parts piece, which Jarod may have mentioned, but the data on this is not back yet. This is a block of lead. We have the sample inside with a gamma ray spectrometer, and we're going to be running this for, I think, another 2 weeks, just to see if there's any radiation coming off that sample, even the tiniest amount of radiation. We're talking about radiation levels so low that a banana is like way above it. Just the potassium in the banana is higher than the radiation levels that we're looking at. And this will be able to tell us whether there was any radiation present at the 1947 crash when this piece was retrieved. If there are any radiation profiles there, we'd be able to know, what decay path it's taking and where it came from. So that's something that we're looking into as well.
Mark, that is awesome.
Yeah, that's pretty much it for Falcon Space.
Awesome.
Although one more thing, we are having a meetup for the APEC anniversary in November, and I want to stress this is invite only. Don't just show up here. Don't just buy a ticket and show up. There's very limited seats. We do not have a lot of room. Yeah, if you know, you know.
Yeah. No, I appreciate your mentioning that. So just for the folks in our community, Mark has actually been lecturing me. He's having me come late, right? I'm like a second-class citizen. So he's like, we're going to be working. We're going to be building things. He's like, Ventura, bring the camera at least a week late. He's like, otherwise you'll interrupt. So
very difficult to build anything when you're being asked to take breaks for interviews.
It's okay. I only cried for, a couple of hours, man. That was it.
You might have to change your flight. I'll talk to you about that later.
Oh, you know what? We're getting into that Thanksgiving holiday. I know I'll be changing the flight at least a couple of different times. So, I mean, in the middle, I've been, because I flew all summer, right? And so, I had all sorts of, anytime you get close to a holiday at all, they're like, yeah, your flight's been canceled. It's been delayed. It's been this. It's been that.
No, I'm saying you might have to come a little earlier because we have some surprises that might happen.
Ah, okay. Well, I'll talk to you offline about that. But yeah, so let me do this. Let me go to Drew in sunny Florida, and Mark, if it's okay, I'll take you out for just a moment, and then Drew, can you give us some updates, sir?
Yeah, sure. I had to sanitize the information because, we're still inside of a patent. So I just thought I'd throw up some screenshots of some successes today. The reason I was in and out of the conference all day is because I was running a warp drive testing all day. But the stuff that, the arts parts thing, yeah, we have got to go back and visit that, because I was torn between playing on the warp engine and listening to that, and that almost won. So let me see. Give me a second.
Oh, sorry about that. Yeah, so if you click again in StreamYard, There's a
share
present
screen.
button. Yep.
Entire screen. Share.
And okay. And let me see.
I
There
can't
we go.
tell.
Add to stage. Yep.
Okay.
Perfect.
So, let me think about what this isn't gonna make any sense. Give me a second to throw up my. Let's see. This is what's in the chamber right now. This is what got tested today, and basically this is just an aluminum frame, and this is the force meter right here. Then this is the test article, and basically what it is, it's a quad test article. So there's 4 identical cells, and the testing now is all driven towards activating cell 1, then 2, then 3, then 4, so that basically it's we can show that as you add cells, you increase thrust. That's kind of the gist of the current testing. This is just a real good example of. Hang on a second, I gotta losing my mouse. Okay, so this is system on, turn on. So basically, this is cell number 1. So turn it on, and then this is the voltage coming down until it hits, I think it was 7,500 volts. And basically, it was generating something on the order of around 140 micronewtons. Then turn it off, and then turn it back on, and then turn it off, just basically to see how it works. So that all went fine. And then I believe this is, I don't know what this is. This should be the second one. So this should now be cells 1 and 2 put together. So turn it on, generated something in the zone of around 300-ish, 290, something like that. Turn it off, turn it back on, turn it off, Then this is 1, 2, and 3 put together. So basically turn it on, and it generated, this was, let's see, 1, 2, and 3. So this is somewhere in the zone of around about 300 again. Turns out my number 3 plate is either not working or dead. I haven't figured out which. But either way, it showed that it wasn't adding to the group happy factor. So that was interesting. I have a way of checking to see if I have a dead cell. Kind of like it's like having a dead cell in your battery. They all still work. Just if you have a dead cell, since it's all in parallel, that one thing isn't making any thrust. Okay, so this is 1, 2, 3, and 4. So starting at wherever it started at, and then kind of just playing around. I kind of let me think. Let me find where I was at. So yeah, right about here. So it went to about 900 or so. So 1, 2, 3, and 4 was doing about 900, 960 micronewtons. And then I just decided to go into play mode and have some fun, and just kind of screwed around with the system for the next couple of hours. So basically, I was just trying different things, 1 and 2, 1 and 3, 1 and 4, 2 and 4, just messing around different things. That's how I found out my number 3 cell was dead, which is always exciting. And then towards the end of the day, I started getting hungry and had to go get some food, so I shut her down. But she was making 1.76, I think was the end. 176 millinewtons. So it's 1.76 millinewtons, and that was at full power. So that's basically on, and then turned off because this system decided to start charging up. So as it is right now, it's hovering at around 1.4 millinewtons sustained. And over the course of this last week, I forgot to shut off my recorder. So I went 72 hours recording the thrust in the chamber, and it maintained something like 1.3 millinewtons of thrust in the off position, fully grounded. So all the plates in the system were grounded, and it maintained I don't know, like 1.3 millinewtons of thrust for 72 hours. Then I went and said, oh crap, I forgot to left the thing on. So it was kind of fun. It made a like a 15 gig file, something stupid, but it was fun to see it. So that's pretty much what I have been doing. I don't think I have anything else. Again, this is my chamber. It's about 3 times the size of the glass thing that Mark showed you, and I can get down to.
Drew, sorry about that. Let me put that back up. I took.
Yeah, I can get down to 10 to the minus. I can get down to 6 times 10 to the minus 6. Did not know this in about 3.5 hours now, because all of my plastic has effectively dried out.
Well,
So,
and let me thank you for working with Jim Woodward and Curtis also with that pump. I know they're a little bit slow, and then you've had some.
Oh yeah, they're just gonna come get the thing. I haven't heard from them in a week or two.
Okay, I will follow up. They're juggling stuff on their end as well. That's like
Sure.
this year for at APEC, the vacuum chambers are multiplying like rabbits, right? Like I heard that David Chester has a vacuum chamber, and in fact, let me bring everybody on stage. I guess we just go to open discussion now. I think
I have a glass bell jar, which is not yet a vacuum chamber.
Do you need a big pump? Because if you do, I know a guy.
Yeah, I've got one more of the 3760s or whatever the hell that thing is.
Is that a diffusion pump?
No, but I have an 8-inch diffusion pump if you want that too.
No, I was about to buy a roughing pump, and then Mark has a turbo pump that he was going to send to me.
See, yeah, it's like
if at all you can avoid diffusion pumps, you want to do that.
Yeah.
You do not want to go through the potential disaster that a diffusion pump is, because if you don't know, diffusion pumps have been known to explode.
Yeah, I'm not trying to mess with that.
Yeah, you don't want to do anything like that. You have to put in the I don't know, it's $1,000 a quart anymore. It used to be $1,000 a quart silicone oil. I think it's now down around $250 a quart. But you have to use the super expensive diffusion oil, and all that does is if you have a bad day, it just keeps you from having a very, very bad day. It still doesn't keep anything from getting ruined. It just keeps it from going on fire. Yeah.
Yeah,
diffusion pumps,
turbo pumps.
bad. Yeah,
I feel left out. I feel left out. I'm like the only person.
Super negative, bad, expensive, but they're worth it. When you have a bad day, it's worth having a turbo pump burn up, and you just cry about how much it costs. Well, Tim, we can rig you up a little tiny vacuum chamber. I mean, you can get a little tiny bell box, or stick a little $30 pump on it. And you could explode marshmallows all day long.
Yeah, Tim, you want Drew's diffusion pump?
Oh, I don't know.
Yeah, in fact, I have a 4-inch diffusion pump stack, the entire stack, from the chiller to the valve, the gate valve, a 4-inch gate valve, down to the diff pump, the diffusion pump, and also a monster roughing pump that can go with it. You just gotta pay the shipping to get all that mess to your house.
Right now, I'm most excited just to see what Mark will do with the bell jar, because he can do Beefield Brown stuff in that really easily. And so he's already got kind of, in fact, what he thought about, we were talking the other day, and I said, what if you were able to take a couple of Drew's thrusters and create a balanced rotator, right? Like the old TT Brown rotators. And put if it fit in that bell jar, that would be interesting. You might be able to get that up to high speed.
Talk to Mark about that. I think his moment arm is too short. We built a 24-inch rotator, and it was a nightmare. There's a lot of problems with coming that close to the edge wall of a chamber. A lot of problems.
Yeah, this is an interesting year. So much.
I have 2 things for Drew. So earlier today, Hongdu was talking about how there was $1 million prize if you can show like 20 milligrams of sustained
I
thrust.
heard that.
So if you want that cool new equipment that'll let you do some fancy stuff, that's one way you might think about doing it.
Yeah. Had this been a
that was-
couple
that
of
was-
weeks ago, I would have really jumped on that, but lots changed in the last 2 weeks here.
So
I hope that's
did you say
good.
$20 million prize, or is that the $50,000?
The one. It's the $1
1
million
million euros.
prize.
Oh,
Or 1 million
okay,
euro, yeah.
okay.
So that was
the one I kept. Sorry, go for it.
So that was the one thing for you, Drew. The other thing that I wanted to run by you. So as I was going through that arts parts stuff, I couldn't help but think of your stuff the whole time, which is basically T.T. Brown like esque type stuff, right? So as I was looking at those little zinc lead like microspheres that are all over the place, and how some of them seem to be overdriven and ruptured, while others weren't, I couldn't help but wonder if maybe those might be kind of like miniaturized versions of your plates, like maybe these layered zinc lead things sitting on top of magnesium bismuth substrate might somehow be similar in function to what you're doing, except because they're a ton of them and they're round, they have a lot of surface area, and they have some weird arrangements. You might be like focusing fields somehow. Just thought I'd drop that by you.
Yeah, I was listening to that very carefully. I like the idea of them. I'm sure the aliens are way smarter than us, but we're discovering, my team is discovering that charge is a very big thing going on here, and more charge equals more thrust, and it don't really matter how it gets there. If you need it, you need it. And if those little tiny things were some kind of tiny charge reservoirs that could be activated in some way, when you want to wake something up, you just throw a switch and kind of like boop, dump all that charge into the system, or have a lot of charge in the system and then boop, pack it away in those little coolers or something, kind of like little charge coolers or something. I don't know. It's a big rabbit hole that I didn't got the time to go down. But damn, I wish you'd hurry up and figure it out and tell me how it works.
Yeah, and the quasi-crystal thing that's really intriguing. And Jarod had kind of pointed that out too, because from my understanding, I could be wrong, but quasi-crystals are new enough and have been fairly obscure, and so the work that was done on Art's parts and the thought that went into it probably completely bypassed that path, right? So it could just be like sitting under everybody's noses just because it wasn't known before.
And the idea that the special geometries that you get, the fractal scaling nature that you get with quasi-crystals, and how these special charge spheres, how they might have that arrangement, it makes me wonder if maybe, especially for like Drew's stuff, if there were certain geometries that would like orders of magnitude increase the effect by like stacking the charge fields, static fields, like on top of each other like that.
Well, yeah, I'm convinced that, and I don't know how we do it, but I'm convinced that we're throwing out like a sail in the vacuum. We're just throwing out a sail, and all of the interactions are hitting it, and they're hitting it, and they're hitting it, and we're stealing some of that momentum. That's the only thing I can think of, is that, we're stealing it. Well, if you had a sail here and a sail here and a here, and you have hundreds of them per volume, then you don't need a whole lot of universe to interact with each one of them individual sails. So you could stack them puppies right on top of each other. In your case, the material, that material went up by microns or something. So that might be what's going on. And, it would be awesome if you could figure out some clever way to, I don't know, convert free charge into something that you could use. Because, there's like a million times more free charge than there is bound charge. If you could figure out some clever way to convert free charge into bound charge and then utilize it. I mean, if you figure that one out, let me know, because I'd love to know how to do that. But man, it's got to be, is it? Can you get more than a grain of sand of that stuff? I mean, is there a bigger piece of it?
We're currently chasing down a couple different options to get a couple different pieces. We'll see how that goes. But going back to your sail analogy, I really like that, because if you think of like stacked sails, we have one really big sail and then another smaller one and another smaller one. If you wanted to like maximize those, I would imagine you'd have like big holes in the big sail and then smaller holes in the middle sail and then, no holes in the last sail kind of thing. And so the sizes of these microspheres, how that they're not uniform in size. Like you have all these different sizes, right? When you look at it under the colors, you see these different colors, right? So I wonder, similarly to your analogy of like catching the stream of charge, through the charge of space, if maybe that's kind of what these quasi-crystal lattices might be doing, is you have the large ones that are capturing, larger waves. You have next smaller ones catching small ones, and perhaps they're charging them up with these terahertz free electron lasers, and they might even have special modulations on these lasers so that you are able to capture these different wavelengths, right? So instead of playing a note with your laser, you're playing a chord with your laser, and you're catching these different discrete sized microspheres.
Is there any possibility? I mean, I don't know exactly how a laser. I know how they work. I just don't know how you build one that's the size of an atom. But is there any possibility them little crystals are the exciters? That maybe they're a converter from like RF in some way, some kind of RF energy, and then hey Curtis, and then maybe they turn into the exciters that do all the magic. Is there any possibility we just got this backwards?
So I've looked into this. Like, is it possible that when you charge it up, is it like glow in the dark material where it holds on to some of that charge and it's emitting that charge slowly over time, right? And that charge gets emitted from a bigger one and captured by a smaller one type thing, or vice versa. I've kind of looked into that angle. I haven't come to a conclusion one way or another. But this idea of exciting it with RF, right, with very, very high frequency, specific wavelength EM, charging it that way, and then it holding onto that charge in order to produce thrust, similarly to how glow-in-the-dark material holds onto that charge to produce light. I can't help but just wonder.
Wait a minute. I'm just looking at our, when Curtis came on, like, here, hold on. Okay, share screen. Does this look familiar? Yes. We look like that's what it is. They copied the Brady Bunch layout. Okay. I just had to share that real quick. Had to interject a little bit of humor. Okay. It was when Curtis came on and it went into that 9-grid layout, and I was like, I've seen this before.
Well, let's hear some mock effect stuff.
Yeah, Curtis, you have an update for us, sir?
Curtis,
you're muted.
Yes, I could probably best to share my screen so I can play some videos for you guys.
Yeah. Okay. Let me take everybody out for just a moment, and then I'll bring them back in, and we'll go back into open discussion after that.
Okay.
Okay. And sorry. Okay.
All right. So okay. So basically we have ordered 4 stacks from a vendor that actually makes PZC's material and PZC stacks. We're looking, as I mentioned before, we're looking for a new a material because we're having trouble getting the material we have been using. And so we're going to be testing that new material to see if we get comparable results from similar geometries. And once that's done, we're going to be having them make 4 more stacks with the existing material that we have on hand. We've sent to them 2mm stacks, basically 2mm discs like we've been using. But also we're going to have them build a stack with 1mm discs, which we're hoping will 10x the force that they're measuring. So that's in progress. That's been ordered. That's in the works, which is good progress, because one of the things about these stacks is that they're hand built individually, and so quality control can vary there. So everything else is pretty much the same. We have been having discussions about the future funding, how we would go about that. Likely, it would be a crowdfunding type of thing, and we're also still interested in going to the NSF. So the next slide here. Let's see here. Okay, there we go. Advance the slide. So in terms of future testing, I just wanted to kind of point out, on the right there, I didn't take the other steps, but basically, the steps that we're going for the long term, it's going to be a stepped approach, going up the TRL scale. So basically, right now we're still working with external power. We want to get that replicated. Later on down the line in the lab, we want to have the power source included with the motion, so that it's moving together. And then the next step after that would be like something like a floating device, including the power source outside of the lab, likely still in vacuum, but show that it can like independently work and move. And then we want to do the same kind of experiment in high altitude, and show that can create some reliable, repeatable accelerations. And then the last step in terms of the getting up the TRL level is doing this in space. So that's kind of the overarching goals. And on the right, what each step, for some reason 4 and 5 didn't get included there, but I'll skip ahead. So we are improving the brass reaction mass. And I mean the supports in terms of the number of bearings. We're going to be including currently this device is being retrofitted with 2 more bearings on the aluminum, the bottom aluminum ears. So right now you can see that there is no bearing at the bottom there. That's going to be included or added to this device so that we could test something with 6 supports. Ideally, the supports would be further apart, but Jim decided to do this with one further apart here at the top and then these 2 in the middle. So I'm not really sure what will happen with that. It's going to be an experimental test. There's practical reasons why, because it's very difficult to pop these out and put them back in. So we're going step by step here, which is okay. But ultimately, we want to have as far apart as possible for the ears to minimize, whatever issues may be coming up from binding or what have you. Next, this is a tracker plot of a recent run that was done on the 19th of September. You can see the file down below at the picture. And you can see that basically one thing to note here is that it starts out just above -12. And then in terms of like the blue trace is the center of mass. And you see that kind of settles like a little bit lower. So what happens oftentimes with this thing is that the center of mass or of the entire thing shifts after the first kind of wiggles after the first run. So what I've been doing is analyzing it and showing that like basically after the first run, all these others are pretty much on the same center of mass shift. And we can tell because the green trace and the red trace are approximately in the same area after the power's, kind of after we've come out of resonance. So all that being said, we are showing consistent forces. This is within the resonant frequency. It's a 4-second sweep. And you can see that, we're able to repeatedly get a push every single time. So this is really good that we're able to do that. And this is with a device, not the one I showed pictured before, but one with the traditional devices where the bearings are closer in. And in this case, they are the sleeve bearings. They're not the Biggers type, which Biggers type, we get even better results so far. So, and this is again the August 1st. I kept this in here for us to show, what we got back then and kind of what we're striving to get and repeat. So this is what we had before. And what I'd like to do is show some videos. I guess if Tim, we could, if I could share my screen.
Yeah, go for it.
Share screen. Okay.
And then I will have to put it up, I think. But that's easy. That's just a single click.
Okay. Let's see. Window, entire screen.
Yeah, and Curtis, I don't know if you caught it earlier, but we are starting our broadcast in full 1080. Okay.
Oh, really? That's great.
That's your screen. Okay, perfect.
Yeah. So let me get the video run here up there. Okay. And so this is that run of September 19th. And so these are 4-second sweeps that happen. So you can see consistent pushes to the right. And you can see that jerky motion, that's kind of a stick slip, but the stick slip really doesn't have any effect of the center of mass. That's actually in the calculation. So that's pretty good. Now next, what I'd like to do is what I'd like to do next is actually share a couple of, I'd like to go back over and talk about physics next. So one of the things I, have been talking about quite a bit is looking at what's fundamental, trying to decide, kind of keeping an open mind about what we know and don't know about how things work in the universe in physics, and trying to figure out, okay, is quantum mechanics, fundamental in terms of like working in all domains at all energies? Is it something that is always there? It does. It is a very, we do know that for light, for certain things in the energies that the domains that we do see certain things that are there. But the question is it really fundamental to everything in the universe, including space, whatever you want to call space-time, or inertia and everything else, right? So we know matter is waves, so we know certain things. But the question of quantum mechanics, I wanted to bring up because of a couple of things. So let me share this video. This is going to be a couple of short clips I want to share with you guys. This is a video that just came out today, and it's of course clickbait, right? So in terms of the title, so anyway, so in context, what I think he means is it's not fundamental, right, to all domains. So but I want to play this one too. This is a couple minutes. This is a long talk by Carver Mead. This particular video is in fact a short part of that talk. But these are the fellows that actually gave us the kind of computing revolution, right? They figured out Moore's law was true, and we were able to spend money on shrinking device sizes and have the technologies that we have today. So it's interesting hearing from these guys that were doing this stuff and what they think of quantum mechanics.
Okay. So Curtis, the volume is not playing. You might have to reshare, and there should be a checkbox for share audio. I thought that when you played the first one. I didn't hear anything, but I thought maybe I just missed it.
Okay, let's see here. Entire screen.
Yeah, and there should.
You share audio.
Check. Yep.
Share a tab. Okay, it says share a tab instead to share audio.
Yeah.
Okay.
Okay.
So that's what it wants to give me 1 second. Let me add a tab and I'll put these on here. So you guys weren't getting volume, right?
Yeah, on that first one. And again,
Okay.
I thought maybe I missed it or it was soft.
No,
or
no, no.
something.
That's great. Thank you for telling me. I'll put it in. I'll put it in there so we can. There's going to be ads. Of course. Let me skip those real quick, and then we'll. Okay, we can get to that one. Give me 1 second here. Skip.
Yeah, well, and thank you for giving us all these updates.
And
I mean, this has been an absolutely tremendous year. You guys are all just everybody involved with this conference is just kicking serious butt. So it is so exciting.
Let's see here. Share screen. Okay, there we go. So now we got this tab, right? Now, if I do
There
a
we
full
go.
size, you can still see it, right?
Yeah.
Okay, great. Oh, I have it muted.
As a whole is wrong. It's not Einstein was wrong. Quantum mechanics is wrong.
So that's that clip, and let me play Carver Mead's clip, because that's longer, and it's very interesting to hear. And like I said, I mean, this is about figuring out, okay, what's fundamental here. And,
The following program is brought.
Well, in the general area of computation and communication, Amnon mentioned it briefly today. People are just now starting to do radio techniques at optical frequencies. And that's really exciting. This whole idea of statistics and quantum mechanics is being shown to be as brain dead as it always was. And that's just wonderful. I read a paper the other day by Ted Hench, who's a good friend of the family here, and they have an optical fiber length between two of their sites, and the coherence length of the photons in that fiber length is 10 to the 8th meters. So much for statistics. Yeah. The role statistics plays in quantum systems is what we engineers used to call noise. So that's playing out, and we're getting finally a sensible view of what quantum systems are, not some statistical garbage but they're nice systems that have the properties of waves that we engineers understand. We know how to work with those.
Okay, I'll stop sharing there with that, and go back to the slides. Okay, so anyway, so yeah, I think Eric Lerner's presentation that just I'm sorry, Eric Ryder's presentation that was just done. It would be great to have him do a second one if he's interested. I'd encourage that. I hope he does. And that's the thing with this, like, as we do these things, what is really going on there? That's the question, right? We were talking about, well, the discussion when I popped in was like, what's really going on? How do we make this thing really work? And what is happening, right? So how does inertia, how does it mass, how does it all interact, and what are we doing? So really, I'm really excited about this. And one of the things is I do want to keep collaborating with you guys. I know I've been really rather busy, and some of you guys have reached out. I haven't been able to engage, but I am interested in engaging. And I do think that, we're living in a time, like I mentioned before, the other stuff I have on these slides, like the parity violation of the large scale structure of the universe, that being shown as something that's there, 7 sigma detection. That's what got me reinterested in Sachs's work and work like that, like Penrose's work, pushing GR forward. And all these things that are coming out about quantum mechanics in terms of the limitation of what domains it actually applies in, kind of basically gives me hope that we can actually start making progress, because we can look at experiments, and from those experiments have informed decisions about what we're taking as fundamental. In addition, there's some theory work that I was not aware of that I recently discovered that push forward some of the ideas from Sachs and those kind of things. The issue is, again, what's fundamental, right? Is the Big Bang fundamental, or can we only take the redshift, right, as an observable that we can depend on? So really the question here is, what can we know for sure? Our experimental results, they tell us, what happens in there, and build off from, right? If we go too far and we take things that are not necessarily fundamental, they're extrapolations, that could lead us astray. So one of the things I've been asking my particle physicist friends is, if you have a theory and you calculate the mass of a particle that's transient, right? Let's say it's not a stable particle. What do we need to calculate? Do we need to calculate the mass at the energies it was measured at, or do we need to calculate the rest mass that's assumed, right? Is there a difference? So that's one of the things I'm thinking about and trying to decide, okay, where do we need to draw the line with that, for example? So anyway, so that's my presentation. That's my update.
Curtis, thank you, man. Thank you so much. Okay, so let me bring everybody back in here. So yeah, again, guys, back to open discussion. I think, I forgot Mr. Yates. I feel like I'm forgetting somebody else too. Where'd our Brady Bunch layout go? Oh, well. Okay.
Yeah, you're stuck on that, Tim.
I know.
Can I quickly say something about the Tim, you're categorizing my view as that Einstein is wrong. I just want to clarify that, understanding that there's this subtle differentiation where Einstein was focused on a methodology and a superior method of calculating, because of its ease of use, is truly a superior method of calculating for most things. But then a statement about reality is different from a method of calculating. They're two different things. And so Einstein found a faster way to get at things that would help us predict reality. Whereas the view that there is something underlying in creating those structures that he's categorized and uses a certain methodology to address, there's a separation between those things. And so we can take, in other words, the Einstein's view, which is using Minkowski spacetime, would only be just, it's a methodology instead of a statement about reality. And what I'm saying is that there is a statement about reality where there are mechanics underneath that you can have in addition to what Einstein was doing, basically. So in other words, that's how I'm trying to say that Einstein's not wrong. It's just, it's a limited view based upon a methodology.
What I was thinking was that one of the things that makes our community really unique, I mean, really unique, not just in science, but like in culture in general these days, is that we have like a wide diversity of viewpoints, and we have a lot of folks that disagree with each other, but like they're still able to communicate and like discuss things and have discourse in a friendly way, right? And that makes us, I mean, like I'm sure you're on a lot of these email lists too, right? Where you've got physicists like just beating each other to a pulp, and I'm not even going to get into politics, right? But I mean, it's like that's society these days. It's just like fight, you know. And it's cool that we're able to kind of like give different perspectives and discuss them without like having these freakouts that seem like they're happening more and more in society these days.
Yeah. By the way, Shiva, I did. Recently, I was watching some more of those, like about 8 years ago when they had the 100-year anniversary of relativity. There was a lot of presentations given at that time, and some of them do cover really accurately what Einstein was really trying to do, what he really thought of certain things in terms of taking from what because they have a lot of things he wrote that weren't necessarily published, and it's really interesting that what you say, because what he was trying to do was basically try to think a theory using like meta principles, I guess we would call it nowadays, right? Things like the Noether theorem, stuff like that. But the thing about Einstein's program is that he was limited in terms of like the symmetries of nature that he understood at the time. And so that's one of the points that both Penrose is taking advantage of, and also Sachs took advantage of others, right? They're looking and say, okay, well, you know, he had until 1955, 1956, we discovered parity symmetry violation. And so that's really, to me, that's really a question. The question
did
is going to be.
Did you catch my video earlier, by the way?
No.
I think you really like it.
Yeah,
but yeah, you know, to going back to what Tim was saying, basically, you know, I think that both Curtis and I representing two parts of saying change, a subtle shift to both quantum mechanics and to relativity. In other words, I'm saying there's a subtle shift to relativity that leads to a subtle shift in quantum mechanics. And so that most of what we already have is actually true, which is why it's so hard to change the paradigm, because it's such a small little shifting of things. And so, yeah, it's interesting, you know, to say it's not wrong. It's just
right.
expansion.
Yeah.
So
there's
I just
general
dropped
saying it's wrong, but it's.
I just dropped the video link back in. And, you know, Curtis, if you have video links too, let me know and I'll drop those into chat as well.
Okay. Yeah, no, I'm not good at the this is the most I do in terms of I'm pretty busy lately, especially.
Yeah.
But at least I'm saying
well,
something.
Don't forget.
I've been keeping quiet for decades, so at least I'm talking to people now.
No, that's awesome. Don't forget that vacuum pump from Drew. He's down at the bottom of the screen. He's ready to send it.
Yes.
Yeah.
Yeah.
I'll be getting that arranged for
next week.
Yeah, there's a second one up for grabs and 2 diff pumps if anybody wants them. Actually, 3 diff pumps. I'm just trying to get rid of all the old stuff that I'm never going to use again.
Sure.
But you know, it's perfectly serviceable if anybody wants some older high vacuum equipment.
Yeah. And by the way, Shiva. So in terms of, I don't know if did you get a chance to look at Ryder's research, his experiment? I think he was on last time.
I don't think I saw Ryder's. I was going to ask you about the Dayton Miller paper if you had a chance to see it. I haven't had to look at Ryder's.
Yeah, no, I haven't. I haven't. Like I said, I've been really swamped. But yeah, please take a look at that. I'm kind of curious. Both you and David Chester, I see you there, and the rest of you guys. I'm really curious what you guys think of that, because I keep pointing back to the physics. Like, it's like we got to understand what's fundamental, because as we're trying to figure these things out, it may be that, you know, there are quantum effects that they're taking advantage of in terms of like creating resonances in matter and stuff like that. But some of it may be reaching beyond that domain. And where is that limit, right?
Is that the same writer who wrote a textbook on quantum field theory, or is this a different individual?
No, he's been doing experiments for 20 years. He was on the last APEC, and he shows very compelling experimental evidence that there are the quantum doesn't work in the high energy domain of certain experiments. So yeah, it's interesting. So
I also wanted to ask about.
Curtis, I don't want to alarm you, but there's a little person behind you.
Yeah, that's one of my daughters. I'm home alone with the wife, so that's.
I just want to make sure, like, somebody wasn't sneaking in and stealing your work.
No, it's one of my girls. So, yeah, my wife's out this weekend.
You're
so
down there in SoCal.
Yeah,
you still have nice weather. It's getting cold.
Oh,
it's
yeah.
starting to get cold up here. It's starting to. Yeah. We're getting into fall. So
it's called the sunshine tax. Yep.
I looked at Drew's. Drew's 82 and like 85% humidity down there in Orlando. So.
Oh yeah, we have good weather here today. It's 95% humidity in the shop.
Hey Curtis, I was gonna try to address what you're saying about the difference between rest mass. I don't know if this answers your question, but I mean, I think it's pragmatic to distinguish between rest mass and just like energy. Like you could say equals mc squared, or you could say like equals gamma mc squared. And then that gamma factor is taking into account the kinetic energy. So even if you have a particle in motion that has kinetic energy that's adding to the rest mass, I think it's still convenient to refer to the fact that that particle in motion has like a rest mass value that's the same. You know, it's the value of the mass in the rest frame. I don't know if that addresses what you're getting at, but I figured I'd see.
No, you could take a, well, in terms of the quantum stuff, or Jim's. And one thing I want to make clear, I mean, with Jim, what I like about it is that there's an experiment here that we can progress with and show that there's something there, right? In physics, experiment is prime, right? So we can argue till we're blue in the face, but knowing what nature is really doing, that's what we care about. And,
well, that's, I mean, with Woodward, what he's doing is he's pumping the system with electromagnetic energy and then referring to it as mass, which, it depends how you're defining what mass is. Some people would, it's kind of a semantical thing. At the end of the day, energy and general relativity, at least, is what sources gravity, which includes mass. So that's why it's kind of okay to, word it however you want. But I think it's at least worthwhile to understand those distinctions. But
it's
mean,
funny how the source side of the GR equation is called the stress energy tensor, right? So
stress, and it has stress, energy, momentum, and exactly.
Yep.
That's sourcing.
Yep. That's the source.
Curvature or the metric.
Yeah, that's right. So, that's where you want to go with that.
Rotation in a constant continuum. So there's the close way in which these things can be related is something I do eventually want to have a discussion about. I'm just not prepared to talk on it fully. That's what a lot of those slides I have today are about.
And the Lorentz group is just a generalization of rotations to space-time. And if you gauge the Lorentz group, the field strength for that, the Yang-Mills field strength of that is essentially the curvature tensor. So, you can relate rotation to curvature in that way, or translational holonomy. Buzzwords that Drew knows and loves, I know.
There's some comments in the chat here. So, I think a good paper to follow up with what I've shown here. I didn't show it explicitly, but Roy Kerr, he just released a paper in December 2023 about basically kind of shooting down the singularity thing and actually calculating his metric and the internal metric and showing what actually happened, what actually could be happening in rotating black holes. So,
well, it's worth pointing out that spin density sources torsion a little bit, and so some studies of very fastly rotating black holes use torsion, or people will not use torsion but use effects that can be derived from torsion, and that does change the singularity structure. So I find it a little unfortunate that Kerr just kind of doesn't seem to be aware of that stuff. So,
well, no, if you look at, did you see that paper, David?
Yeah. I mean, he just wrote down some words. It was like, okay, that's your opinions. That's cool.
Yeah. There's a basically it becomes I guess you could call it a ring singularity. It's a little, basically the point was that it's more complex than just.
Well, I mean, that's been discussed for decades though. Like, I don't and honestly, Penrose used to discuss torsion and forgot about it. Like, he wrote about it in the 80s and just literally doesn't remember they worked on it.
Yeah, probably not. He's moved on. So, and in there though, one of the things that's in there that's really interesting is that whole metric, that whole frame dragging thing is apparent in terms of like outside. It's throughout, and most gravitational sources that are big, like the sun, they're all rotating, right? So there is a little bit of that frame dragging from all these sources going on all over the place. So there's a lot of these nonlinear, basically I would call them nonlinear effects, just as a general term, but I don't know.
Okay, so here's a fun little debate So Sky is saying that Hawking radiation isn't real. Shiva's saying that fluids are really important. So what about those experiments that were claiming to simulate Hawking radiation through fluid dynamics analogs?
Are you talking about where? Let's see. I know there's they've created sonic black holes in fluids as a method of simulating black holes in fluid dynamics. But was that what you're talking about, where there was some sort of Hawking radiation from those sonic black
So
holes?
people are claiming that these fluid dynamics experiments are kind of like quantum evidence that maybe Hawking radiation is onto something, at least in this mathematical analog that they're making with black holes.
I mean,
I don't.
sense to me. I mean,
I don't know what you think of these experiments, Shiva, but I look at them as basically analog computations, right? So the question is, when you do any kind of computation, you're making a lot of assumptions, but your computation is a computation, right? The results of that all
right,
based.
And that's the problem. Is we haven't gotten past linear. In other words, we touched on analog computation for a short period of time, and then because of its lack of precision, because of there's always a little bit of wiggle room, we had we kind of abandoned it. It was extremely valuable. It was how we did our first our calculations of how to shoot bombs and things like that were through mechanical devices, and we find that like I mentioned earlier, the slime molds solving the traveling salesman problem. There are all of these different simultaneous calculation problems that that nature is constantly doing. In other words, it's a different sort of different form of computation. In other words, analog computation is not at all like linear computation, which has this we conceive of linear determinism in a certain way, and that's where we run into problems. Even language itself has this linearity to it, and so that's that there's a problem we keep running into because we don't. Whenever we're delivering language, even it's not in the way that reality works. There's many simultaneous things that are all interdependent, and that interdependency is just not reflected in our typical mathematical language or our spoken language. They are a linear way of delivering information and computing information.
Yeah.
Was it obvious, by the way, to those who saw the my presentation, was the way in which the Doppler? I know I've made it pretty dense and went through it quickly. That video was actually meant to be paused and some of the diagrams and things like that looked at. But I was hoping that it still got across the way in which there are these automatic compensatory illusions that reality creates, and especially pointing out the way in which the Doppler effect creates this perfect, illusion that hides motion is, I think, very demonstrative in a way that can help one understand. So long as one understands what I was saying, and I was wondering how you guys felt about the first pass of just listening to it once, if you understood how the illusion actually occurs with the Doppler effect. Drew seems amused by something. So.
Guys, I need milk. I need milk and cookies and aspirin so you can just listen.
Yeah,
listen to y'all.
I didn't see your presentation, but I will say that I saw you sent me those papers on the the Doppler effect or the measurement of speed of light and trying to find ether. All that being said, it's a matter of, like, the way I see it, the fact that we are able to have the Breit-Wheeler process and matter annihilation. Like, we do need to think about, like, how does that really happen, right? That's a question. I mean, is it really energy turning into light? I mean, mass.
You can look at it either way. I mean, renormalization allows you to look at electron-positron pairs as electron-positron pairs or nonlinear photons. So you can choose different interpretations.
Yeah, and from a fluid mechanics perspective, if you think of a particle as a rotation that is leading to cavitation, and so the energy is just stored there as kinetic energy of the medium, then when that that mass disperses, in other words, the kinetic energy of rotation disperses, it can turn into waves, which actually, change into a different, form, basically. In other words, so the energy itself can actually, leave that center of rotation. So it's, there is a way in which you can conceive of it in a mechanical fashion.
Yeah. So what's really going on there? I mean, the theory we have right now, GR, is basically a unification of gravity and inertia. That's what it is, right? So
is it?
Yeah. That's what
What if
that's
there
what
is
the
no
intention
such thing
was.
as gravity, guys?
Yeah.
What if this whole gravity thing is nonsense? What if it's all about charge, which is what I want to talk about?
I was
So
going to
I
ask
heard
you,
something
do
very-
you think that we can push off the quantum vacuum for propulsion applications?
Yes. Yes. I want to talk about charge. Every
So-
time the word gravity shows up, I want to talk about charge.
Yeah.
Go
So
ahead, start talking, because I have no idea how to talk about that.
So David, so basically, the question is I have for you is, based on what I said earlier, is it acceptable? Do you think it's still acceptable to use quantum, basically GR, when we know that the symmetries it's built on isn't the symmetries of that we know now that are correct in the universe, right? So what do we do about
You
that?
know that?
Do we have to
How do
change
you know
it?
that? I mean, there's like a lot of tests of Lorentz symmetry violation. I mean, there's a lot of opinions on that it's not violated. What evidence?
Parity symmetry, time symmetry. Those are the two, right? We have PCT is the symmetry that we have.
I mean,
now,
yeah, but there's
right?
CPT symmetry, and that's fine with Lorentz symmetry. That's totally fine. Like nobody is worried because of parity symmetry. I mean, it's more of a it comes up more in quantum field theory, but I don't see.
Hold on a second. That it comes up in look, GR is supposed to be a unification, right? That's what he was trying to do. And so if you're going to do a unification and you don't have all the symmetries, it's not a unification anymore.
Oh, well, yeah. I mean, clearly general relativity is not a theory of everything. I mean, that's obvious,
Okay,
but I mean,
thank you.
Yeah, but I mean, like Einstein was never claiming it was. I mean, he was trying after GR to unify electromagnetism with GR.
So when he made GR, right, electromagnetism didn't come out of it, but he would have liked it to, obviously.
He got half of Maxwell's equations to come out of a non-symmetric metric in 1925, and then really kind of what happened is the Dirac spinner was invented, and Einstein also invented the frame field, which is very useful for studying Dirac spinners in curved space-time. But since the mathematics was so difficult and new at that time, his unification physics got worse over time. So by 1929, he lost all of Maxwell's equations instead of half of it, and then ended up with this theory that was merely a theory of gravity, and that's like Einstein's failed teleparallelism. And then he started going through a bunch of complicated ideas for a decade, and then eventually kind of came back to some stuff around the 1940s that was kind of revisiting the 1920s stuff. But really, I mean, in terms of unification, the big thing is that right around the time that Einstein died is when QCD and the weak force, some of that, CP violation stuff. Like, I always ask the question, what would have Einstein done if he was alive to see the development of the standard model? I think that's a really good way to think about it.
And that's exactly the same thing I'm asking. So in 1956 is when we had that parity symmetry experiment happened, right? So that was it. He died in 55. So what would he have done differently? And that's, I think
fiber bundles is really promising. I mean, understanding like the Wu Yang dictionary. I mean, Eric Weinstein talks about this. Not that like he's done tons of people discuss as well that are like acclaimed physicists, but like understanding gauge gravity and understanding how like an affine connection is like a Yang-Mills gauge field is really deep, because it there's tons of work in the 1970s about how to formulate unified field theories. So, I mean, that's one way to look at it from kind of a conventional viewpoint. But really, like the ultimate problem with unification was more just quantum gravity. Like the problem is that people ran into infinity problems with
So
perturbative quantum gravity, which has nothing to do with unification, and that dilemma stopped people from really trying to unify gravity further. And then you have grand unified theories where they're like, let's just forget about gravity because of the infinity problems. But like mathematically, there's tons of mathematics that allows for symmetry groups that I've done work on how to get like the conformal group, which contains the lens group, with like SU5 gut, which has a standard model. So like there's tons of mathematics out there. String theory has their own view on stuff. They've studied a lot of the similar overlapping mathematics and then thrown a bunch of extra stuff. So there's tons of math to get these unified theories, but still the problem is like, how do you get UV finite quantum gravity in that framework?
So hold on. So you're going way further and way faster than I would go, because first of all, the question is what Einstein would have done. Second, would he have included the new symmetries? Probably, right? Because if you don't, you don't get everything. But the other thing is, we know he wasn't treating quantum mechanics as fundamental, right? He never did. And so that's one of the other things. Like if we look at, okay, what would he have done? Those are the things we know he would have done. And that's the road Sachs went down, and some others went down a similar road, like you point out. And it kind of, people just try to do quantum standard model. Now the question is going to be, is a standard model in quantum something that emerges? And what's interesting is the recent work I found, from Marcus Cohen, that basically he kind of took the stuff that Sachs did some more sophisticated, basically topological calculations, and he is able to get more or less the standard model using a kind of a topological argument. But that being said, his values for the rest masses are slightly off for some of them, and they're pretty like 25% off for certain class particle, and that's problematic. But again, at the same time, he's treating quantum as fundamental and making certain assumptions about the Big Bang and other things in his calculations. So I don't really know if that's already been worked out, because I got to go redo everything, and that's going to take time. But the question is, like, what do we do now, knowing what we know, and why is this whole thing of quantum gravity may be a misnomer, right? So following Einstein's program may or may not get us further. But what I find interesting is that Einstein's program, if you do that with the new symmetries, right, CPT, that's basically all Sachs did is redo that program, and he ends up with the background pair gas that is equivalent to the vacuum pairs or the quantum vacuum type of thing. So, and you don't get the infinities, right? That's the thing with the quantum vacuum. We're skeptical of that because there's infinities that get involved, and there's little tricks that you have to do to renormalization tricks to ignore those, right? So the basically nonlinearity, you have to correct, mess around with the math to get right answers. But the issue I have with it in terms of quantum field theory and those things is that it's more of like a after prediction, right? That approach has been going on for a long time. So basically you do experiments, and later on you figure out how to calculate it with QFT or what have you. And that's not what I'm hoping that we go the other way and we're able to like actually use it to make predictions, right? So I bring up the Brett Wheeler process.
And the Higgs particle were predictions of general relativity and the standard model that took decades to experimentally confirm. And those are like, the two most expensive experiments like of all time, right?
Yeah. The Higgs was something that was predicted It doesn't necessarily do what a lot of people think it does, but it does do something. and you know,
the question is there a proportional relation between the experimenter effect and the cost spent on an experiment?
Yeah, well, who's to say about that? But I'll tell you that I wasn't interested in being involved in that. So I personally, I don't think it was worthwhile. It's good to complete that model, right? So now they think it's complete, but of course they want to still build bigger colliders or do other higher energies.
I'm just saying, nobody has tried to actually. No one's able to compute the UV corrections to Lovelock gravity, and progress has been made in the past decade that no one is really paying attention to. So there is progress in understanding how to quantize general relativity by having higher energy modifications, but everyone's kind of moved on from looking at gravity as a quantum field theory for the past 30, 40 years. So there's just a very small camp. Well, you know, even Nima Arkani Hamed is kind of.
What does that mean?
What David? What
those words that just came out of your mouth, David? What does those words actually mean in English?
Okay, so you can have gravitational waves, and you can study how they would scatter and the probabilities of the outcomes of the momenta and the directions that they travel when you scatter these waves, and you can calculate what you would get for these probability amplitudes, for these scattering amplitudes, in some theory of quantum gravity. Just taking general relativity as a quantum field theory, which is used in quantum electrodynamics as one example of the quantum field theory. And so they originally calculated that there would be, the probabilities would essentially be infinite. And they call them UV divergences because UV is like high energy light. So it's a high energy divergence because they were doing these integrals over momentum space, and at high momenta is where these infinities were popping in. And so that's honestly, in my view, that's like like if that problem was, if progress was made by Zvi Bern 40 years earlier, you know, everyone would have been less likely to question, you know, what if gravity can't be quantized, because like progress has been made. I'm not saying it's the right theory. I'm just saying, like, you know, it can be approached.
I think, David, to me, when I think of quantum, I think of basically wave effects. And so, yeah, with gravity, you would probably have in certain scenarios, you would have wave effects that you can have a descriptive model for. But to me, that's not understanding, or that's not moving it forward. That's taking like low energy approximations of the full thing. I understand what you're getting at.
Well, I mean, quantum gravity would only matter at high energies. I mean, it's a weak force, and you know, I mean, the real problem is there's also not experiments that we can come up with to prove quantum gravity because so energetically inaccessible.
So okay, so at higher energies you get gravity waves, but those gravity waves, okay, it's proportional, right? You could have these kind of low energy in relation to that theory. What comes out in terms of waves that are, you know, have linearity in the domain that they're in. Okay, that's what we're discussing. So what I'm trying to get at is looking at the quantum idea. Is that really applied to all domains appropriately? Okay, are there limits? That's the question, and it's looking like there are. So that changes, and it doesn't negate the work, but it just puts it in context of you know, it's within its domain. And so you have not
quantum effects can be slightly off, and we can reapply our understanding of quantum from just slight shifts in our understanding of what is the causal reason for quantum effects. You know, in other words, like that's what you were talking about with that. Well, all I could see with it being waves. In other words, you were talking about quantization having to do with the fact that a single wave can be, you know, can be compared to another wave, and there can be a minimum wavelength, and there are these effects that have to do with specifically with wavelengths, and then there's a quantization that can occur in wave phenomena. Correct? That's kind of what you were getting at there. That even that something that can be thought of as continuous when it's a wave-based phenomena can also show quantum effects because of the fact that waves can look like singular things. In other words, there are ways in which harmonics and interference and things of that nature can lead to the quantization.
So basically, in terms of what we're talking about here, propulsion, these theories that follow Einstein's path and take into account those symmetries end up with basically a vacuum spinor field that pervades the universe. Now, what properties that field has and how that gives matter, it's basically, again, symmetry breaking, right? And then there are basically, I don't know if I would call it torsion or how I would describe it, but there are basically nonlinear effects where matter can appear and interact with that field. And that's what we're getting at here in terms of what is being potentially done is some kind of subtle interaction with a pervasive vacuum field or vacuum spinor field. And that interaction, for us to figure out how to do that interaction, we need to figure out what that vacuum spinor field, what it consists of, how it interacts. And we do have proof of it. Again,
there's an experiment.
Matter, antimatter, annihilation, and creation is something that is done in the lab. So we know we can take energy, electromagnetic energy, and make particles and create particles. I mean, destroy particles, right? When we say destroy, what is really happening? They're probably reverting back to vacuum spinor fields that are outside of the domain.
That's all in the quantum field theory paradigm.
Yes, it is.
Yeah. So going back to the vacuum spinor fields, and there is an experiment that Sabine just covered about a week ago, where it's the name is an electromagnetic vortex cannon. Is the name of the video, and it's about a paper that's an observation of resilient propagation in free space skyrmions and toroidal electromagnetic pulses. So basically the idea is that once again they're treating the vacuum like a fluid, and they're able to project electromagnetic pulses as toroids. And so that is one, an interesting. And she actually kind of discusses the way in which we see these vortex fields, which in a 3D space they're going to require that it be a spinor type of formation. And so it just kind of relates back to what you're saying about a spinor field vacuum, which is I'm proposing as this as fluid dynamics in nature, fluid dynamical in nature, and this experiment actually is one of those things that I think that this community really should be very interested in. The one that she just covered in that video, because it is a way in which they're manipulating the vacuum in a novel fashion that really indicates a very fluid-like behavior in the vacuum, as well as a way of manipulating the vacuum. So that by itself really should be part of this community's experimental knowledge now.
Yeah, and piggybacking on that, Curtis, I'll have to dig up some work, but there's a way to actually get like Dirac spinors to actually kind of look like Maxwell's equations, but you have to go to these pre-potentials or Hertz potentials kind of, or I think they actually discuss the Whittaker potentials, but they're kind of the same thing. And if you study the Wu-Yang dictionary, you can ask, okay, is there something deeper to quantum mechanics? In quantum theory, we have these force fields, and then, Hertz thought that these force fields, the electric and magnetic fields, the electric fields that Drew plays with, they thought that was fundamental. And then they realized, oh, wait, there's this electromagnetic potential. And eventually, the Aharonov-Bohm effect basically experimentally validated the idea that the potentials are what's physical. But Einstein was saying that, hey, wait, like, what if quantum mechanics isn't what fundamental? General relativity had a metric, and then it had a connection, and then there's a curvature. But the connection is like the potential, the electromagnetic potential. So if there's something deeper to quantum mechanics, and you look at the Wu-Yang dictionary, it's like, what is the gauge theoretic analog of the space-time metric? And the Hertz and Whittaker potentials fit in there. and the Hertz potentials allow for a superfluid interpretation, which could have topological structure. And you could eventually invent non-abelian Hertz potentials and see if you can get some vortices of the ether to leave two fundamental particles. And various researchers are trying that. So that's kind of one of the perspectives I've been looking at. But yeah.
Yeah, and again, I'll say that was already been done in terms of not with the particular Hertz potentials and just looking at Maxwell's equations, but treating that spinor field and that approach of generalizing gravity with the symmetries that we know now. And so, yeah, there's a topological approach, and you get these Coxeter numbers.
So what spinor field are you referring to? Because usually, like let's say you just have an electron, you described it as a Dirac spinor. That spinor field has classical modes and these virtual modes, and so now you're saying that there's like this vacuum spinor field, but it's like, which field is it? I mean, or are you saying there's some other unified field thing we haven't that's my problem with a lot of these like theories.
I'll send it to you.
Okay. Yeah.
I'll say it's pretty. I'll send you the papers, but basically, this work is taking the next steps from where Sachs left off. It's more mathematical. It's done by a mathematical physicist, not a physicist, but anyway. So he ends up using the Coxeter numbers in a topology to basically calculate the masses from the standard model, treating the electron as mass of 1. So he gets most of the masses within 1%. The pions are 25% off, or somewhere around that. But I think there's certain assumptions that he made that are probably things that we might not do realistically. But yeah, it's a lot further than Sachs went, because Sachs he basically only calculated the mass of the electron with his theory. He didn't calculate the other particles, from what I recall. So, and it's that kind of approach that you're describing. It sounds very analogous. Again, the whole thing about the field theory that Sachs did, removing that symmetry, when you take Einstein's approach, you do get the full Maxwell equations from the antisymmetric part of that formulation. So it's all there. That being said, I don't know if it's right. we got to do experiments. We got to look at it, and it could be that that vacuum spinor field does exist, right? I mean, there's a lot of things pointing to it. Now, the thing about quantum, I keep bringing this up because we know that these quantum theories have quantum inbuilt, okay, and that's creating a linearity or problems for us that we may not need to address. Meaning that if we remove that as fundamental and we build up a theory, and if we linearize that theory and we can predict the same things that come out of quantum predictions, then I think we're fine. As long as our theory can predict experiment, then we're okay. I don't see why we need to keep retaining the quantum idea when it's shown experimentally, and people are saying that, okay, it's not basically it's not fundamental. So what domains does it work and not work, right? That's what we got to determine. And we don't know the domain we're talking about. We don't know if it applies and when it applies and how, is it all quantum effects, or is it something that there's more going on? And so that could be the difference between us succeeding and failing with this.
So one of the things that David was saying earlier is that he doesn't remember exactly why, but at some point he thought to himself that space may be a quasi-crystalline superfluid, and so going back to what you were talking about with a spinor field, whenever we think of a spinor, I always immediately think of the belt trick, and whenever you look at like the Wikipedia entry has good little visualizations of spinners, and basically what it shows is mechanical constraint. In other words, like if you have three-dimensional gears, and there's this great website where a guy actually tries to create three-dimensional gears that all rotate together, and he does a good job of it. His name is Bugman or something, I think. But the point is that there are mechanical constraints to three-dimensional gears that are not the same as two-dimensional gears. And basically what a spinner is doing is representing a field of three-dimensional gears. In other words, where they have to relate in three dimensions. So that is in other words, a very rigid and crystalline-like substance would have to gear against the nearby substance. In other words, the particles would have kind of a gearing effect. And I've actually, just like Oliver Lodge and those others had the rubber band model for for fields. A good way of looking at the idea of the stress tensors and things of that nature that would categorize our electrical fields and things of that nature would be to think of a set of foam gears. In other words, like foam is a little bit squishy, right? And a little bit it can actually flex a bit. And so if you had a set of foam gears and you had them all in a big grid, they could all turn just fine. What you could do is kind of stick your hand in there and squash them and make them misalign, right? In other words, you could take one of the teeth and move it to one of the nearby places, and then that tension would be spread throughout the whole set of gears, right? And so that's kind of a good analogy for how this stress energy could be described. But in this idea of a superfluid, which is, in other words, it's a superfluid at a higher scale, but at a lower scale, it's actually this more granular thing that is a quasi-crystal. And those quasi-crystals are actually gearing against each other. They're acting like teeth of gears, and they can become in that same way that I've just described, the gears being out of place from each other, where the teeth are locked in a place that is not natural, and so there's the stress that is shared throughout the whole set of gears. That same thing can happen in a fluid that is made up of these crystalline structures, and then it is only a crystalline defect that can come along and allow that stress to be released in what we see as electromagnetic electrons.
So I'll quote from Cohen's paper. So what he says is nonlinear interactions of opposite chirality components through the vacuum spinner fields creates the inertial mass of a bispinner particle. It also produces a gravitational interaction between particles. So that's the kind of like summary of the vacuum spinners producing inertial and gravitational mass. And that summarizes, there's a lot of math in there. There's a lot going on, and whether that's right or not, right? We gotta figure out experimentally. And this propulsion stuff, this is the experiment, right? Where we're determining whether that's actually happening.
Yeah, I really hope our experimentalists here get interested in that experiment that Sabina just covered, because being able to produce toroids in space, that is really, really interesting, really new and novel, and so because it's so cutting edge, I think that this group, if they were to try to replicate and play with that, they might find things before anybody else does, because they're a lot more open-minded.
Actually, isn't that the stuff that there's a fellow that talks about, Leonard? I think he's been talking about toroidal effects, like till he's blue in the face, sort of, right? So that's a well-known thing, and I think it's just a matter of
well, now it's at least a mainstream experiment that has been accepted, that they're actually projecting these free space skyrmions is what they're talking about, and creating toroidal electromagnetic pulses. So
and David Chester in the chat said elementary particles could be topological defects. That's exactly how they show up in the vacuum spinner field. That author talks about them as basically that kind of thing. So basically,
the particle would propagate. Like if you think of this set of gears, that you could have a bunch of these dislocations of the gear teeth that cause a stress in all the gears to each side of these dislocations, and then only when a space opens up between them, and it would rip through them like a particle. And basically, that is the crystalline defect, allowing the stress between the two sections of these gears that are locked together to be relaxed. Or, what we see as a particle propagation.
And I think to Drew's point, for us to get anywhere, we probably have to just there's the physics and the logic. We got to be clear about what we're saying. If it's something we can't explain, then we're just spinning our wheels, right? We got to get that. So I'm all for experiments. So I would love it if Drew's surfaces are interacting with that vacuum some way and pushing off against it. And like I said, one good experiment would be have an entire volume where you take inertial mass in there. If something changes, that would be very interesting, because if you're able to lower the inertial mass in a container, that's showing that what's really happening with inertia and mass. So.
And interested as you are, Curtis, in getting down to the very nitty gritty of our fundamental assumptions, I really look forward to you watching the video that I presented today, and because I think that it's going to be right up your alley, and I really would like to hear your comment on it. And I think that right afterwards, if you will eventually get back to that Miller 1933 paper, I think you're going to see a lot of things in a different light.
Yeah, thanks, Shiva. Yeah, Jared, I was going to ask you, how is it going with the arts parts? I know you gave a presentation. Are you did you move on from you're working on that now? Are you going to continue that spinning? What was it called?
The gravel flyer.
The gravel flyer.
Gravel flyer. Don't just go point to it. Go make that thing spin or fly or something.
Did you make any progress there?
So yeah, I've been working on the arts parts thing for the better part of the last few weeks. I haven't done decent gravel flyer stuff for a hot minute. I'm still planning on continuing testing on it though. I have David, Chester, and Tim are supposed to be coming by this way in a little bit, and we're going to spend some time together doing some gravel flyer testing, hopefully. The current next steps that we're working towards, we have, I don't want to say too much, but we have some irons in the fire that might get us some more information about this, hopefully, maybe. Yeah, I can't really say a whole lot more than that. I wish I could.
That's okay.
So hopefully if we can figure out some more stuff about this thing and how it's made. Now, I will say this. No, I shouldn't say that. I shouldn't say that. I wish I could say more, but it's going to have to wait a little while.
That's all right. That's all right.
Well, tell Tim to turn off the recorder so we can hear what you want to say.
Yeah, if we go off, then I'll totally tell you guys.
Sure.
Yeah.
Tim, where are you?
Well, guys, I can't turn off the recorder until we end the conference. I'm charging up my earphones. My earphones ran out of juice, so I got to charge those up for a few minutes.
We're not on Zoom tonight, so.
If your earbuds went dead, does that mean we literally talked your ears off?
Yeah. Yep. Yeah. But yeah, I mean, if you guys want, we can close things down now, or if you want to wait for maybe wait 15 minutes or so, it's up to you.
Sure.
Yeah. Sure. Wait. Sure. What? Sure. Should we end the conference?
I'm fine with hanging out for a little while. If anybody wants to put any arts parts question in the chat, it's probably going to be a couple of days before I get it. The arts parts presentation uploaded to my channel where you can see the links.
Okay. Well, why don't we? Do you want to close things down at 6 then, or do you want to go until you want to just close things? Give people a couple minutes to. I'll tell you. Why don't we do that then? We'll give maybe 2 or 3 minutes, and then we'll close things down a little early. Yeah.
There you go.
Yeah, it's been a tremendous conference. In fact, let me see if these things are charged.
Yeah, I wonder if there's any interesting comments from the audience that we can address. Maybe around this time in the future, we could ask the audience to put together some actual good questions about things that are going on.
How do we see this? Is that what's in those comments thing?
Yep,
yeah, over there on the right hand side.
Oh,
yeah,
dude, there's hundreds of them.
Yeah. Those are from folks on across 3 different YouTube channels.
There was somebody in there who their username was Bob Lazar. I'm not sure.
No,
if that's
that person is always here. That's not the real
Yeah,
Bob.
no.
There's literally hundreds of these things.
Yeah.
That's being live, man.
We're live. People are talking the whole time.
Who are all these people?
Oh, it's great. Drew suddenly is, in front of an audience. He didn't realize. Okay, let's see. Mendeleev proves 2 elements X and Y that are noble gases smaller than hydrogen. Those good candidates for ether. I don't know about that specifically. I would not think that that thinking of ether as an element is a good idea, because I believe that we were talking about ether. I can't really propose much about the ether other than I believe that it probably is a quasi-crystal, and the way in which that quasi-crystal works. Well, there's just not enough research. That's something that's basically going to be probably Planck scale, other than the behaviors that we see that are emergent from it. So, I do have an idea for what the shape of ether particles and the behavior for ether particles, and that they have 2 transitional shapes. But at a certain point, you have to kind of draw a line on any kind of causal, look at the world, because otherwise you get into infinite regress. And so the when it comes to ether particles, that's just not something that we're going to have. Even if we go, if the ether's right, let's go this direction. There's still going to be a period of time of experimentation, et cetera, before we can actually comment on that next layer down, in any authoritative fashion. Any other questions? You guys see any other questions in there? I don't really see any yet.
I saw one that was asking if we're still using Teflon. We pretty much don't use Teflon anymore. It soaks up charge too much, and it doesn't have it's just an unhappy material to play with.
Some of these comments are so silly.
Yeah, you guys are just going through the comments, so I'm
So I'll let me share my screen real quick for David's benefit. I think he's still there.
Yeah, David's here. He's hiding out.
Let me share my screen.
Oh, yeah.
Share entire screen.
I
Screen
missed
2.
this
Okay. And here's
Wow.
You guys see?
A lot of
Oh
them.
wait, no, that's a slide. Hold on. There we go. There's my screen. So there it is. That's on the right there. You can see basically the mass versus mass of an electron, and for the different particles, what's calculated and what's observed. So, like I said, the pions are the ones that are kind of off, about 25%. Most of the others are within a few percent. They're pretty close. So, there's reasons why I think that is, but I need to go through and work that out. It's a pretty involved theory, so it's taking me some time.
What is this chart?
This chart on the left is the particle. So you have the electron, the muon, the tau, etc. One of these is the
Is
proton.
that like
down at the
electrons
bottom.
and protons and
Yeah, down at the bottom
neutrons?
is the proton. Down at the bottom is the
okay.
proton. And then on the right here, there's the first the S over 2 cubed. That's the calculation using Coxeter numbers of the particular the Coxeter numbers here. This gives the S. It's a topological thing. Anyway, it gives what the mass would be if this theory is correct. These are the calculations, and on the right are the observed masses. So basically, you want to be close. These need to be close for it to be right. So, 25% is pretty far off, and that's for the pions here. Anyway, some of them are a lot closer than others. So there's more work to do. But this is a theory that, is basically taking the vacuum spinners, the one I mentioned earlier, as fundamental. Okay, and calculating masses. So there you go. That's where I'm at now with my own research.
So I have a question. Has anyone computed the rest mass of deuterons?
I think here that would be these are just the bare part, the fundamental particles. None of these are composites of that order. So you would for a deuteron, you would take a neutron, a couple positrons, right? Or a couple of neutrons and a positron.
Yeah,
So-
right now the standard model doesn't have the ability to compute it because, first of all, it models any proton or neutrons as three quarks, and the three-body question is unresolvable. It requires tons of parameters.
This theory does not use is not using the standard model.
Oh, okay.
Completely different. Yeah. So anyway,
somebody also mentioned asked if Tim had been able to invite Unzicker on here, and I would love to have Unzicker on if there's any chance of getting him on. That would be freaking great because I think he does a fantastic job of dealing with topological defects and looking at views of the ether in a novel fashion. So just a suggestion for Tim if there's any chance.
No, send me if you can send me his info. Send me his info, and I will.
Yeah, unfortunately, I don't have his info. I've never talked to him. I've just seen his channel and enjoyed it.
Let me dig. So Unzicker, you said?
Mm-hmm.
Okay.
Yeah, his channel is like Unzicker's Real Physics, I think, and I think he's a. And
I know you've sent me a couple in the past, and I've tried to, get in touch with them, get through.
Sometimes it's so hard to reach out to people.
Yeah.
But yeah, he would be great to have on here because he really does a good job of explaining some of those, and he knows a bunch of the researchers who have published papers on these topological defect versions of particles and in fluid dynamic versions of space, and so it's definitely a researcher that I have a lot of respect for.
Well, guys, I think we're just about getting there. It seems like things have wound down pretty well just in the last few minutes. So why don't we call it a night? And I'll leave things going in the background. Bring David in just very briefly, and let me thank all of you so much. In fact, why don't we close things out? Give yourself a hand for amazing presentations and lab updates. This has been APEC for September 28th, 2024, and an amazing conference session.